Without a shred of doubt, our worlds revolve around data. You draw money from the ATM, you've generated data. You purchase juice at the supermarket, further data is created. You clicked on this video, you get the gist. With all these resources in hand, we have realized that we can use this data to work smarter and innovate to make life so much easier. We have data with which we can come up with problem statements, but what methods can we employ to make inferences and act upon it? A subject like statistics is perfect for handling such problems and coming to good, useful conclusions from the information at hand. So, we have designed a full course on data science that includes the basic foundation of problem solving using statistics and implementing it in Python. Now, before we start off with the session, I'd like to inform you that we will be coming up with a series of high-quality tutorials on computer vision, cybersecurity, cloud computing, and so much more. So don't forget to subscribe to our channel and hit the bell icon to get a notification when we upload new videos. If you like this tutorial, don't forget to click on the thumbs up button and comment down below what you'd like to see next. Now, let's go through what you will learn in the first half. First, we'll discuss the contrast between statistics and machine learning. Then, we'll get you introduced to the different types of statistics, namely descriptive, prescriptive, and predictive statistics. Once that is done, we can explore the various types of data. Then, we can understand correlation of data and how important it is for data science. We will also cover the topics of covariance of data. This course will be taught by Dr. Abhinanda Sarkar, who has his PhD in statistics from Stanford University. He has taught applied mathematics at the Massachusetts Institute of Technology. He has also been on the research staff at IBM and led the quality engineering development and analytics function at GE. He has also co-founded Omics Labs. Without any further ado, let's get into the statistics for data science module. It's time for some great learning.
What you now need to do is you now need to be able to get the data to solve this problem. So therefore, the statistical way of thinking typically says you formulate a problem and then you get the data to solve that problem. The machine learning way of looking at things typically says, here is the data, tell me what that data is telling you. Many of my colleagues and I myself have run into this problem when going for interviews, etc., etc. And so, sort of statisticians say that we're not getting jobs out there. And so I go to people who are hiring and saying that, why don't you hire statisticians? And I reach an interesting conclusion to this entire discussion, that sometimes around the way the interviewer who's interviewing the statisticians for a data scientist job asks the question, here is my data, what can you say? And the statistician answers with something like, what do you want to know? And the business guy says, but that's why I want to hire you. And the statistician says, but if you don't tell me what you want to know, how do I know what to tell you? And this goes round and round, right? No one's happy about this entire process. So there's a difference in the way these two communities approach things. My job is not to resolve that. Because in the world that you will face, you'll see a lot more of this kind of thinking than you'll see in this kind of thinking. Because in this world, the data is cheap and the question is expensive. And you're paid for asking the right question. In this world, the question is cheap and the data is expensive. You're paid for collecting the data. So sometimes you will be in a situation where this is going to be important. For example, let's suppose you're trying to understand who's going to buy my product. You're asking the question, let's say that my products aren't selling, and you want to find out why. What will you do? Get what data? So let's say that you're selling, I don't know, what do you want to sell? You want to sell watches, say? So let's suppose people aren't buying watches anymore, which is a reality, correct? So you're a watch company. Who buys watches these days? The entire business model of a watch is disappearing. Do you have watches? Some of you have. Right? He has. Actually, a surprising number of you have. Maybe they do different things these days, right? That seems like a very, that's a fitness device, is not really a watch at all. So something like this was actually with my daughter at lunch today. So she got something like this. I'm not sure. My wife, who's an entrepreneur, runs her own company. She came back from Delhi. She came back with 2 of these. I don't know where she picked them up. So my daughter, the first thing she did, she took one of this and she took this thing out. Because she thought of the whole wristband as an unnecessary idea. I mean, that didn't occur to her. I mean, that's a separate thing. That's a nice little beautiful red wristband, etc. So a watch is a different thing. But let's say that you're a watch company, nobody's buying your watches. Or fewer people are buying your watches. Now, how are you going to solve this problem? Or how are you going to process this information? What do you want to do? What do you want to know?
Check the models testing, do not say.
Okay. But remember, I'm asking this question also from an analytical perspective. So when you say that, to check the model and see what is not sold, that assumes the whole data question. So first order, you'll see sales. For whom and when and how? How do you structure your data? How will you arrange the problem?
Let's say what are your competitors selling?
Okay, that makes problems even harder because now you're going to look for data that isn't with you. No, he's right. Maybe people are not buying watches because they're buying something else. That's a reasonable thing. But let's keep this problem simple. Let's consider only data that is within you. We'll go outside, not to worry. But let's say that I'm looking at my data. What data do I want to see and what questions do I want to ask of it? So sales year by year, types, and then what comparisons do I want to do?
Year on year.
Year on year?
Region wise.
Region wise, age. With what purpose? What question am I asking the data?
What section of customers are buying my product or
what section of customers are buying my product compared to what?
What has changed in terms of the
what are my biggest set of customers?
So that's one thing. Who are my biggest customers? Okay. That's a very interesting question to ask, except that question implies that I needed to know who my biggest set of customers sort of could have been. But it's a good point. Where is the bulk of my sales coming from? Then someone else says something about time. Is it going down? So you can look at things like saying that for which group of customers are my sales going down the most? For example, you could ask that. I'm not saying that's the right question, but that's a possible question to ask. So let's suppose you follow that approach, that I'm trying to understand. I know that my sales are going down. That's an obvious thing. My CEO is telling me, my CFO is telling me, and if I don't stop this, we're all going to be out of a job. Correct? The HMT factories in Bangalore are not in good shape. One of them, I think, has become the income tax office. Right, somewhere in the Malleshwaram area. So that's going to happen to me if I don't do this well. So I know my sales are going down. But I don't know by how much and particularly for whom. So are there segments for which the sales are going down? Which segments are sales going down the most? In which segments are they going down a little bit? How fast are they going down? I can ask questions of that sort. Now, what conclusions at the end of this do I want to be able to do? How do I want to use this information? Now, for this, you usually follow something like a 3-step process, and you may have seen this, and this covers both these sides. And these words should be familiar to you to some extent. The first is called descriptive. The second is called predictive. And the third is called prescriptive. Have these words been introduced to you, at least in this at least you've read it, I'm sure. You all cruise the web and look at blogs and things like that. Nothing new in this, I'm sure. But I just want to set a context because it's going to talk a little bit about what we're descriptive. There's a C here. So descriptive, predictive, and prescriptive. Now, what is a descriptive problem? The descriptive problem is a problem that says that describe for me where I'm losing my sales and when I'm losing my sales. It just describes the problem for me. It tells me where the problem is. It locates it. It isolates it. The predictive problem says, look at this data and give me an idea as to what might happen Or what would happen if I change this, that or the other. So let's suppose I do the following kind of idea. I say that, let me relate my sales to my prices. Let me try and understand that if I reduce my prices of my watches, will more people buy them? Conversely, if I make my watches luxury items, increase the price of a watch, remove a low-end brand and make a watch an aspirational thing, a decorative item, a luxury item, a brand item, so that people wear a watch not to see the time but also as a prestige statement, as a fashion statement. Whatever it is, if I do this, then what will happen? That's predictive. I'm trying to predict something based on it. I'm trying to say if something happens to, let's say, one part of my data, what will happen to the other part of my data? And then based on that, the doctor carries out a predictive analysis of you. Because I see this, I now think you have this issue. You have this thing going on. Let's say I'm diagnosing you as being pre-diabetic. You're not yet diabetic, but you're happily on the way to becoming a diabetic. Now, because of this, I now have to issue you a prescription. I now should tell you what to do. So there's the data that comes from you. That data in some way is modeled using the domain knowledge that the doctor has. And that model has translated into an action. That action is designed to do something. Typically, it's designed to do something actually fairly complicated. The first action that the doctor tries to do is, number one, let's say, do no harm, the Hippocratic Oath. First, let me make sure that I don't do any unnecessary harm to the patient. Then let me, shall I say, optimize his or her welfare by making sure that I control the blood sugar the best and that I postpone the onset of diabetes as best as I can. It's a complex optimization problem of some sort. In a business also, it's a complex optimization problem. Right? I need to be able to sell more watches. But I also need to be able to make money doing so. I can increase my sales, but if I increase my sales and my profits go down, or my earnings go down based on the cost, then that's a problem. But at the same time, if I try to run a profitable business and nobody buys my product, that also is not a particularly good idea. Then there are other issues maybe in running the company. I've got employees that I want to keep on the boards. How do I run the company in such a way so that it needs that particular labor force? I have finances to take care of. I have loans to repay. How do I get the cash flow in order to repay the bank loans that I have? So the prescription has to meet lots and lots of requirements. If you are building an autonomous vehicle, you'll have situations saying the car has to do this. But it also has to follow certain other rules. For example, if it sees someone crossing the road, it should stop. But it shouldn't stop very suddenly. Because if it stops very suddenly, it's going to hurt the car, it's also probably going to hurt the driver. So it needs to stop, but it shouldn't stop too suddenly. It has to follow the rules of the road. Because otherwise the computer will simply say, oh, you want me to avoid the person crossing the road? I'm just going to go behind the person. And you're going to tell the car to please don't do that because there's a house next to it. You can't just sort of do that. Oh, you didn't tell me that. You just told me to avoid the person. You didn't tell me about the house. Okay, we'll put that as a constraint in our program and see how well it goes. So prescription is problematic. Another simple way of doing it might be to say that description is how many centuries has Virat Kohli scored. Look up Cricinfo and it will give you the answer. Prediction might be try to guess how many centuries Virat Kohli will score in the World Cup. Prescription might be how do we get Virat Kohli to score more centuries in the World Cup. And as you can figure out, you're going from a purely data-based version of the problem into something that's only notionally about the data. Data will help you, but there's a lot more than the data when it gets to that. What we'll do today, what we'll do now, once I've finished talking to you, is we'll take a look at what the descriptive part of analytics is. So the descriptive part of analytics is talking about simply describing the data without necessarily trying to build any prediction or any models into it. Simply telling you the way it is. This is hard. This is in itself not necessarily an easy thing to do, because you need to know very well how to do that and what are the ways in which one looks at data. This is skillful in itself. So, for example, let's suppose that you're a doctor. You go to the doctor, and the doctor is looking at your symptoms, and the doctor recommends a blood test. Now, how does a doctor know what blood test to recommend? Based on the symptoms. But remember that potentially there's an enormous amount of information in you. All of us as biological things carry an enormous amount of information in our blood, in our neurons, in our genes, or wherever. You know, if you're talking about big data, as I said, there's 2 meters inside every cell, and there are a few billion neurons in your head. You don't need to go far to see big data. You are big data. You are one walking example of big data. We all are. Right? Now, in that big data, what little data does the doctor know to see? That's a descriptive analytics problem. The doctor is not doing any inference on it. The doctor is not building a conclusion on it. The doctor is not building an AI system on it. But it's still a hard problem. Because given the vast amount of data that the doctor could potentially see, the doctor needs to know that this is interesting to me, and this is interesting to me, and this is interesting to me. And this is interesting to me in this particular way. For example, a blood test. Let's suppose that I draw blood from you for a particular purpose. Let's say for blood sugar. Correct? Leaving aside the biology of how much blood, etc., to draw. None of you, I guess, are a doctor. Any of you are doctors here? Any doctors in the room? No doctor, so I can say whatever I want to. You won't understand what I'm saying. No, but I'm old enough that this is a real problem for me. So you have a large amount of blood that's flowing through you. We all do. This blood carries nutrients. What that does is that every time there is a nutrient inflow, the blood looks a little different. So if you eat, your blood looks a little different. Because that's your blood's job. The blood's job is to carry nutrients. So if you want to run, you want to walk, if I'm walking around, my legs are getting energy from somewhere. The energy needed to my legs is being carried from the blood, and it is being generated through inputs that I get. Some of it because of the air that I breathe, from where it gets the oxygen to burn things. Some of it from the food that I've eaten, the nice lunch that I had, where it gets the calories to do that. So therefore, based on what my energy requirements are, and based on what I've eaten, my blood is not constant. My blood content is what is known as a random variable. What's random about it? Because it looks a little different all the time. Your blood at 12 o'clock is going to look a little different. 12 o'clock at midnight is going to look a little different from 12 o'clock at noon. Because it's doing something a little different. The same phenomena is there everywhere. If I were to, for example, measure the temperature of the oil in your car or in your two-wheeler, what do you think that temperature will be? It depends. First of all, it depends on whether the car is running or not. It depends on whether it has run or not. It depends on how much oil there is. It depends on how you drive. It depends on the temperature rest of the car. The answer is it depends. And the same is true for your bodily fluids. So this becomes a slight problem. Because if it is random, then from a random quantity, how do I conclude what your blood sugar is? How does a doctor reach a conclusion of any sort? Average of what? Average of particular duration. So there are multiple averages that you can get. First of all, there is a question of saying that if I take blood from you, how is the blood usually collected? So the phlebotomist comes and usually takes an injection from one point. Let's say by some strange accident, this is thoroughly inadvised, but let's say by some strange accident, 2 different people are drawing blood from 2 hands at the same time. Do not try this at home. But let's suppose they do this. Will they get the same blood?
Depends. Ideally, yes.
Ideally, yes.
It depends.
What time it is?
Two different.
Same time. Right, at the same time, as I said, do not do this at home. But at the same time, you're getting two different samples. There's not just a question of time. Your blood is not going to look the same even within your body at one period of time. Even from the left hand, even from the right hand at exactly the same period of time, it's not going to look the same. There is a slight problem that's somehow a little obvious, that you know your heart is in the middle. Right? Your heart is actually in the middle, but it beats to the left. Why? Because the heart is what? The heart is both a pump and a suction device. The pump side is on the left, the suction side is on the right. So your blood pours out from your left side and it goes back in on the right side. So there's a slight asymmetry in your body between left and right. One side tends to go out, the other side tends to come in. It's slight, it mixes up all in the middle. So one sampling idea is that I'm taking a sample of blood from you, and it's just one example. The second question is, as you were saying, it's a question of time. So you can average over time. Now if you average over time, this is a little easier. You can say I'm going to do this maybe before eating, after eating, a little after eating. So for those of you who have blood pressure tests, for example, blood sugar tests, once they ask you to do it, fasting. And then they ask you to do it some 2 hours after eating. Do they tell you what to eat? Sometimes with glucose. Okay. Sometimes they don't. They sort of say that based on what you naturally eat, let me figure out what you are processing. They expect you to eat a typical meal and not go and eat, large amounts of KFC if that is not what you normally eat. Just eat what you normally eat. If you're vegetarian, eat normal vegetarian, eat normal food, and then figure it out. Let's see how good your body is at trying it out. So it's saying, do a normal thing, and I'll take another normal sample. Then one of you said something very interesting. They average things out. Now, what does averaging do?
Neutralize.
That's an interesting word to use. Neutralizes things.
Provide a general idea.
No.
Provide context.
Provide context. Context of what? Context. That's a good point. So what is the doctor trying to do? So let's simplify things a little bit and say that, let's suppose that the doctor has a threshold. Let's give it a number. Let's say the doctor says that if your blood sugar is above 140, I'm going to do something. If your blood sugar is, say, less than 140, I'm not going to do anything. I don't know whether this is the right number or not, but just let's make it up. Now the doctor is going to see from you a number. It may be a single reading, it may be an average, it may be a number of things. How is the doctor going to translate what they see from you and compare it to the 140? How is that comparison going to be made?
Maximum number of people.
Normalizing the values.
Maximum.
So let's suppose I have just one reading. So let's suppose that I have one reading, and that reading, I don't know, is 135. I've just got one reading from you, 135. What does that tell me?
Standard, how much it is needed.
No test required.
No test required. One argument is, it's simple. Let's take a very machine learning computer science view to this. 135 is less than 140. So now he's saying, yeah, but you know what? Let's say that 135 and another guy who say 120, there should be something that says that this 135 is a little bit more trouble than 120. Closer to the threshold, as he says. So maybe, in other words, this threshold isn't quite as simple as I thought it was. So I can solve this problem in one of two ways. One way to do this is to make this 140 a little range. This is sometimes called fuzzy logic. Right? In other words, the question you're asking becomes fuzzy, not as crisp. You're not fiddling with the data, you're fiddling with the boundary, you're fiddling with the standard. The other way to do that is to create a little uncertainty or create a little plus minus around the reading itself, around 135. Saying that if this is 135, and let's suppose that I go and get another reading, and the second reading that I get is, say, 130. And the third reading that I get on the day after that is say 132. And I'll say, okay, seems to be fine, I might say. But let's suppose after 135, the guy goes in, I do my usual thing, and I measure it again. And this time, it comes out as 157. And I do it again, and it comes out as 128. And I do it again, it comes out to be 152. So, in both cases 135 was probably a good number, but in one case 135 was varying very little, and in the other cases 135 was varying a lot. Which gives me different ideas as to how to process it. So what descriptive analytics talks about, essentially, is trying to understand certain things about data that helps me get to conclusions of this kind a little more rigorously. Now, to be able to quantify what these plus minuses are is going to take us a little bit of time, and we will not get there this residency. We'll get there next residency. To say that in order to say it's not 135 but 135 plus minus something, that question now needs to be answered. But to do that, I need to have two particular instruments at my disposal. One instrument that I need to have at my disposal is to be able to know what to measure. I need to say, what does an error mean? I need a statement that says that maybe I'm 95% confident that something is happening. I'm 95% sure that this is below 140. I need a way to express it, and that is the language of probability. So, what we will do tomorrow is we'll introduce a little bit of the language of probability. It will be sort of unrelated to what we're doing today, so there's going to be a little bit of a disconnect. But what we're going to do is we're going to create two sets of instruments. One instrument that is purely descriptive in nature, and one set of instruments which is purely mathematical in nature, so that I can put a mathematical statement on top of a description. And the reason I need to do that is because the pure description is not helping me solve the problem that I've set. So therefore, what will happen is, you will see in certain medical tests, you will not see points like this, you will see intervals. Your number should be between this and this. Your cholesterol number, your HDL, whatever, should be between this and this. You won't see a number, you will see a range that typifies a variation. And in certain cases, you will see thresholds, and maybe it's just a lower limit or an upper limit, but you'll also see a recommendation that says, please do this again. In other words, I'm going to compare, I can't compare one number to one number. One number to one number is typically a very bad place for any kind of analyst to be in, because you've got no idea of which is error prone and where the error is. So therefore, what happens is you try to improve one of those numbers. And so either by fiddling around with the range or by getting more measurements. And you'll do that, and you'll see that as we go along a little later. So this is a context for what we have. In terms of data, let's see. So this is a set of files that has been loaded. It's a very standard set of files. It's not mine, to be honest. I just want to make sure that I'm doing what I'm supposed to be doing. So for reasons that are more to do with security, my understanding, the notebook will not access your drives. So keep it on your desktop and not complicate life. So, and there is this notebook. It's called Cardio Goodness of Good. The word statistics refers to the idea that this comes from the statistical way of thinking, which, as I said, opposed to the machine learning way of thinking, tends to be a little more problem first, data next, which means we worry about things like hypothesis and populations and sampling and questions like that. And the descriptive part refers to the fact that it is not doing any inference, it is not predicting anything, it's not prescribing anything, it is simply telling you what is there with respect to certain questions that you might possibly ask of it. Now, what is the context to the case? The market research team at a company is assigned the task to identify the profile of the typical customer for each treadmill product offered by the company. The market research team decides to investigate whether there are differences across product line with respect to customer characteristics. Exactly what you guys were suggesting that I should do with respect to the watch. Understand who does what. Entirely logical. The team decides to collect data on individuals who purchase a treadmill at a particular store during the past 3 months. Like watches, they're now looking at data for treadmills. And that is in the file, in the CSV file. So what you should have is, you should have a CSV file in the same directory, and through the magic of Python you don't have to worry about things like path. Before we get there, remember, because we're looking at this statistically, before we get the data we should have a rough idea as to what we're trying to do, and so they say that here are the kinds of data that we are looking at. The kinds of products, the gender, the age in years, education years, relationship status, annual household income, average number of times a customer plans to use a treadmill each week, average number a customer expects to run walk each week, on a self-rated fitness scale on 1 to 5, where 1 is in poor shape and 5 is in excellent shape. Some of this is data, some of this is opinion. Some of this is opinion masquerading as data. Like for example, number of times a customer plans to use a treadmill. Hopeful, wishful thinking. It's still data. You're asking someone, how many times will you use it? Her rows, daily, no problem. 7 times a week. Oh, we'll see. But it's still data. It's come from somewhere. So what has happened, the way to think about this is to say that I want to understand a certain something. And the certain something has to do with the characteristics of customer characteristics. And to do this, you can then use you can either take, let's say, a marketing point of view, who buys. You can also take a product engineering kind of view, what sells, in other words, what kind of product should I make, etc. In business, as you probably know, for those of you who are, any of you entrepreneurs? One hand up. One hand up. There are closet entrepreneurs from what I could figure out. Right. Sometimes it's unclear what that word means. In other words, you think you are, or you're not confident enough to call yourself one, or you're doing that. In IT space, if you're an entrepreneur, for example, in physical product space or even in software space, one of the things you often think about is what's called the product market fit, which is you're making something. How do you match between what you can make and what people will buy? Because if you make something that people do not buy, that doesn't make any sense. On the other hand, if you identify what people buy and you can't make it, that also doesn't make too much sense. So the conclusions that we will draw on this, we will not draw on today. But the purpose is to be able to go towards the conclusions of that kind. Either isolate products, isolate customers, and try and figure out what they tell us. Pandas generally has a fair amount of statistics built into it. That's what it was originally built for. NumPy is something that was built more for mathematical problems than anything else. So some of the mathematical algorithms that are needed are there. There are other stat plots in Matplotlib or Seaborn and many other things that you've seen already. Python is still figuring out how to arrange these libraries well enough. Shall we say, the programming bias sometimes shows through in the libraries. So I, for one, do not remotely know this well enough to know what to import up front. But a good session, you know what to import up front and you do all this up front. So you don't get stuck with what you want to do. The naming is up to you. If you like the names as they are, then that's fine. If you want a standard set of names. So when you wrote the data set, if this is in the right path, just this will work. .csv. It's usually smart enough to convert Excel forms into CSV. In other words, if you have this as XLS and things like that, it's usually smart enough. But if it isn't, then just go in and save an XLS file as a CSV file and operate that way. In case it doesn't do it on its own. But more often than not, what you see is that when Jupyter sees it, it will see any XLS file as a CSV file, or go and make the change yourself. Or you can have other XLS, other restatements in it as well. You can change functions inside it and you can figure out how much to head. What this tells you is there's the head and the tail of the data. This is simply to give you a visualization of what the data is. This gives a sense of what variables are available to it, what kinds of variables they are. We'll see a little bit of a summary after this, etc. So for example, some of these are numbers. Income. What is income? Income is annual household income. That's a number. Some, for example, let's say gender, male, female, this is a categorical variable. This is not entered as a number. It's entered as a text field. If you are in Excel, for example, right at the top, if you go in and you see that, it will tell you how many distinct entries there are, how many distinct settings there are. So usually what happens right at the beginning, and a data frame like this, if it is created, this is a data frame. If a data frame is created, when it gets created, the software knows as to whether it is talking about a number or whether it is talking about categories. There are certain challenges to that. You can see one particular challenge to this. What does this 180 mean? Counts. Why do you think there are so many decimal places that comes here? 14 years of experience, 16 years of experience. Why is it going 0, 0, 0, 0, 0, 0?
No, that's because mean, median, low are the next.
By default,
Yes, it does this because it sees other numbers where those decimal places are needed. So what it does is, what any software typically does is, when it sees data, it sort of says that at what granularity do I need to store the data. Sometimes this is driven by your computer, your 64-bit, your 32-bit and things like that. But what it does is, it means that the data is stored in the data frame to certain digits. Now, usually you don't see that, you'll see it in this way. But sometimes, for example, when you say include equal to or and you ask for a full description, the data comes out in this slightly irritating way. Because of something here, because of, let's say, the income field or any of that. Now, when it looks at the descriptions of this, what is the description that it is reporting and how does it choose to report out the description? In this particular situation, so let's take a little bit of a closer look at this. One thing here, look at the way it's done here. So count, unique, top, frequency, and then there are certain things here: mean, standard deviation, minimum, 25%, 50%, 75%, and max. When it sees a variable like gender, it reports out lots and lots of NANs. What does that tell you right off the bat? It can't do that, which means it's not a number. This is not a number. In other words, if you ask me to find the mean of something and you're giving me male and female as inputs, I don't know what to do. Which is an entirely reasonable stand to take for any reasonable algorithm, right? It requires another kind of description for it to work. But the problem with this syntax is that it's asking for the same description for all of them, whether it's in significant digits, whether it's in columns, etc., etc. So it's chosen this description and it says that that's all that I'm going to give you. But where it makes sense, let's say for example I look at age. Now for age I've got 180 observations and it is calculating certain descriptions for it. Correct? So what are the descriptions it is calculating? Let's look at these. It's calculating a description like, say, minimum. Minimum is what? 18. Maximum is 50. These are easy to understand. Then let's look at something a little interesting. Suppose I want to report one number, one representative age for this data set. This is like asking the question, how do I get a representative blood sugar number for you? I can give you a minimum and a maximum, but to do the minimum and maximum, I need to draw blood many times from you. But let's suppose I want one representative age for you. Somebody asks you, what is your blood sugar? You want to give them one number. Similarly, somebody is looking at this data and asks the question, give me a representative age. How old is your typical user, or what age do you want to build it for? Or you're even asking, let's say, a product question. You're a product designer, and a product designer building a treadmill. Now, how do you design a product? Those of you who are engineers, based on the weight. Now, very good. What weight? Whose weight? Who's the user? What is the weight of the user? He's got a good point. As a design engineer, I need to know what weight will be on that treadmill. Now, what is the answer to that question? Max?
Users who visit the gym.
So there's a question of saying that if I want to measure a variable by one number, how should I even frame that question? What makes sense? What is a one average? No? Max? In this particular case, you might argue the max is the right number, because I want to be able to say, if I can support him, I can support anyone. But there's also a downside to that. I've now engineered that product. You could argue that I have, shall I say, over-engineered that product. Correct?
Factor of safety.
I'm sorry?
Factor of safety.
A factor of safety? Okay. Alright. So let's suppose that you are doing this for a mattress. You all sleep on mattresses. We're all relatively wealthy based on the fact that we're here. So we probably sleep on a mattress. Not everyone's fortunate enough to sleep on a mattress, but let's suppose you do sleep on a mattress. How much weight should that mattress be designed to bear? If you over-engineer it, what will happen is that, number one, for a reasonable weight, let's say weight a lot below that, that mattress is not going to sink. Let's say that you design it for 100 kilos. Now, if you're 50 kilos or 60 kilos, that mattress is not going to sink for you, because it's going to feel comfortable for someone who is 100 kilos. And for someone who's 50 kilos, you're just going to bounce on it. You're not going to feel its soft silkiness or whatever it is you want to feel from the mattress. It won't work. So what to do? So that's a hard problem. It's a description, but it's a hard problem. Who do I engineer it for? And so therefore, people have different ranges of what I mean to represent it. So here's one version of it. This is what is called a 5-point summary. I report out the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Variable by variable, I report 5 numbers. I report the lowest. What does 25% mean? 25% of my data set, or the people, are younger than 24. The youngest is 18. 25% or a quarter of them are between 18 and 24. A quarter are between 24 and 26. A quarter are between 26 and 33. And a quarter are between 33 and 50. This is what is known as a distribution. This is what is known as a distribution. Statisticians love distributions. They capture the variability in the data and they do all kinds of things with it. So I'm going to draw a typical shape of a distribution. We'll make more sense of it later on. This is a theoretical distribution. A distribution, for example, let's say has a minimum, has a maximum, has say a 25% point, has a 50% point, it has a 75% point. In terms of probabilities, there's 25% here, 25% here, 25% here, 25% here. If you want to think in terms of pure description, this is not a probability, it's just a proportion. If you want to think in terms of probabilities, what this means is that out of 180 people, if I draw one person at random, there's a 25% chance that that person's weight is going to be below 24. Sorry, age 24, correct. If you want to think in terms of probabilities, we'll do that tomorrow. But this is a description. So what this description does is it gives you an idea as to what value to use in which situation. So for example, you could say that I'm going to use 26 as my representative age. If I do that, what is the logic I'm using? This 25%, this 50% point, so to speak, this is called the median. This is called the median, and we'll see it. Median means the age of the average person. First sort, take the middle person and ask, how old are you? The age of the average person. I could also ask for the average age of the person, which is what? Which is the mean, which is 1 over n x1 plus xn. Now this is algebra. What you have to do is you have to put n equal to 180. This is the first age, the second age, the third age up to 180. 1 by 180, age 1 plus age 180. This is called the mean. This value is what? 28.79. The average age is about 28 years or 28 and a half years, 28.8 years. But the age of the average person is 26. Yes?
So could you please repeat the median and the mean?
The difference between the two?
You described what is the age of the person.
So I described the median as the age of the average person, and I described the mean as the average age of a person. Now he's looking at me like saying, you have to be kidding me, right? That's confusing. I admit to it. The easy way to understand it could be this. What is the mean? Add them all up, divide by how many there are. What is the median? Sort them from the smallest to the largest, pick off the middle. If they're an even number, what do? You take the average of the two middle ones. If they're the same, it'll be the same number. If they're not, it'll be a number between them. So sometimes the median may show up with a 0.5 or something like that for that reason. If there is an integer counts, but there are an even number of counts. Now, which do you think is better? You're giving the right answer. It depends. You'll figure out that I like that answer. They both make sense. They both make sense. It depends on what context you're going to use it for. In certain cases, yes.
You said that median is basically the mean of the.
It's the age of the average person. It's a reading from the average person.
So what is the parameter we are saying it is the average person? How we are getting that average?
Okay. So if you're talking in terms of parameters, so he used an interesting term. He's saying, what is the parameter I'm after? Parameter is an interesting word. Parameter refers to something what generally in a population. It's an unknown thing that I'm trying to get after. For example, blood sugar is a parameter. It exists, but I don't know it. I'm trying to get my handle on it. Correct? So if I'm thinking in terms of parameters, then these are different parameters. So let's look at a distribution here. I'm not sure whether this will pick up things. I hope so. So the median is a parameter such that on this side I have 50% and on this side I have 50%. This is the median. The mean is what is called the first moment. What that means is, think of this as a plate of metal and I want to balance it on something. Where do I put my finger so that it balances? It is the CG of the data, the center of gravity of the data. You can understand the difference between these two now. If, for example, I push the data out to the right, what happens to the median? Nothing happens to the median because the 50-50 split remains the same. But if I push the data out to the right, the mean will change. It will move to the right. Your lever, the lever principle, right? If there's more weight on one side, I have to move my finger in order to counterbalance that weight. So these are two different parameters. If the distribution, for example, is what is called symmetric, symmetric means it looks the same on the left as on the right, then these two will equal. Because the idea of going half to the left and half to the right will be the same as the idea of where do I balance, because the left is equal to the right. So when the mean is not equal to the median, that's a signal that the left is not equal to the right. And when the mean is a little more than the median, it says that there is some data that has been pushed to the right. And that should be something that you can guess here, because the mean and the median to some extent are what? 24, 26, etc. The lowest is 18. That's about 6 years, 8 years less than that. But what is the maximum? 50. That's 25 years beyond. The data is pushed to the right a little bit. Instead of saying pushed to the right technical term is right skewed. There are, shall I say, people are more not average on the older side than on the younger side. There was a hand up somewhere. Yes.
I was just confused with the statement that median would not move, but then you explained it.
Yes. So therefore, one reason that the median often doesn't move is because it is not that sensitive to outliers. So let's suppose, for example, we look at us and we ask ourselves, what is our mean income or our median income? And we have that. Each of us make a certain amount of money, we can sort that up and put that in. Now let's suppose that Mr. Mukesh Ambani walks into the room. Now what is going to happen to these numbers? Mean is going to go up, right? He alone probably makes a very large multiple of all our incomes put together. Possibly. I don't know how much you make. I know how much I make. But what's going to happen to the median? It's going to stay almost the same. The typical person may move by at most half. Because what is a typical person going to be? The typical person is going to be an actual individual in the room, or maybe an average of 2 individuals in the room. And that person is not going to change. Yes. Yes. That's one conclusion we can draw on this. There are other plots below which will also show the same thing. You're not being able to draw that conclusion. Well, good logical reason. I haven't shown you the full data. We'll see the histogram and we'll do that. So hold on to that question. The conclusion was drawn is that there are two things to do. See here. One is, if I simply look at this without seeing any more graphics, where is the middle of the data from a median perspective? At 26? Correct? Now from 26, look at the difference between 26 and the smallest. 18. Between 18 and 26, that's 8 years. This 8 years contains 90 observations because there's 180 total. Now, what is on the opposite side of this? 26 to 50. That's how many years?
24.
24 years. This 24 years now contains how many observations? Same 90. So there are 90 observations that are between 18 and 26. And there are 90 observations between 26 and 50. So if I were to draw a picture, what would that picture look like? Yes, exactly as you're drawing it, right?
What we can say is skewed on the left hand side or right?
This usually by definition is called right skewed. This is a problem that BABI has. Does this mean it's left skewed or right skewed? As a word, right, it's called right skewed. More data to the right. More data is a dangerous word. No, it's the same number of observations. I'll say the data is pushed to the right.
More variation on the right side.
More variation on the right side is probably a safer way of putting it, yes. So skewness is often measured in various things. One measure of skewness is typically, for example, mean minus median. Mean minus median, if it is positive, it usually corresponds to right skewness. Mean minus median negative usually corresponds to left skewness. This is a statistical rule, but sometimes it is used as a definition for skewness. There are many definitions for skewness. Skewed data sometimes causes difficulties in analysis, because what happens is the idea of variation changes. Being variation on one side means something a little different than variation from the other side. By the way, what's happening to you with respect to things like books? Are you getting books? Are you not getting books? I have no idea what the books are. You got one book, which is what? Which is the statistics book? Okay, I'll take a look at that book later. So, this book, right? Okay, show me the book. Okay. Comment 1, very nice book. Comment 2, not a Python book. Right? That doesn't make it a bad book. So, if you're looking for help on how to code things up, this is not the right book. Get a book like Think Stats or something like that. But if you want to understand the statistics side to it, it's an excellent book. So everything that I'm talking about is going to be here. I might talk about which chapters and things like that at some point. And I might talk about how to use this in the book. So for example, at the back of this book, there are tables. There are tables at the back of this book, which we'll learn how to use. And then I'll try to convince you that you shouldn't use them. But remember, many of these methods are done in ways in which either you don't have access to computers, or if you do have access to computers, you don't have them, shall we say, at runtime. In other words, when I want to run the application on it, I can build a model using a computer, but I can't run it within one. The runtime environment for statistics is often done when there are no computers around. The build environment can include computers, but the runtime environment cannot. A lot of statistics is done under that kind of situation.
Even probability is also covered here?
Yes, very much so. Very much so. Okay, so definitions of skewness and things like that. Do it in the way you usually use a book, which means you go to the index and see if the word is there. And then you go back and figure it out, and it will give you some ideas as to how that works. It's a nice book. It's one of the best books that you have in business statistics, but it's not necessarily a book that will tell you how to code things up. That is not a deficiency of the book. Not every book can do things of that sort. There are other books around that will tell you how to code things up, but will not explain what you are doing. It's important to know what you are doing. It's also important to know why you're doing it. But books can't be written with often everything in mind. Yes?
Can you suggest some book which tell us how we can think that way?
The thinking is here. I think this is good for thinking. I would absolutely recommend this book on the thinking side.
Because the problem lies that in which situation what we need to apply.
Yes, and that answer I think is very, very good here. Where you won't get is it will say do this, and it won't give you the Python syntax to do it. That will not be here. So if you can solve that problem through some other means. I used to have a colleague in corporate life who had a very big sticker on his board. It said, Google search is not research. Right? Now nobody agrees with him anymore. So I suppose that when in doubt, you do what normal Homo sapiens do today, which is you Google for an answer. So one possibility is that you understand something from a book such as this, and if you want to understand the syntax, just Google for the term. Say Python, that term, whatever, it will probably give you the code. Things are very well organized these days. There's also the question, and I should give you a very slight warning here, not to discourage you from anything. But in the next 9 months or thereabouts, the duration of your program, there's going to be a fair amount of material that will be thrown at you. Correct? The look and feel will sometimes be like what we would often call at MIT as drinking from a fire hose. You can if you want to, but you will get very wet. So therefore, pick your battle. If you want to understand the statistics side of it, please go into the depth of it. But if you try to get into equal depth on every topic that you want to learn, that will take up a lot of your professional time. Now the reason we do the statistics first, one, it's a little easier from a computational perspective, although harder from a conceptual perspective, so we begin it this way. But hold on to that idea, and then as you keep going, see if this is something that you want to learn more on. And if you can, you're welcome. Just write to us or let us know, or let anyone know that Hoita's just come in, let her know, and we'll get the references to you. But if you want to, say for the first 2 residencies, please read the book and see what happens. If there are doubts, yes, but it's a well-written book. Its instructor is one of our colleagues here. If you want, we can also help explain things. So this is the summary. What did the summary tell you? This summary gave you what's called the 5 numbers that help you describe the data. Minimum, 25, 50, 75, max. We'll see another graphical description of this. It also described for you a mean. There is also another number here, and this number is indicated by the letters STD. STD refers to standard deviation. STD refers to standard deviation. And what is the formula for a standard deviation? STD is equal to the square root of little bit of a mess, but 2 steps. Step 1, calculate the average. Step 2, take the distance from the average for every observation. Ask the question, how far is every data point from the middle? If it is very far from the middle, say that the deviation is more. If it is not far from the middle, say that the deviation is less. Deviation being used as a synonym for variation. I'm talking about variation. Variation can be more or variation can be less. More than the average, less than the average. If someone is much older than average, there's variation. If someone is much younger than average, there is variation. So therefore, both of these are variation. So what I do is, when I take the difference from the average, I square it. So more than x bar becomes positive, less than x bar also becomes positive. Then I add it up and I average it. There's a small question as to why it is n minus 1, and that is because I'm taking a difference from an observation that is already taken from the data. Now I have squared. When I have squared, my original unit was in age. When I have squared, this has become age squared. So I take the square root in order to get my measure back into the scale of years. So the standard deviation is a measure of how spread a typical observation is from the average. It is a standard deviation, where a deviation is how far from the average you are. And because of this squaring, you need to work with a square root. In sort of modern machine learning, people sometimes use something called a mean absolute deviation, MAD, very optimistically called. So what MAD is you don't take a square, you take an absolute value, and then you do not have a square root outside it. And that is sometimes used as a measure of how much variability there is.
So why it is squared then?
Why is it?
Why we just...
We square it because we want to look at both positive and negative deviations. If I didn't square it, what would happen is it would cancel out. What was the word that one of you used? Neutralize, right? I love that term. Your positive deviations would neutralize your negative deviations.
So I went with this x minus x bar is
Yes.
So it should be like x square minus x square. And if you are seeing the positive end of the
This number is going to be positive if say x1. So let's look at the first number here. So if I look at the head command here, when I did the head command here, what did the head command give me? The first few observations. So now this is an 18-year-old. This is probably sorted by age. This is an 18-year-old, correct? Now I'm trying to explain the variability of this data with respect to this 18-year-old. Why is there variation? This 18 number is not the same as 28, and 18 is less than 28. So what I want to do is I want to go 18 minus 28.7. What I'm interested in is this 10. This 10-year difference between the two. Now the oldest person in this data set is how old? 50. When I get to that row, this 50 will also differ from this 28 by 22 years. So I'm interested in that 10 and I'm interested in the 22. I'm not interested in a minus 10 or a minus 22. I can do that. In other words, what I can do is I can represent 18 minus 28 as 10, and I can represent 28 minus 50 as 22. And that is this. As I said, 1 over n minus 1, absolute x1 minus x bar plus absolute xn minus x bar. That is this. With n minus 1. And this is done, as I'm saying. This is what is called mean absolute deviation. And many machine learning algorithms use this. You are correct. In today's world, this is simpler. Now, when standard deviations came up first, this was actually a little harder. But people did argue about this. I think, well, 150, maybe more about, I forget my history that much. There were two famous mathematicians, one named Gauss and one named Laplace, who argued as to whether to use this or whether to use this. Laplace said you should use this, and Gauss said you should use. Now the reason Gauss won was simply because Gauss found it easier to do calculations. Why is this easier to calculate with? Because Newton had come up with calculus a century or so before that. And so, for example, let's suppose that you want to minimize variability, which is something that we often need to do in analytics. Which means you need to minimize things with standard deviation, which means you need to differentiate. This function, the square function is differentiable, you can minimize it using calculus. This is not. So therefore what happened was, Gauss could do calculations, but Laplace could not, and Laplace lost. And Gauss won the definition of the standard deviation.
We haven't much used 25% or 75, so
okay. Why do we not do that? So, today, this entire argument makes no sense. Because today, how do we minimize anything? Our computer program. You don't use any calculus. You run fmin or something of that sort, you basically run a program to do it. So therefore this argument you can both do calculations equally well with this as in that. So today what is happening is that Laplace's way of thinking is being used more and more. This one is a lot less sensitive to outliers. This one, what it does is, if it is far away, the 22 squares to 484 or something like that, which is a large number. So the standard deviation is often driven by very large deviances. Larger the deviance, the more it blows up. And so therefore this is often very criticized. If you read, for example, the finance literature, there's a guy called Taleb, Nassim Taleb, he writes this book called The Black Swan and Fooled by Randomness, where he left and right criticizes the standard deviation as a measure of anything. So today this argument doesn't make a great deal of sense, and when in practice something like this makes sense, it's often used. So a lot of this is done historically. It looks this way because of a certain historical definition, and then it's hard to change. So today in centuries after Gauss, sad people like me are trying to explain it and having trouble doing it because there's a logic to it, right? I mean, and that logic doesn't hold at all anymore now. Yes.
Standard deviation in simple terms is that 18. How far generally is that from the median.
How far on the average is an observation from the average? Confusing statement again. He's again going to be unhappy. But how far on the average is an observation from the average? If that answer is 0, that means everything is at the average. But you're asking the question, how far from the average is an observation on the average? If I take your blood pressure, how far from your average blood pressure is this reading? If this is exactly equal, then I don't need to worry about variability. Every time I measure blood pressure, I'll see the same thing. What is your average bank balance? Don't tell me that, but you know what I mean, right? You have an average bank balance. Your bank account manager or your bank actually tracks this, what your average bank balance is. But you're not actually, your balance is almost never or very, very rarely equal to your actual average bank balance. It's more and it's less. How much more, how much less is something that the bank is also interested in order to try and figure out, how much of your money, so to speak, to get out there. Because the bank is going to make money by lending it out, correct? But when it lends it out, it can't give it to you. So it makes an assessment as to how much money, I don't want to get into finance now, but you get the drift. So therefore, it is a measure of that. It is not the only measure of that. So for example, here's another measure. So you remember this 25 number and the 75 number that you're asking about? Let's say that I calculate a number that looks like this. Let's say 33 minus, let's say 33 is a 75% point, minus 24. So 33 minus 24, let's say this is my 24 and this is my 33. Between this, how much data lies? 50%. Why? Because this is 25% and this is 25%. This now contains 50%. This is sometimes called the interquartile range. Interquartile range. Big word. Right? Now, why is it called an interquartile range? The reason is because sometimes this is called Q3 and this is called Q1. Q3 stands for upper quartile. You can understand quartile, quarter. So upper quarter, and this is the lower quartile. And the difference between the upper quartile and the lower quartile is sometimes called the interquartile. Why is it called the range? Because what is the actual range of the data? The range of the data in this particular case is 50 minus 18. And 50 minus 18, which is your max minus your min, this is sometimes simply called the range. Range is maximum minus minimum. Interquartile range is upper quartile minus lower quartile. And these measures are used. They do see certain uses based on certain applications. You can see certain advantages to this. For example, let's suppose that I calculate my 5-point summary. With my 5-point summary, I can now give you a measure of location, which is my median, and I can give you 2 measures of dispersion, which is my interquartile range and my range. So those 5 numbers have now been twisted to give me a summary number, which is the median, and a range number. Interestingly, I can also draw mental conclusions from that. For example, I can draw conclusions from these 5 numbers in the following way. 24 and 33. Half my customers are between 22 and 24 and 33. So if I want to deal with half my customers, I need to be able to deal with a range of about 9 years. Within this 9 years is all that I'm interested to get this right. So if I'm building my machine, I'm going to make sure, let's say, that the 33-year-old is okay with this and the 24-year-old is okay with this. Will the 50-year-old be okay with this? No, may not be. But if I want to make the 50-year-old okay with this, I'll have trouble with the 18-year-old. So I can do a lot with even these 5 numbers. We'll see more descriptive statistics as we go along. By the way, this is only for age. I can do this for usage, I can do this for fitness, I can do this for income, I can do this for miles. Income is interesting. Here's the median income, $50,000, and the mean income about $53,000. If you see income, in almost all real cases, the mean income is going to be more than the median income. The per capita income of India is more than the income of the typical Indian. Say, what does this command do? If I say mydata.info, what this is doing is, my data first of all is a data frame that I created. Just to review, I read the PDF file this way. Now this is a describe, and this here is info. Now describe and info in the English language are similar things, description and information. This is interpreted in the software as 2 completely different things. Information is like your variable setting. It's like your integer field, your real field is setting like that. It's giving you information on the data as data. The word data means different things to different people. To a statistician, data means what? To a statistician, data means a number. To an IT professional, what does data mean? Bytes, information. I've lost my data. I don't particularly care what the data is. I've lost my data. So this is that information. It tells you about the data. It's an object. This is description. It's a 64-bit stored integer. It's an object. So it tells you about numeric, categorical. It tells you about the kind of data that's available. Non-null fields. In other words, there are objects in the field, etc. There are so many integer types which are stored at 64 because this computer is probably capable at 64. And there are 3 categorical variables. This is, shall we say, a data object summary of what is there in that data frame, not a statistical summary. Useful in its own way, particularly if you are processing it and storing it. For those of you who are going to go into data sort of curation-like careers, this kind of a database is a nightmare. Because typically what happens is, when you store real data, in addition to data, you often store what's called a data dictionary. Sometimes that's referred to as metadata, data about the data. Because simply storing a bunch of numbers is not enough. You have to say what the numbers are about. This adds a layer of complexity to the metadata. You now have to store not only what the variable is about, but what kind of a variable it is. So many professional organizations say is that archival data should never be a mixture of both numerical and categorical objects. And they pay a price for that. Numerical things should become categorical or categorical things become numerical. But what happens is, if you are storing large volumes of it and archiving it and making it available for people who have not seen it before, it sometimes gets convenient. So therefore, fields like this are often useful to see how big a problem you have. Right? Now I want to plot a few things. To plot, you can plot anything. Seaborn, I think, is coming a little later. But this plot, this is from Matplotlib library, and it is plotting through a command called hist. Hist means histogram, which you've already seen. You've covered histograms, right? I think you've seen histograms. So this is a histogram. Now histogram as a syntax has bin sizes and figure sizes. So what you can do is you can play around with these and see the differences in what this histogram does. But there's a certain default that shows up, and that default is quite good. And here is a histogram distribution of the age. This is not a set of numbers, this is a picture. This is a picture. What does this picture have? This picture has a set of bins, and it has a set of counts within each bins. Between these two numbers, between say 10 and whatever this is, let's say 22 or thereabouts, I have a count of, let's say 17. So it gives a count, and it does this by getting a sense of how many bins there are and plotting this shape. It's a little bit of an art to write a histogram program. there's a Python book out there, I think ThinkStat is one of it, in which sort of the first 1/3 of the book is basically how to write a histogram code. It's a wonderful book, but because it treats this example, it got terrible reviews. Reviewers said, why do I want to learn how to code a histogram? And the book's author is, I'm teaching you how to write a code. A histogram is an example of how to do that. And I tend to agree. If you want to test yourself of your understanding of data and your understanding of any programming language and any visualization language, code a histogram in it. And have fun. So it's a nice challenge from many perspectives. The data challenge, the language challenge, the visualization challenge, all of that. Yes?
So you said archival data should not be numerical plus category.
Many companies do that. That they want archival data to be of only one data form, only one format. Why is that so? Because, as I said, when you store data, how do you store it? Let's say that you've generated an analysis. The analysis is done, correct? And you've decided not to destroy the data. You're going to keep the data in your company's databases or in your own database. How will you keep it? You can take a technology. Let's pick an example. Let's say pick an example. SQL, Excel, whatever. Let's say Excel. Let's say I keep it in Excel. Now, if I keep it in Excel, what will I now do? So let's say I have an Excel spreadsheet. Let's say my cardio data set. Let's say this data set. Now, in addition to the data, what do I need to store with it?
Metadata.
Yes, metadata. How do I store that metadata? Yes, so one possibility is I can have a text file like that, like I had at the top of this, describing all of this, which is typically what happens in Excel storage. It describes this and it describes, there's one file called .dat and another file called .disc or something of that sort, which basically describes the variables, and the idea is that they have the same name, and one extension gives you the data, the other extension gives you the description of the variables that are in this data. Correct? Now this is good. Now what's going to happen? On that data, certain code has been run. That code is going to assume certain things about the data. What do you want that code to assume about that data? Whatever you want that code to assume about that data should be available in the data dictionary. Now, if that code is stable enough to realize that whatever fields you give me, I will run on, that's cool. But if that code requires you to know what kind of data is being used, let's say discrete data, let's say continuous data, in the future you'll be doing things like linear regression, logistic regression. Linear regression will make sense if the variable is a number. Logistic regression will make sense if the variable is a 0 or a 1. If you have that problem, now in the metadata you need to be able to tell not only what business information this variable contains, but also what kind of a computational object it is, so the code can run. So therefore what people often say is that I'm going to make it very simple and I'm going to assume that my entire data frame consists of only one kind of variable, so that when I run any algorithm on it, I know exactly what kind of data input that algorithm is going to get. But I'm saying it's a practical answer that many companies often have. And I've worked in a couple of companies, at least one company where this was very seriously done. So we had to when we put data back in, we had to convert it. And in the situation that I was in, it wanted everything in categories. So what we would do is we'd take continuous data and we would do what's called fine classing, which means that we would divide not into 4 pieces but into 10 pieces. Decile 1, decile 2, decile 3, decile 4 up to decile 1. And every variable was stored now not in its original numbers but as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So let's suppose that I tell his income is 9. What that means is I know he's in the 9th decile. 10% of the people or more have income more than him, 80% have less than him. He's in that bracket. And all variables were stored that way. Now what happens is every algorithm knows that every variable is going to be stored that way. And you can keep writing algorithms that way. Otherwise what would have to happen is every algorithm would need to be differently. And let's say you're doing credit scoring. Let's say you're doing CRM models. You're doing something of this sort, and you've built a very sophisticated CRM model that tracks your customers, and it works. Now suddenly you've got a new variable coming in, the Twitter feed, and suddenly nothing works. What to do? Go back and rebuild that entire model. That's going to set you back 3-4 months. That's going to set you back a few $1,000s. So you say, no, any variable that has to go in this form. And if it goes into this form, my algorithm can deal with it.
So well, in such case, it might not affect the efficiency of the model that we generate.
Yes, yes. And in practice, I'm going far away from topic now. In practice, a professional analyst has to struggle between doing the right thing badly and the wrong thing well. You want to do the right thing well. But the right thing well is going to cost you time, money, data, and everything. So you struggle between saying that I'm going to get a flawed model quickly built on a new data set, or I'm going to get an inefficient answer on a model that's already been built. And let's see how far it goes. And so these are more cultural issues with how an analytical solution is often deployed in companies. They vary very much from industry to industry. They vary very much from company to company, from the culture of a company to a culture of a company. They depend on regulatory environments. In certain environments, an auditor-like entity comes in and insists on seeing your data. Show me your data. Let's say in finance, this is sometimes happening. Regulatory agency, let's say Reserve Bank of India, goes into a bank and says, show me your data. All this NPAs, etc. Show me your order book, show me your loan book. Correct? And now that has to be done, and the decisions you made have to be done in a way that is patently clear why you have done this. So very often people say, I don't want to make the best risk decision. I want to make the most obvious risk decision. Which may not be the same thing at all. But I'm being audited. So that's a practical question. And I don't have a clean answer to that. But I do know what happens. Is it right? No, it's not. But we live in a world that has that kind of imperfection. One of my teachers, his name was Jerry Friedman. You'll see some of his work later on. He came up with algorithms like projection pursuit, CART, Mars, gradient boosting. He created many of the algorithms that you'll be studying. One of my teachers at Stanford. When he ran our consulting classes, he would say this: solve the problem assuming you had an infinitely smart client and an infinitely fast computer. After you've done that, solve the real problem, where you do not have an infinitely smart client and you do not have an infinitely fast computer. This was in the early 1990s, where computer speeds were a lot slower. And we didn't have powerful machines like this around. So a lot of this is done in that kind of situation, where you are struggling for continuity, when you're figuring it out. Imagine yourself as an analytics manager, and I hope many of you will be. And you have an analytics team sitting in front of you, correct? You're looking at them and you're looking at them in the eye, and you know how much you're paying them. And you know that half of them are going to leave at the end of the year. What are you going to do with regard to the modeling and things like that? Your first order business is going to be to ensure continuity in some form. Keep it simple, right? Keep it simple. Keep it obvious for the next bunch of people who are going to come in. And for that, you'd be willing to trade a little bit of make it right. So now the new person coming in will now not want to solve a very complicated kind of situation. This is not where you want to be, and I do not want to depress you on day one. But it's also the fun part of the profession, right? It's also what makes it interesting and interesting and exciting. Right? So it's not all bad. Okay, so the histogram command summaries of what these histograms are, and each gives you a sense of what the distribution is. And as you can see from most of these pictures, most of these variables, when they do have a skew, tend to have a right skew. Maybe education has a little bit of a left skew. Maybe education has a little bit of a left skew, that a few people are educated and most people are here, but even so. Right? Now here's an interesting plot. Matplotlib has this as well, but Seaborn has a better version of it. This is what's called a box plot. You've seen a box plot? This is a box plot. People are unsure as to where this box came from because there's a statistician called Box who's used this before, but this box came from, it used to be called a box and whisker plot. These are the whiskers. This whisker will go, this is the median, this is the upper quartile, the top edge of the box, the bottom edge of the box is the lower quartile, the end of the whisker is 1.5 times the interquartile range above the box. Right? If you want a formula, sort of the whisker, the length of the whisker is 1.5 times IQR. Should I have a break now? A little bit maybe, huh? So we'll, okay, 3:45 or whatever, we'll go up to there at least. Yeah, I haven't stopped, I just got distracted. So 1.5 times the, so it goes up to that. If a point lies outside it, the point is shown outside it. If the data ends before it, the whisker also ends. Correct? What is the whisker? Okay, what is the whisker? Alright, let me explain another way. The whisker is the maximum, the top of the whisker is the maximum, the bottom of the whisker is the minimum. Okay? Not okay. Okay. Some of the points are outside. So, this point here, now what is this plot here? Age for males. So what this means is this is the minimum, 18 or whatever it is, and this is the maximum, 48 or whatever it is. Minimum and the maximum. So if you see nothing else on the box plot, no other points other than just the box and the whisker, then your 5-point summary is sitting there. That's it. Right. Now, what happens if you see points like this? Outliers. What is an outlier? An outlier is a point that lies more than 1.5 times the interquartile range above the box. So this whisker will not extend indefinitely. It will go up to 1.5 times this box and then it will stop. And if any points are still left outside it, it will show them as dots. You can treat this as a definition for what an outlier is.
What about the lower whisker?
Same thing.
1.5
Same thing in the other direction. The logic is symmetric.
1.5 times compared.
No. That means this it hasn't. The data is ended here.
The data is ended.
The data is ended here.
Was there any other number tried instead of 1.5?
I suppose so, and you can change it. You can. I won't try it now, but you can go to the box plot syntax and change that. So you can go to box plot syntax and you can change that 1.5. It's not hard coded into the algorithm. I think 95% sure. As a statistician, I'm never sure about anything. But it's a parameter in the you should be able to pass the parameter in the box plot function. Default is 1.5. You should be able to change it.
And what's the color part? That's the median, is it?
Which one?
The color.
Color?
Blue color or orange color?
Oh no, these two colors. These two colors are because I've asked for two things. I've asked for male and female. If I had 3 of them,
That's okay. But how the range of the color? The box.
oh this one here. Oh, this is Q3. The lower is Q3 and the upper is lower is Q1 and the upper is Q3.
So this is the quartile range.
Quartile range. So for males, between the bottom whisker to the end of the box is a quarter of your data. The box is half your data, and the top of the box to the end of the whisker is quarter of your data.
So the middle line is
The middle line is the median.
This is the IQ.
The middle line is the median. There is also a function in box plot you can play with where it will give you a dot, and that dot is the mean. I mean, you can ask boxplot to do that. But a mean is not a general standard component in the 5-point summary. It's a different calculation, not a sort. But if you want to, you can make boxplot to give a dot on the mean as well, by definition. Yes. So mean median. So half the data is between 24 and 34 or whatever that is. Half of all the men in my sample are between those two numbers. I think boxplot doesn't allow you to change the shape of the box. I think that is set. That's sort of central to the idea of a boxplot. It does allow you to fiddle with the size of the whisker, but I don't think it allows you to fiddle with the size of a box. In other words, if you change that to something else, let's say the 20% point to the 80% point, 80-20 rule, that's no longer a box plot. It's another interesting plot. The significance of it is exactly this, as we had seen before. The significance of it is that the data looks like this. It's right skewed. Think of the picture. So if this is your Q1 and this is your Q3, this is your Q2 or the median, then the median is going to be closer to Q1 than it is to Q3. In the same way that the minimum will be closer to the median than the maximum, same idea. This is a summarization for numbers. If you want to summarize for categorical data, what's called a cross tab or a cross tabulation, this is simply how many products are there? Product category 195, 498 and 798. They've got 3 kinds of treadmills and they're trying to understand who was using what kind of treadmill. Our business problem is to understand who was using what products. This is a cross tab. What is this? This is something that will be used for categorical variables. No box plot will make sense here. There are no numbers. So now you can ask interesting questions here if you want to, and you can think about how to answer it. Is that, for example, you can ask a question, is there a difference between the preferences of men and women? Possibly. Is there a difference in the products that irrespective of gender, is there a product that they prefer? You can ask all kinds of interesting questions and you can find ways to answer it, which we will do, not in this residency, but next time around.
For those we can categorize it also?
Categorize?
For those preferences?
So this is simply, once again, this is descriptive. All this has done is it has simply told you the data as it is. What I'm saying is that if you want to do a little more analysis on it, you now have to reach a conclusion based on it. So for example, one conclusion to ask is that do men and women have the same preferences when it comes to the fitness product they use? Now that's a question. To answer that question, it's enough to look at the data. But just looking at it will not give me the answer. I need to be able to find a statistic to figure that out. A statistic that does what? That in some way measures that difference. Let's say measures the difference between men and women, or what we will do is not measure that. What we'll do is we'll measure that if there was no difference between men and women, what should this table have looked like? And then we'll compare the difference between these counts and that table. But that's the interesting part of a statistical statistic, which we'll do. That's called a chi-square test. It's coming up in the next residency. But that's the prediction part or the inference part of this description. This is just the description. You can do a similar thing here. This, for example, is for marital status and product. What product you use. Are you not very dependent on whether you're partnered or single? What is marital product versus product? Maybe it has to do with age, or maybe they're correlated. Should you use one as opposed to the other? Okay. You can use counts as well. If you say instead of doing it this way, instead of seeing it as a table, if you want to see it as a plot, you can ask for counts. So there are things like count plots and bar plots, which allow you to do counts In the lab, you'll do probably a few more of these. This is simply another visualization of the same thing. For those of you who like things like pivot tables in Excel, Microsoft has made, wonders of us all. In corporate life, I was told that, you can have a master's in bachelor's and master's in anything, engineering is good, etc. And it's nice if you have PhDs in a few areas, but what you really need is a PhD in PowerPoint engineering. I mean, that's a necessary qualification for success. So certain tools have been used. So therefore, those tools have been implemented in many of these softwares as well. This is the pivot table version of the same data set. This is the last, not last, but still this is a plot. Let me show you this plot and then we'll end or we'll take a break. This is a plot that is a very popular plot because it is a very lazy plot. This plot requires extremely little thinking. Pair plot of a data frame. Right? You don't care what the variables are. You're telling it nothing about the plots. You're simply saying, figure out a way to plot them pair by pair. And it does that. So for example, how would you read this plot? On this side, so it creates a matrix. The rows are a variable and the columns are variables. What is this? This is age versus age. Age versus age makes no sense. So what it plots there is a histogram of age. Doesn't like the gap. Nature abhors a vacuum. I suppose Python does as well. So it'll now plot what it should have plotted is age versus age. You're right, it should have been a 45-degree line. But a 45-degree line is a useless graphic, particularly if the same 45-degree line shows up in all the diagonals. So to make a more interesting graphic, it plots the histogram there. This analysis, this kind of analysis sometimes has a name associated with it. The name is univariate. Univariate means I'm looking at it variable by variable, one variable at a time. When I'm looking at age, I'm only looking at age. It's called univariate analysis. It's just a word. Uni as in uniform, same form, unicycle, cycle with one wheel, things like that. Univariate. Unit.
But for the other set of data also, will it replicate the same kind of pattern? If I'm going to give the other set of data.
Another set of data, it'll replicate the same nature of the data. There'll be histogram here again.
Age and the education versus education, this
So yes, so what it will do is, remember that this graph, the nature of the graph, so let's see this. Right? So where is gender here? Where is gender here? Is it there? Is gender in my data? It is there? So when I did pairs plot my data, what did it do with gender? Yes, remember in info, when we did info here, remember how it had stored the data? No, not NAN, here. So it had product, gender and marital status, it had identified as objects in the data frame when it had formed the data frame. So now what does it tell you about the command, the pair plot command? Yes. It will ignore those objects. So in answer to your question, if the data frame has been stored, has been captured with integer 64, basically integers or numerics in it, it will plot. If it's only objects, it will probably give a null plot. Yeah.
So how come age is not a particular?
Say again, age is not?
Why it is not a linear line?
Why like that? This is the histogram. This is the same plot. This plot is the same as which plot? This one. It's the same as this one here. No, this is not age versus age. This is just age. Age versus age would have been a 45-degree line, but it's not plotting that. It's not plotting that. In the diagonal, it is not plotting age versus age. In the diagonal, it is simply plotting age's own distribution.
With count. Age with count.
Yes, with the count. So what it is doing is, it is essentially running hist on age, on each observation, and putting it on the diagonal. Yes.
What can we infer from the histogram of like 20 to 25 bins?
20 to, say again?
There is a bin, right?
There is a bin.
So what can we infer from that? From each bin?
From each bin, it's a count.
Count of people in that age.
It's a count of the number of people who are in that age group. Here, this is age. No, this is miles. This is age. This is age. So let's say between here, between let's say 40.5 and 43.5, or whatever these numbers are, there are 3 people. Remember, the histogram is a visual thing. You can data mine a histogram if you want to, which means you can find out what those are, and you can see it inside histogram. Just ask for a summary of that, it will give you what the features are of that histogram. But the histogram is not meant to be used that way. It's meant to be used as an optical device, to see the shape, to see the count. It's an art to do a histogram. If you change the bins a little bit, the histogram will look a little different. So I would suggest that unless you've got a lot of experience in this, or you really enjoy the programming, do not fiddle with the histogram. Its shape will change. I'll show you a little later after the break. Not change the histogram, but what shape is. No, not in default. You can go in and change it on size. But the bin width, etc., the bin width of histogram takes a little more to change. Right? So there is stuff out here. You can find other things in which you can play this. So there are ways to do it. Okay? So quickly ending, we're losing our food. So these different plots, and we'll continue after the break. The rest of it is simply an X versus Y. So for example, this is age versus education. This is age versus education.
So the second graph from the first one is just rotated.
Yes, he's right. If this is education on the y-axis and age on the x-axis, or vice versa, then these two plots, 1 and 2 and 2 and 1, are just mirror images of each other.
It's not a mirror image. No, it's just rotated.
You're right. Depends on where you look, where you put the mirror. But yes. Mirrors. So I remember when I was a kid, mirrors would confuse me. So I would ask a question like this: that when I see a mirror, left and right get switched, but top and bottom don't. And I never understood why. Like, due to gravity? You can think, left and right get switched, but top and bottom don't. I thought it was something to do with the mirror. And then I thought it was something to do with my eyes, maybe because they're left right. So I looked at it this way, and that didn't help. So yes, it's an important point. When you do symmetry, it's a good catch. It's a good catch to realize that there aren't so many plots. There are actually only half as many plots, because the plot on this side of the histograms and the plot on the opposite side of the histograms are the same. There was another question that one of you asked, is that many of these seem to look like rows and columns, in the sense that what are these rows? Now what does this row look, what does this mean? It means that this variable fitness actually has very few numbers in it. It has a number 1, 2, 3, 4 and 5. Now why is that? Because remember how I defined fitness is my perception of whether I was fit or not in my original definition of the variables. Here you go. Self-rated and fitness on 1 to 5 scale, where 1 is in poor shape and 5 is in excellent shape. This was the created data. So in this data set, I now have this variable in it. These kinds of variables sometimes cause difficulty in the sense that there's a word for it. These are sometimes called ordinal variables. So sometimes data is looked at sort of, numerical and categorical. And categorical is sometimes called nominal and ordinal. Nominal means it's a name of a person, north, south, east and west, gender, male, female, place, etc. It's a variable. Essentially it's a name. Ordinal it's also categorical, but there is a sense of order. There is a sense of order. Dissatisfied, very dissatisfied. So there's an order, therefore ordinal. This variable, the fitness variable, can, if you wish, be treated as an ordinal categorical variable. So for example, the Likert scale is that, so the 7-point scale. Not satisfied, very dissatisfied, dissatisfied, moderately dissatisfied, neutral, moderately satisfied, satisfied, very satisfied. Mark 1. This generates a data from a scale of say 1 to 7 or 0 to 6. So it will show up in your database as a number. Like for example, here you can say instead of 1 to 5, very unfit, moderately unfit, okay, relatively fit, very fit. Instead of giving 1 to 5, give it that way. And you code it up this way, your choice. So sometimes when you have data that looks like this, the Python or any database will recognize it as a number because you've entered it as a number, but you analyze it as if it is a category. So the opposite problem also sometimes exists in that sometimes you get to see a categorical variable show up as a number, but you know it's a categorical variable. A zip code is an example. A zip code shows up as a number, but it's obviously not. You can't add up zip codes, right? You take two places in Bangalore and you want to find a place between them, that's not the average of the zip codes. It might be close, but you can't do arithmetic with zip codes. The other difficulty with zip codes is that there can be many of them, which means that as your data set grows, the number of zip codes also grows. So the number of values that a variable can take grows with the data. And this sometimes causes a difficulty. Because what happens is that in the statement of the definition of the variable, you now cannot state how many categories there will be present. So you know that there will be more zip codes coming, you just don't know how many more zip codes will be coming. But you also know it's a categorical variable, so you can't treat it like a number. And so there are some special types of problems like zip codes that require special types of solutions. So the plot itself is a very computational plot. If it recognizes it as a number, it plots it. If you don't want to make it plot as a number, change it to a character. Most softwares, including Python, will allow you to do that. Now, this is in some way a graphical representation of it. For the end of this session, we can talk a little bit about the numbers associated with it. So here, for example, my data age, you can also go, dot age if you want to and things like that. This is the mean. 27.7888 is the mean. So you can extract it. There are functionalities of the mean that can be recovered, like trimming, etc., that if you want to. You can calculate the standard deviation. You remember the standard deviation formula? That strange formula that I wrote on the board? This is the standard deviation formula if you want to calculate the standard deviation. You can do this for other variables as well. This is an interesting plot. So I don't want to go too far into this plot, but it's an interesting plot. Right. In Seaborn, there's a warning on the code. This is called, or what they're referring to, is a distribution plot. So this is a plot that tries to look at not what the data is, but what the distribution is. So remember, I was drawing these odd pictures like this, and drawing lines on it. Those were distributions. So what it's trying to do is it's trying to go after the distribution of the data. Now, what does this mean? It means that it says this. It says that there is an underlying distribution of the age variable. This distribution is a distribution you do not know. However, you have a sample from that distribution. How big a sample? About 180 observations. From that sample of 180, can you guess at what that distribution is? In other words, can you give me a curve? It's an answer to that problem. And it gives a curve. Why is the raw data not enough? So the raw data is not enough, then this goes to the heart of what the statistical problem is because I am interested not in the age of this particular group of people. I am interested in the corresponding age of another very similar group of people. Why? What is the problem I'm trying to solve? I'm trying to solve the problem of who is buying my cardiac equipment. Now, when are these people going to buy my cardiac equipment? At some point in time? Okay. Now, what is my data? But for whom is this data? Who have I got the data for? Right. People have already bought. So I have a problem. My problem is, I want to reach a conclusion about my future customers based on my old customers. How to do this? What mathematical logic allows me to say something about the future based on the past? Yes. In short, the way to do this is to assume that there is what is called a population. We'll talk more later. At this stage, to assume a distribution. To assume that there is a distribution. From this distribution, I have seen a sample today. From this distribution, I'll see a sample tomorrow. The people are not the same. Because the people who are going to use my cardiac equipment yesterday are not what are going to use it next year. If it was the same, I'd never have a growing business. There's no point analyzing data of customers unless I want them to buy more things or I have new customers coming in. So what is common between my observed set of data and the data for my new customers? That commonality is what you can think of as a distribution. So he says that from this, can you give me a sense of what this distribution is? And from this distribution, I can think of other people coming. So what we'll do tomorrow is we'll talk about a few distributions, few specific distributions and how to do calculations in the distributions. For now, what this graphic does is it simply calculates that distribution for you. I'll explain very, very briefly how it does that. Won't go into too many details. What it does is, it takes the averages of points. Yes?
So you mean that for a sample, distribution cannot be done?
I'm saying that for a sample, why is not the sample the distribution itself? Why am I not saying, it's a good question, why am I not saying, ignore the curve, why am I not saying that the original histogram, which I've seen 3 or 4 times before, Why is that itself not the distribution? That's similar to the following question. Let's suppose that you have done a blood pressure test and you've gotten a few measurements. You've been tested twice today, let's say pre-prandial, before breakfast, after breakfast. Next week also you have done this. Let's say you have done this for whatever be your reason. You have done this, say, once a week for a month. So now you've got 4 readings. No 4 readings, 8 readings. Now these 8 readings, is that the distribution?
No.
You need to have a range.
Yes, so there's something that says, yes, if I want to understand what my blood sugar is and what it will be going forward if I do not get treated, then certainly there's a relationship between this and what will happen in the future. For example, if I behave exactly the same way, if I eat exactly the same way, or I exercise and not exercise exactly the same way, if I smoke, if my lifestyle is exactly the same as it is, I would expect my readings to be the same. But what about it is going to be the same and what about it is different, I don't quite know. Yes, it is true that those 8 numbers are a representation of the distribution, but they're not the distribution itself. If they were the distribution itself, I would be forced to say that in the next month, I would have exactly these 8 readings. But I know that's not true. But I also know that from these 8 readings, I can say something about what will happen next month. It's not that there's useless information there. So if my readings this month, for example, are, let's say 110, 120, 115, 125, let's say in good health, 130, etc. I know these are my 8 readings. I know with some idea perhaps that if things remain the same, next month they will not start becoming 220, 210, 215, 230. They will not become that. How do I know that? Because I have this readings this month. So the idea of a distribution is to be able to abstract away from the data the random part and the systematic part. And the systematic part is what remains as the distribution. Around it there's going to be a random variation. And that random variation is going to exist from data set to data set, like this month and next month, like this bunch of customers and another set of customers who buy cardio equipment, maybe from another branch of my store. If I am, for example, running, let's say, a chain of stores, let's say that I'm, I don't know, not to pick names, but let's say, I don't know, Reliance Fresh or something of that sort. And I want to understand how my stores are doing. Let's say I take 5 or 6 stores and I study them extensively. How do I know that those results are going to apply to the remainder of my 500, 600 stores? What is common between these 5 and the remainder? How are they representative of it? What part of it applies to the rest and what part of it does not? How do I extend it? How do I extend your blood pressure readings to the next blood pressure readings? How do I figure this out? That is the heart of statistics. That's called statistical inference. To abstract away from the data certain things that remain the same and certain things that do not. So a distribution is an estimate of that underlying true distribution of age. And so it's not as rough. It's smoother. How smooth is something that the plot changes, that the plot figures out on its own, like histogram. But you are free to change it. You are free to change it. There are functions within it, functions within this plot, and it's a fairly sophisticated function, which you can do many things with. I mean, it's a fairly sophisticated thing. There are many functions available within it. So, for example, this bin of histogram, this allows you to say where should the boundaries of those the histogram part of it be. Whether you want to plot it or not, whether you want to plot that what I was calling a distribution, the Gaussian kernel density estimate, it's a sophisticated way of saying the same thing. And there are functions available to put into that. So you can change this. It's one of the most sophisticated plotting functionals that you'll be able to see. I wouldn't suggest doing it now. Get a little more experience in doing this, but yes.
Slightly different if you use Gaussian.
Gaussian will not make too much of a difference. What will happen is if there is no smoothing out here, it'll look like a normal distribution. These little wiggles will go away.
I mean, it's
better, gives you a smoother curve?
We will discuss that a little later as to when, maybe tomorrow, as to when it's a good idea to do that and when it is not. Just hold on to that question a little bit. We haven't talked about the Gaussian distribution yet. I'll deal with that when the Gaussian distribution comes. For now, what this is it gives you a visual representation, simply a descriptive representation of the underlying distribution. Hence a distribution plot.
So the distribution you always want to compare with the samples, 8 samples if you take an example.
Yes.
You've distributed them, then you're taking a current sample.
Yes, so if my distribution is correct, let's suppose in an ideal world, if my distribution thinking is correct, then here's what would happen. If I take my old 8 data and I do a histogram, I do a dist. In the new data, I do a dist again. These two should be very similar. The histograms may be different, but the distributions should be similar, if I've done my analysis correctly.
Does that mean the variance is?
I wouldn't use the word variance, I'd say variability. It means that there is a sum, this is called sampling variability. In other words, there's a variability that is due to the fact that you've taken a sample. There is an underlying truth, but you're not seeing that truth because you're taking a sample. There is an underlying level of your blood sugar, but you're not seeing that because you've taken only a very small sample of your blood, a few milliliters, where there are liters flowing around, and at only at a few seconds in time. There are many hours in the day. There are so many other things that your reading could have been. But if it is a good sample, then what would happen is that I'll be able to cover this variability. So if I want to get a sense of what your blood sample actually is, and I want to sample this well, what I will do is I'll take samples in different kinds of situations. One thing they cover, for example, before eating and after eating, that they cover. Maybe I want to cover other things as well. For example, in certain kinds of diseases, they're very conscious as to where to take the blood from. Because the metabolism in the blood changes based on what? Certain diseases, and I won't make what. For example, you draw the blood near the liver. The liver is the body's filtration system. So essentially you want to figure out the nature of the blood when it flows into the liver, and then after it flows out of the liver, in order to understand whether the liver is filtering your blood correctly or not. Now to do that, you need to draw the blood in very specific places. So in order to do that, therefore your experimentation should cover all of that. What does that mean, for example, in business terms? Let's say that you're looking at sales data and you want to understand your sales distribution. Well, don't focus on certain salespeople. Look at your bad salespeople, look at your good salespeople. Look at your high selling products, look at your low selling products. Cover the range of possibilities. If you do not cover the range of possibilities, you will not see the distribution. And if you do not see the distribution, you will not know where the future data will come from. And if you don't know that, you will not be able to do any prediction or prescription for that. The histogram is just a summary. This is also just a summary. But the histogram summary applies to just this data set. This distribution is pretending to apply to a little bit more.
What is the definition of it?
Definition of?
Distribution.
The definition of a distribution doesn't apply to the data. So a distribution function, so to speak, is just this. So for example, it's sometimes defined this way. F of x is equal to the probability that x is less than or equal to x. This is sometimes called a distribution function. F of x is equal to the chance that age is less than or equal to, say, 15. Age is less than or equal to 16. Age is less than or equal to 17. And now let me confuse you even more. F of x, this is the derivative of x, the differential of x, is the density function, which is the area under the curve. This is called the density function, which is what this plot is plotting. This is sometimes called the density function. The density function, so the distribution function is the integral of the density function, and the density function is the derivative of the distribution function, if you're very mathy in all of this. So what they're plotting is they're plotting the density function. I showed the code. So this is actually called the density function. The reason I'm calling it a distribution function is because it says distribution here. I was hoping not to confuse you. Clearly I failed. Go ahead. Yes. That's the idea. Yes. Now you've hit the problem of statistics bang on the head. How do I get an idea of a distribution that applies to everyone based on only one sample sitting in front of me?
Lake, frozen lake. And then
That is the $1 million question, and that is why people like me exist. Right? That is the whole point of the subject. And it is a hard problem. It is a hard problem because you are trying to draw a conclusion outside your data. Nobody is interested in your data. Nobody is interested in your data. Right? Everybody is interested in their data or in their problem. Aapka मामला आपका ही है. Nobody is interested in your data. Now, but you still have to analyze the data that is in front of you and reach a conclusion that makes sense to them. The bank has to look at its portfolio and figure out what its risk strategy should be. The clothing store needs to look at its sales and figure out what clothes it should make. Great Learning has to figure out its course reviews and figure out which faculty members to keep. You have to look at your expenditures and figure out how much salary to negotiate for. How will you do all of this? How do you do all of this, by the way? Based on some sense of distribution, right? So when you go and you negotiate for a salary, now you're not going to negotiate for 100 crores. You might, but you'll say no one's going to give me that anyway. So maybe you're good enough, I don't know. But what you do is you essentially say, you do roughly something like the following. You figure out how much money you need and how much money you're expecting. And that to some extent is based on your expenditure and what you want to do. Your expenditure is also based on that. You have a certain income and you're spending based on this. You're doing all of this on a regular basis. You're standing on the road. Correct? You're standing on the road and you're trying to decide whether to cross it. How do you decide? Experience. You got past data and that data is telling you, please cross the road. How? That data has not seen that car. K533619 with his driver has not been seen by your data set. How are you crossing? Because you're making the assumption that while I have not seen him, I've seen many others like him. So there's this story, right? So a taxi driver is going at night on the road, etc., and he's just running left, right, etc. So red light, cross, no issues, etc. It just keeps going. The passenger is getting very scared. Stop karo ye. The driver, he says in Hindi, apologize for the language. Hum raaste ke sher hai. And I'm the lion of the road. Who will stop me? He goes through all the red lights. And then there's a green light. And then he stops. And then he says, why have you stopped? Now the guy says, raaste mein bahut sher hai. So the guy on the other side. So he's logical, right? So his data is saying that there are people who cross the red light. So therefore, if I'm standing at a green light, there's red light on the other side, cars are going to cross that red light, right? Very logical. So therefore, and we do this all the time. So while we are not trained as statisticians, at least normal people are not, they behave like one based on the experience. Now your objective and the objective of an analytics professional is to translate this logic into an algorithm, into a procedure that the company and the computer understands. And that is not easy. For starters, let's say that you are here and you say that this is an average, right? This is the mean age. This is 28.7888. And you could say that this is an estimate of the mean of the distribution. This is the mean of the data. But you are not interested in the mean of the data. Why are you not interested in the mean of the data? Because you're not interested in this particular set of 180 people. But you are interested in the average age of my customers. So now the question becomes, what does the age of my new customers have to do with the number 28? Are they related? Yes. You would say that they're like a copy of what I have. Now that's interesting. So if they're like a copy of what I have, then will I see 28.78 again? And now you will say probably not. They're a copy, but not that much of a copy. Most likely, now we are talking. So now, how likely is most likely? And what about it is going to be the same, and what about it is going to be different?
The y-axis of the distribution.
So the y-axis of the distribution you will say is the same. So for example, you could say that this 78.8 is an estimate of the population distribution, which means that yes, it comes from the histogram. It comes from the same data histogram comes from, but it also comes from this distribution. But there's also this nagging feeling that I do not know for sure. I do not know. I don't know what this new data is going to be. So what will happen is we will not give the answer 28, we'll not give the answer 28.7. We'll give an answer that is like 28.7 plus minus something. We'll say, I do not know what the population mean is, but I'm going to guess it's around 28. I know it is not going to be exactly 28, but 28 isn't useless for me either. It's going to be around around 28. How much around 28? Now certain criteria come in. What will this depend on? It will depend on the variation of the data. If the data is standard deviation, if the data is very variable, this plus minus will be large.
And the nature of the data, right?
Same, yes, the nature of it will depend upon how many things I'm averaging over. If this was 180, I'm so sure. If this was 18,000, I'll be even more sure. If this was 18, I'll be less sure. So it depends on how much data is being averaged over. The more data I have, the surer I am about the repeatability of it. The surer I am that I will see something similar again. It depends upon how sure I want to be. If I want to be 95% sure, if I want to be 99% sure, if I want to be 99 the more sure I want to be, the bigger the tolerance I must have on my interval. And those are things we'll get to. So those are also descriptions, but those descriptions are heading towards being able to predict. So now if I give you this 28.78, I've given you a description of the data, but I've not given you a prediction. If I've now given you 28.78 plus minus something, I've now begun to give you a prediction. Today is about descriptive analytics. We're not predicting anything. We'll get there. But this plot is in some way a first measure of looking at this idea of a population and of a distribution associated with the population. Right? This is, yeah.
Variation is less. That means this curve will be almost flat. Instead of
If the variation less, this curve will be sharp. Flat means variation is more. If the curve goes this way, it means that there is a lot of variation. I'm unsure about the middle.
in that case, you can't give the proper prediction.
It's harder. You need more data.
No, if data is more, definitely the prediction will be more.
Not necessarily. The variation of the average would go less. So let's suppose that you have no control over your diet. I'm not accusing you of anything. It happens to humans. But let's suppose that you are doing a job in which your lifestyle is very varied. You travel from place to place, you eat in different hotels, sometimes you don't eat at all, sometimes you stress out a lot, sometimes you're naturally going after trains, and sometimes you're sleeping for 12 hours in a row. Your life is highly variable. Now let's suppose, and there's nothing wrong with that, many people have very varied lives. But let's suppose I'm now trying to measure the blood sugar of such a person. What must I do? Now, try to other variables, or at the very least what I need to do is, if I simply want to get a good blood pressure measurement, is I have to measure it under many different circumstances. Or I could argue, I don't control your circumstances. I can control your circumstances. So I can say, for example, that go and measure it at this time, or go and measure it. Take a glucometer, and before going to bed, do this. Or after you've just had a very hard day, do this. I can give certain instructions to cover all the corners. Or I can simply say, I don't know, but what you need to do is you need to measure your blood pressure, your blood sugar, say every 6 hours. And then tell me what happens. But you need to do this often, because I expect your blood sugar to be highly variable. Simply because your body is being put through an enormous amount of variation. In a business situation, let's suppose that you've introduced a new product. You do not know if this new product is going to sell or not. What will you do? I mean, how will you measure it? You've just introduced it. Based on past data, you'll do that, but you've just released it. You can measure current data. No. Different situation. I've just released the product. All that is over. All that is over. I now have just released this watch in the market. What typically happens is people track the market very, very closely. Number of hits to the ads, the number of sales made, everything. The reason is because they're not sure how much this will sell. See, the question is what changed? What changed was your product release. Now the competitor could be reacting immediately. My point is not that there are many things to look at, which you should. My point is that when there is a change in the distribution, when there is an unknown distribution coming in front of you, whose variation you do not know, you tend to get more data. You sample more frequently, or you get more data. You figure this out. We do this all the time. For example, let's suppose for those of you who have kids, let's suppose your kid is going to a new school. What will you do? You'll ask more questions to them. You'll get more data. You'll find out what is happening in school. What are the teachers like, etc. Because there's too much variability standing in front of you. Now with those answers, and then you do a few trips to the school, you're now a little more, you know. You may like it, you may not like it. But you're at least more informed. That distribution is now known to you. So you get more and more data. That's why you get the experience. That's why you start getting that experience. If you have that experience already, in other words, if you know the distribution very, very well and you're comfortable with it, it'll take time to get there. And that's why this big data world is becoming so interesting, that by the time you have understood a problem, the problem is not important anymore. There's a new problem. Now this is good, right? That's why you guys have jobs. But it also means that the answer to that also means that when you have new data, you solve a different problem. You don't solve the older problem better. Which is what a statistician to some extent is trained to do. That as you get more and more data, get the distribution better. Get a better idea of the unknown. Make a better product. But the alternative view is make another product. Solve a different problem. If you have more data, so the CEO is now saying, I have more data, give me more. More of what? Solve another problem for me. Give me new customers that I can go after and things like that. So therefore, that problem is a problem that statisticians, big data people often, and it's not an easy problem to go after. That as you have more and more data coming in, how do you utilize it? How do you make efficient use of this information? Do you get tighter estimates of what you're going after? You're doing sentiment analysis of text. Many of you will do text analysis. You'll write, Twitter code in Excel, and you'll do latent semantic analysis. You'll look at positive net sentiment scores and things of that sort. And now the question will be that you know that this is going to change. People's opinions are going to change. Correct? So, over what granularity do you expect people's opinions to say the same? Do they change every day? If they change every day, there is no point looking at a person over an average of days, because that average is nothing. Every day is a different opinion. On the other hand, if their opinions change, let's say on a monthly basis, then you can look at daily averages and average them. You'll get a better estimate of that monthly rating. So you have to make a guess as to whether I'm estimating a changing thing or whether I'm estimating a solid thing better. And that's not an easy thing to do. I know it's happened to me. I don't know whether it's happened to you or not. But there are times in my life where I have simply not had haircuts. What that means is I've gone 6 months, 8 months. A haircut has been like a weight loss program. Right? I've not cared what I look like. I'm not sure I do now, but when things become very unhygienic, I go and get a haircut. There have also been times in my life when I've been a lot more conscious of what others think about me. You can imagine what points in my life. So now I groom, I'm very careful, I get my hair done and I'm all correct and I'm getting my hair cut much more regularly. Now what am I doing? So in the second case what I'm doing is I'm trying to make sure that I'm reaching a certain distributional standard. There's a certain target distribution that I have and I'm interested in getting there. I'm intolerant of variability. I'm saying that I'm going to estimate this distribution and I'm going to stay close to it. In the first case, I was not. I was perfectly okay with the variability. And in certain cases, you will be okay with the variability and you will not want to estimate a distribution of this type. And in certain cases, you will. You will want to estimate it very, very well. You'll want your hair to be done very correctly. You'll want your product to be targeted to a very specific age group. You'll want to know that when I am targeting to this particular age group, what advertisements do I want to show? You'll want to advertise it on television. And you'll want to know who is watching the program on which you're advertising this. Are they college people? Are they professionals? Are they old people sitting at home? Who will use this? And therefore, where will I advertise my cardio product? There are times when you'll want to know this very, very precisely. Or as precisely as you can. So therefore, this number, this mean number, and this number from a description perspective, is perfectly okay. It is just the average. But from an inferential perspective, it's just the beginning of the journey. It's just one number. And we're going to have to put a little more bells and whistles around this. Go ahead, you have lots of questions clearly.
Usually what we read is that a variable with not normal distribution should not be taken further in the study.
Okay, so we haven't talked about normal distributions, we will do tomorrow. But, so, statisticians need to make assumptions about their data. One of the assumptions is what he's talking about. It assumes a certain distribution. It says that I'm going to assume that the data has a normal distribution. It's an assumption. Now, why do statisticians make assumptions like that? One reason they make assumptions like that is because they make it, the calculation becomes easier. Now, just because the calculation becomes easier doesn't mean the calculation is correct. Because if the assumption is wrong, the calculation is also going to be wrong. But, because of the assumption, you can do many of these calculations. And if you don't make those assumptions, these calculations now become difficult or even impossible given the data at hand. So a lot of the tests and a lot of the procedures that we'll be talking about are going to make certain assumptions. We'll see one in about an hour or so. And if that assumption is correct, I will have a strong model. But if that assumption is wrong, I will still have a model that is indicative. So there was an economic, I think Paul Samuelson, I'm not entirely sure who, but someone who said, no, George Box, I think, the Box. He said that all models are wrong, but some models are useful. Right? So the question is, it may still be useful. If, in many cases, the distribution is expressly allowed to be not normal, the domain tells you that. Let's say that you are in an engineering domain, you know the data has a certain shape. And the engineering domain tells you that it's a shape, and the shape is sometimes called a Weibull distribution. What that means is that if you are reporting out, let's say, the failures of something, you're reporting out the failures of gas turbine blades. I've spent a number of years doing that. We had to report out a Weibull distribution. We didn't report out a normal distribution, we had to report out a Weibull distribution. In the finance industry, you report out a log normal distribution, means and variances of it. Every industry has its own favorite distribution, because every industry has its own generic data form. Now, even within the industry, a particular data set could violate that rule. And then it becomes interesting that as a statistician, do you now use a higher power tool set, a more powerful tool set to solve that? This leads to certain complexities. The first complexity that often runs into is which one, and do I do it differently from someone else? It's a little bit like a doctor who looks at a patient and says that, you know what, the textbook says that I should do it this way. But I like this guy. He looks different. I've never seen anyone like him before. So let me ignore the textbook and treat him this way. I think he'll get better. Now, could I be right? I could. But I'm taking a risk. So every time you're making an assumption on your own and following through on it, you're taking a very similar risk. You could be right for that particular case, but the precedence, you have far fewer precedences to go on. And as a result of which, later on when you extend it beyond to someone else, you're going to find it hard to do so. So therefore, people often make assumptions on distributions in a sort of historical sense, that they've known that this has worked moderately well over a period of time. And they're very hesitant to change it for particular cases. Sometimes they're not allowed to. In regulatory terms, they're not allowed to. Any accountants here? Accountants, right? So accountants, so you know this. So if you're an accountant, you have to do your books in a certain way. Right? Let's say that you're measuring cash flow. There is a certain way in which you will measure cash flow. Right? Now, you may say that in this particular month, your business was done a little differently, so I'm going to show better cash flow this way. If you can, you know you're running into trouble. Now, you may be right. You may be right in the sense that that may actually be a better way of doing it. But as soon as you go out of CFA, as soon as you go out of a very standard way of doing things, things will be a problem. And the same kind of logic applies to often statistical analysis as well. So as a result of which, like an accountant, you are doing the right thing approximately most of the time. In machine learning, there's a term that you might see. There's a term that's often called, like supervised, unsupervised, etc. It's called pack learning. Pack learning. It's a deeply technical field, and PAC stands for probably, approximately, correct. Probably, approximately, correct. I'm not telling you anything. If I'm wrong, don't blame me. But I'm probably, approximately correct. And the probabilistic part comes from statistical thinking, the approximately part comes from machine learning thinking. And it's a deep field, it's a serious field. But it puts a probabilistic statement or an approximation. So therefore, at the end of the day, whatever method you use, there has to be a sense of how generalizable it is. You will do that. You'll do that fairly soon. In a couple of months, you'll do your first hackathon. In your first hackathon, all your hackathons will have a certain field to them. A common field for a hackathon is, I'm going to give you a data set. You build your model on the data set, and I am going to have a data set that I'm not going to show you, and I'm going to tell you how well your model has done on my data set. And you have a day or 6 hours or whatever to fiddle around with your data set and show improvement on my data set. This is what you'll do. You'll do it twice, I think, in your schedule. What does that mean? It means that by being very good on your data set doesn't necessarily mean you are successful. You have to be good on my data set, but I'm not going to give you my data set. This is not as impossible as it sounds. This is a very standard problem, and this is a typical problem. You will not find this hard. You will find this very easy by the time you get there. No, not a problem. You all will. Your predecessors will. You will. You'll get 90, 96, 99, whatever % accuracy. Not to worry. Technically, this is not hard. Right. So there are two answers to that. One is, if the mean is different from the median, then you ask no. Mean being equal to the median from a distribution sense means that these are the two numbers. Okay. If the distribution looks like this, and I have a parameter mu, we're going to do this later. When statisticians use a Greek letter, they're referring to something that they do not know. Right? It's all Greek to them. So mu is a population parameter. It exists, but it is unknown. It exists, but it is unknown. Now, if the distribution is nice and symmetric like this, then this unknown thing in the middle can be estimated using a mean, or it can be estimated using a median. Now, the question becomes, which is better? And the answer to that, roughly speaking, is this, that if there are many outliers, if this distribution tends to sort of spread out to the tails, then use a median. Because of the reason that I said, the median becomes stable to outliers. If this distribution has a more bell-shaped curve of this particular kind, the mean is more efficient at this. A better answer is, what if the nature of the distribution is not that, but it is like this, then the median may be here and the mean may be here. Now you're asking different question. Now it's not a statistics question, it's a common sense or a science-like question. Which one are you interested in? Are you interested in per capita income, or are you interested in the income of the typical Indian? Correct? For example, let me ask you this. How much time, or give me one number, one representation of the amount of time that you spend on a website? I'm asking for one number. Don't tell me the number, but think in your head as to how you would answer this. How much time do you spend on a website? By a website, what I mean is this. Yes, but what does average mean? So how would I do this? So here's what I'm asking. You're cruising the web every day, let's say. So what I'm asking for is a number like this, and the amount of time that you spend on a website, you go to different websites. And you spend a variable amount of time on each of these websites for whatever be your purpose. Sometimes you're just passing through, sometimes you're seeing a video, sometimes you're sending an email, blah, 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 whatever. And every session I'm thinking of as a different website. And if you go to Google twice, then I'm thinking of that as two websites. So session wise, so to speak. Now I'm asking for a representative number. So how would you come up with that number? What's a fair answer to that? A mean. So if I do the mean, here is how I would do it. On a given day, so the first website I've gone to, I'll find out how much time I spend there. Second, how much time I spend there. Third, how much time I spend there. Fourth, how much time I spend there. And I add this up and I divide. That's the mean. Right? What would be the median? The median would be, I'd look at all those times and I sort it and I'd put this in. Which is going to be larger? It depends, is correct. But in this particular case, so think of your typical browsing habits. Now everyone's browsing habit is different. But just think of it. And people who deal with network traffic deal with this problem on a regular basis. So here is what usually happens. Most of your sessions are actually quite short. For example, a query. You go to a website and you post a query, or you go to your Gmail and you check whether there's been a new email, or you go to a favorite website, news site, and see whether something new is there or not. Most of the actual pages you visit, you don't spend a lot of time on. But sometimes you go to a website and you spend a lot of time on it. Let's say you write an email, let's say you see a video. So what does your data look like? Many small numbers and a few big numbers. This is what is called a heavy tail distribution. The histogram sometimes looks like this. Heavy tailed. This is the right tail. This is called a tail of a distribution. A tail to a statistician is not an animal thing. A tail usually refers to the end of a distribution. Some called a heavy tail distribution. And network traffic is a typical example of heavy tail. So now here is what happens. People in this particular case, the mean and the median are carrying very different kinds of information. The median is essentially saying that for a typical website that you go to, how much time do you spend on a typical website? Now, if that number is low, that is an indication that most of the time you are, shall we say, cruising or browsing. On the other hand, if you're looking at the mean and that number is high, then you know that you're spending a lot of time on certain very specific websites. And this points to two very different kinds of people. So the mean and the median are carrying different kinds of information with them, both useful. So in answer to your question, it depends on what you're going after. And in certain things you will see one of them being naturally used as opposed to the other. There's also a third one called the mode, which is actually harder. When we were statistics students, we would study mean median mode. And the mode is the peak of the distribution, what is most likely. And the reason the mode isn't talked about much is because the mode actually algorithmically is very hard to get at. The mean is a very simple algorithm. The median is a very simple algorithm. The mode is a harder algorithm. You can think about how to write a program for the mode if you want to. It's a much harder algorithm. So the mode essentially, what is the mode of this distribution, for example? So let's take a look at one of them. This is what? This is income for men. What is the modal income? The modal income is here. It's somewhere around 55,000, where this maximum is. Correct? For women, it's here, maybe just less than 50,000. So you understand what the mode is. It is the highest frequency or the most common value. But in practice, that's actually a little difficult to do. If I give you a set of numbers, how will you calculate the mode? But will you see a spike? What is a spike? So I'll give you all your ages. How will you calculate the mode? So one possibility is you will look at the age and ask which age is the commonest.
Where the count of the age is.
Where the count of the age is more. But that almost means that your data is not numerical. You're almost thinking of the data as being categorical because you're counting how many observations there are at a value. The idea of a numeric is that it is sort of continuous. It's not chunked that way. So for data that is chunked up or categorical, you can easily calculate the mode. For something that is not. And so the mode therefore has become less fashionable because it's not a very easy thing to go after. When we were in college, the mode was something actually quite easy to calculate. Here's the way we would calculate the mode. Here is the histogram. And the way we would calculate the mode is this. We draw a line from here to here. We draw a line from here to here. Left to left. Take the highest class. Draw this cross line, and here is the mode. This is the way we would do the mode in the pre-computer era. Right? I went to college where we didn't have any laptops and things like that. Running a program meant running to the computer center with pieces of paper. So many of these things were done by hand, and this is something very easy to do by manually. This is not that easy to do on a computer. The logic is twisted. You have to figure out what the bin width is. Therefore, you have to make, therefore his estimation of mode and his estimation of mode will be different from the same data set. That is not going to be true for the mean or for the median. And as soon as two different people find the same answer to the same, different answers to the same question, you know there's a problem with the statistic. So therefore, this is, so the mode isn't done as much these days. These are the histograms, sort of my data histogram. This is a way of separating out the histograms. In other words, looking at the histograms by different column equal to income essentially means that which variable, the by says which gender, so it's, and they go side by side because they essentially tell you as to what the difference in the distributions is. So what does this tell you? I could have plotted a disk plot here as well, or the code could have, but this says that there is a little bit of a difference between the male and the female distributions in shape as well as in the actual values, so to speak. And so from a descriptive perspective, you can keep doing analysis of this kind to see whether there is a difference, not just in gender variable, but in other variables as well. Do people travel the same amount of miles on different devices? A plot like this will tell you. To compare these two, what we can do in next residency, or you can do as an assignment after that, is you can say, is there a statistical difference between the miles of products that are traveled or that are used for between the different products. In other words, is there a difference between these three products in terms of how much usage they see? And you can compare three distributions. And we will compare three distributions in time. Okay. Now the last idea I want to talk about today is we've talked mostly about univariate, which is one variable. We saw a little bit of a plot, but I want to talk about, shall we say, bivariate. Bivariate means two variables at a time. If you want to talk about many variables at a time, that's called multivariate. But before we get to many, let's get to two. So we've looked at one notion, or we've looked at two notions. We've looked at the notion of location. Location means that if there is a distribution, what is its middle? And that can be mean or median. We've looked at variation, like standard deviation range and interquartile range. But when I look at distributions of two variables, there's a little bit more to it. There is a relationship between the two variables that I want to be able to capture. A sense of relation or a sense of correlation. That how do I measure whether one variable is related to the other variable or not? Remember, I'm still describing. I'm still trying to find a number. Like a mean, like a standard deviation, I'm trying to simply describe a number. If that number is this, correlation is high. If that number is this, correlation is low. What should that number be? There are many ways of defining such a number. Here is one, and is there in the book. Let's suppose, so I'm going to do this slightly abstractly. So I've got numbers that look like this, x1, these are my points. So for example, if I look at, say, a plot here, let's take one of these. This is, say, miles and income. The amount of exercise done and income. Each of these points has an x coordinate and a y coordinate. These coordinates I'm calling x1, y1, x2, y2, x3, y3, x4, y4, x180, y180. You understand? They're pairs of observations. This is, say, x1, y1. This is, say, x2, y2. This is, say, x3, y3. They're pairs of observations this way. Right? Now, x bar is what? 1 over n, x1 plus xn. And I'm going to write this simply because I'm going to have to write something a little more complicated now. Summation I is equal to 1 to n xi. If you don't like the sigma notation, that's fine. You can write it with dots. Why add a little complexity here? Y bar, which is the average, is similarly summation I is equal to 1 to n yi. Okay? Now I'm going to write something here. I'm going to write summation xi minus x bar yi minus y bar. I'm going to write that down. I'll tell you why I'm writing that down. But look at that. What is xi minus x bar? It's sort of like a variation or a spread of xi from its average. Similarly, yi minus y bar. Okay. Now, when is this term xi minus x bar, yi minus y bar, when is it positive? When both of these are positive or both of them are negative? Right? Now, both of them are positive means what? Both of them are positive means xi is above average and yi is above average. Right? Both negative means xi is below average or yi is below average. So, imagine a data set that looks like this. Where is X bar and Y bar? Somewhere in the middle here. Here is one line, sorry, here is a line and here is another line. For all the points here, Xi is above its average and Yi is above its average. For all the points here, Xi is below its average and Yi is below its average. Which means all these terms or most of these terms are going to be positive. I may still have a point, for example, say this point where it is negative. But when my data looks like this number will be positive. What happens when my data looks like this? When my data looks like this, then Xi is above its average, Yi is above its average and Xi is below its average. That means one of these is positive and one of these is negative. That means this guy is negative. So when the data looks like this becomes negative. What happens if the data looks like this? The positives and the negatives will, this number being negative means when one is high, the other is low. For example, let's say height and weight. Height and weight means what? The taller you are, the heavier you are, the relationship between the two. My doctor says that I'm about 4 or 5 kilos overweight. I say, no doctor, I'm about 2 inches too short. I don't have a weight problem, I have a height problem. Your interpretation. So therefore, if you want to therefore get a statistic that captures whether your data, whether your variables are moving together or in opposite directions. Opposite directions, for example, might be something like, say, weight of a car and mileage of a car. Bigger cars have lesser mileage. Which means that if you have an above average weight car, that probably has a lower than average mileage. So this particular measure this is an addition. When I divide it by 1 over n minus 1 to take an average effect, this thing is called the covariance of x and y. This is called the covariance of x and y. Covariance are very heavily used in certain areas. They're heavily used, for example, in dimension reduction, in principal components. You'll see that in time. They're used in finance, for portfolio management and things of that sort. This is called the covariance of x and y. What is the covariance of x and x? The covariance of x and x, which means instead of y, I'll just put x. This becomes 1 over n minus 1 summation I is equal to 1 to n xi minus x bar into xi minus x bar, which means xi minus x bar squared, which is the square of the standard deviation. This is sometimes called the variance of x, which is the same as the standard deviation of x squared. So that thing that before I took the square root, that's called the variance. With the square root is called the standard deviation. Without the square root it's called the variance. By the way, it's all there in the book. So in case you didn't get it, you can see the video or you can read the book, or these are very standard definitions. So the covariance is a measure of the nature of the relationship between x and y. If the covariance is positive, they are moving in the same direction. If the covariance is negative, they are moving in opposite directions. If the covariance is 0, then many things can happen. Either the data looks like this, there's no relation, or maybe the data looks like this. Not a normal distribution. This is not a distribution. This is, say, price and profit. For example, what is the relationship between price and profit, by the way?
Price increase, sales down.
So this is the theoretical relationship between price and profit. On this side, as price goes up, your profit increases because you're getting more money per product. And on this side, with even higher price, fewer people buy your product. So your profit goes down. Now for such a thing, the average is somewhere here. So the correlation also becomes 0. Another way to think of it is it's positive on this side and negative on this side. So if this is 0, it doesn't mean that there is no relationship. It could mean that there is a complicated relationship. Something that is positive on one side and negative on the other side, and not that simple. I once remember doing an analysis in which we were trying to find out, it was about attrition, why people leave companies. And inside it there was a model where we were trying to, for some reason, trying to find out the relationship between, or trying to understand where people stay. Do they stay close to the office or do they stay far away from office? And now what do you think is the relationship between, say, experience and distance to home?
Higher the experience, closer the distance.
Higher the experience,
The
further is the home.
No, because if I have home very far.
Tenure or experience? Okay. We had normalized for that. In other words, think of it as just experience, but we were looking at populations in which experience loosely translates to age. But you're right. There could be people who join the company very old. I agree with that. But let's simplify life and say that you have a data set in which you experience. And here's what we found. That early on in their careers, people live close by. In the middle, they moved away. And towards the end, they again became closer. Now, this was an observation. There's no science to this. This was just simply seen. In that particular company, this particular thing would happen. But remember, the point is not to describe. The point is also to predict, to understand and things like that. So we had to build a story around this when we went to the CMD and said that, here's what we had done. So you can make up a story around this. And the story we made up, correctly or incorrectly, I don't know, is that in the beginning, to some extent, people have low dependencies. You typically coming, you're unmarried, bachelor, etc. You're also ready to work a lot harder. So staying close by is convenient. You get a PG or you get an apartment, you stay close to work. Because staying further away from work gets you no particular benefit. It's just inconvenient. But as you reach in some way middle age, so to speak, things become very complicated. There is a spouse here, she may have a job, there are kids, there are schools, there's kinds of houses that you can afford. And so this solves a more complicated optimization problem, and you may not be able to find a solution to that problem close to work. But people who survive even longer in the company earn enough to solve this problem through other means. And then what happens is they move back to work again. Buy a villa close to, etc. And now there are multiple cars to take people elsewhere. Kids are often grown up. So the number of dependencies are a lot less. You may agree with the story, you may disagree with the story. But the point is that there's a complicated relationship you're trying to explain based on what the data is. Now the use of it, I won't talk about much. So this number is a number whose sign, positive or negative, tells you about the nature of the relationship. But only the sign tells you. The value is much harder to interpret. The reason is because I can measure these things in whatever units I want. Suppose I'm measuring, so height, say height and weight. And I measure height in centimeters and weight in kilograms. That's one answer. But I can measure height in feet and weight in pounds and get a different answer. I can even make this number much higher by measuring height in millimeters and weight in milligrams. I don't know why I do that, but I get. So this as a value is entirely dependent upon the units of measurement, which makes it a problem. So what statisticians do when they reach this situation is that they normalize things. They make the unit go away. So the way the unit goes away is you divide this by the standard deviation of x, and you divide this by the standard deviation of y. Now I can do this on the board without writing anything again, but I would suggest you write the whole formula again. When I divide this by the standard deviation of x and the standard deviation of y, now the units cancel out. Now this value becoming 1 means xi is 1 standard deviation above average in whatever be its units. And yi is say 2 standard deviations above average in whatever its units. The unit has gone away. This number is called the correlation between x and y. And the correlation between x and y is a number between is a number between -1 and 1. The correlation is between -1 and 1. If the data looks like this, then it is 1. If the data looks like this, then it is -1. This is the correlation. It is a measure of the relationship between two variables, measured in this very peculiar way. It is not just a measure of the relationship, it is a measure of what I would say the linear relationship between x and y. A non-linear relationship or a strange relationship could cancel out positive and negative and end up with 0 or a low number. So if the correlation is close to +1, there is a strong positive relationship between the two. Strong positive relation means what? If one of the variables is above average, then the other is also very likely to be above average, and vice versa. So what I can do is, this is the, when I do my data and I do .cor as a function, right? This gives what is called the correlation matrix. Again, it will calculate it only for the things with numbers. If it doesn't, in other words, if you give it a data frame and this doesn't happen, then just make sure that you only take the subset of it which has only the numbers. Do not calculate correlations for things that aren't numbers. If they're not numbers, there are other ways to calculate association. We'll see that later as well. Now, based on this, what do you see? First of all, the correlation between age and age is 1. Why? Well, it's the 45-degree line, right? By definition, it is 1. That this is a number that comes from one data set with one kind of relationship. What does that say anything about the practical world, so to speak? It's another way of saying what I've been saying all along. How does your data have anything to say about these relationships outside the data? The problem is a little clearer here maybe, but the problem exists for anything. So for example, there is a correlation of 0.28 between education and age. 0.28 means that there is a positive relationship, but not a very strong one. Where is that graph? This is age. Education was the second one, right? So this one, right? Or this one, whichever way. This shows that there is a weak positive relationship between them. When one goes up, the other does have a slight tendency of going up. Now I should warn you that there is no sense of causation here. There is no sense that if x goes up, then y goes up. Because correlation of x and y is the same as the correlation of y and x. Definition? This is a symmetric concept. It makes no attempt at causation. That's a different thing altogether. So this is a positive, this is a positive relationship. It's a weakly positive relationship. This is about usage and education is about 40.4. Income and education is about 0.62. Miles and usage is about 0.48. Miles and fitness is about 0.78. Let's see miles and fitness. This is miles and fitness. Nothing in this data set has a negative correlation, but you might have seen it if one was negatively correlated to the other, negatively related to the other. Okay. Close to 0. So you're looking for low correlations, right? So age and usage, for example, is a very low number. Age and miles. In other words, age doesn't seem to have much to do with things, shall we say, other than income. But age and income doesn't really have much to do with your product per se. It will be useful in when you do clustering later on. Variables like that are useful to try and segment. Rich old people. Always an interesting segment. Yes.
Correlation is 0. What is the meaning?
Correlation means 0, that there is no relationship between the variables. It could mean, for example, that a plot that looks like this. Let's pick a variable. So closest to 0 is what? Age and usage. So age and usage is where? Usage and this one? No, this is age and miles. That also is probably low probably. This one? No, there's no relationship between them in the sense that there probably is a relationship in the variability. In other words, there's more variability here than here. But if I want to draw a line through this, the line doesn't have a positive slope or a negative slope. There's no idea that says that if one of them is above average, the other is also likely to be above average. So low correlation means that there is no sense that one being above average related to the other being above average. No increasing, no decreasing. Correlations are notoriously hard numbers to interpret, but they're also very useful summaries, particularly for large data. The question that he asked is does this make any sense in the real world has two components to it. Component 1, is your relationship between the two related to a linear concept? So for example, I was talking about height and weight. What should be the relationship between height and weight? Linear. So if I plot height versus weight, I should see a straight line. Okay. Now she's going to say not necessarily. Okay. Removing outliers. We're all outliers, aren't we? Okay. Have any of you heard of a concept called the BMI? Body mass index. In this day and age, you have all heard of body mass index. क्या होता है? What is body mass index? Height by? No, there is no age in it. Height by weight squared. Height by weight squared. Now, so BMI is height by weight squared. Now, if BMI is height by weight squared, what does that tell you about the human body? Height by weight squared is what is called BMI. And this number, let's say, should be around 25 if you are healthy. What does that tell you? If you are taller, what will happen? How should your weight increase? No, there's a square here. Half the rate. So roughly this should mean, let's say that this is correct. Let's say roughly that this is correct. If this is correct, what does that mean? It means that height is approximately 25 into weight squared if you're healthy. That means if I see a bunch of very healthy people and I plot their height versus the weight, I should see a curve like that. Not a straight line. She's figuring this. She's saying, now why? If I'm twice as tall, I should be twice as heavy. Yes, if you want to give it a fancy name, correct. No, you're right. That is a parabola. Undoubtedly true. Now you could argue as to why is it height by weight squared? That's a slightly different question. Why isn't it, say, weight by height? So let's suppose that so weight by height means what? So let's suppose that these two, they're not the same. Well, let's suppose that they're, so these two, so this is a certain height, this is a certain height. If I put this on top of this, what happens to the weight? If these two are exactly the same, this is going to double. Or if I take two of these, I don't see two of them, I apologize, but anyway, okay. So here's one more. So these two, so if I put this on top of this doubles. So therefore, if I look at objects such as this, then by doubling the weight, I'm doubling the height. So height by weight remains a constant, correct? So if I'm looking at BMI for bottles this way, it should be weight by height. So if you were a bottle, your BMI would be weight by height. Okay. Now imagine that you are a football. Now if you're a football and your height doubled, how much bigger would you be? You understand the problem? Is a football, it is now twice as high. How much heavier is it? By a factor of what? So the height has doubled, volume has gone up by what? No. Pi r what? No. 4 by 3 pi r cube. It has gone up by a cubic factor. So now for a ball, the BMI should be weight by height cubed. So you're not growing like a cylinder and you're not growing like a football. You're growing like something between a cylinder and a football. We all are, not you personally. So, which is why it looks like that. Right? Babies grow like cylinders. We don't grow like cylinders, because if we grew like cylinders, we'd be a lot thinner. Think of yourself, imagine yourself when you are, 5 or 6, and now double your height. You'd be a lot thinner. Right? Similarly, you don't grow like a football as well. Imagine yourself at 5 or 6, and now imagine you grew in every dimension in the same way. You'd be a lot fatter than you are now. So therefore, this relationship depends on the empirical relationship between height and weight for the data that is available, which is of humans growing. And so empirically people have discovered that this is the object that should be invariant. This is an example of what's called dimension reduction. Two variables are being combined into one, which is carrying information for you. But it relies on a nonlinear relationship between the two that is not going to be only picked up by the correlation. So the correlation goes so far and no further. It is not one of the more analytically useful things. Very often we do test a hypothesis. Is the correlation 0 versus is the correlation not 0? To ask whether the correlation is real or what is often called spurious. And in a later class, I think about 2 or 3 residencies from now, you'll spend some time on things like spurious correlations. In other words, I'm finding a relationship between X and Y, but is it real or is it due to something else? Yes, it could start as a basis for a causation. It gives you some summary of the data. It is at best a descriptive measure of association. Sometimes people want to see it in another form. This is what's called a heat map. It is exactly the same thing as a correlation, except that in a heat map, it gives you nice colors. It gives you nice colors. And you can change those colors, so to speak. Here's the index of what the color is. -1 is pale blue, positive, etc. And positive was in the same direction. So it gives you a sense of what the color is. So sometimes when you have lots and lots of variables, this is too few a set of variables for a heat map to be useful. So for example, let's suppose that you're looking at a product catalog, a few thousand products, and you're trying to find the correlation between sales of those products across time and across geographies. And you give a display of, where, and so you do a heat map and you find those regions where the products are sort of clustering up. We often do it in medicine through what is called microarrays, where essentially we look at data from genes, and let's say there are thousands of genes, and you look at the expression levels of each of these genes, and you say these are the genes that have been expressed, and these are the genes that haven't been. So if you are doing correlations of thousands of variables or hundreds of variables, often a nicely arranged set of variables with a heat map gives you a good picture of the data. So heat map in this form is exactly the same as a correlation, except that it adds colors to the numbers. So that you're not looking at the numbers, you get a visual picture of it. So the traditional choice of it is hot is related. So red is related and white is not. But there are many ways in which you can change the coding of the heat map's colors. Okay. Now comes to some extent a tool that is descriptive. However, it is the first predictive tool that you will see. I will not want to use it like a predictive tool, but I'll still show it. So let me show you what the end product is. The end product is, I want to summarize the relationship between, say, miles, usage and fitness, variables like these. Right? Now in relationships of variables such as this kind, here's an equation. Miles is equal to minus 5.75 plus 20 into usage plus 27 into fitness. This is, shall we say, a targeted equation. What is this equation? As far as I'm concerned today, this is a description of the data. But the description of the data will be used in order to predict how many miles my instrument will run. So, think of what the instrument is. The instrument is an engineer designed instrument, and I'm trying to figure out how much it will be used, how many miles it will be used. To do that, I will figure out whether people consider themselves fit or not and how frequently they use it. And using that, I want to get an equation for the number of miles this will run. Is there a descriptive way of getting at that equation? So, what this does, this kind of an equation, it's what's called a linear regression model. This is your first model. This is going from descriptive to predictive. I haven't done it yet. I'm just saying what I'm trying to do. Self-rated fitness on a 1 to 5 scale. I'll get there. Okay, so maybe I shouldn't have shown you the output. Always dangerous to show good people output. Never show output, moral of the story. So what I want to do is keep it deliciously vague. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2. I want to fit an equation of that type. Why do we have multiple variables? I can't do it with one variable. Maybe life is simpler with one variable. You have given me itna sa data diya, ek hi variable ye kya hai yaar? So you can. In the code, as you'll see, you can have one variable, you can have two variables, you can have three variables, you can have any number of variables. I think they've chosen two to say that, I once had we were going from bivariate distribution to multivariate distribution. So he did all of bivariate distribution, and then at the end he said, now put 2 equal to n. And we were telling him, sir, it doesn't work that way. If you do it for n, I can put n equal to 2. But if you want me to put 2 equal to n, in which 2 do I put which n? So he's saying, I'll show you it for 2, but if I show it for 2, you can do it for 1, and then you can do it for 3, you can do it for any. But we can try it for 1 also if you want to. So let's look at that, and what am I trying to put here? I'm trying to put miles here, and I'm trying to put usage here, and I'm trying to put fitness here. I forget which was where, but anyway, these two variables. How am I using it to describe? So you might want to think of it this way. If I give you 3 variables, How do I describe the relationship between them? If I give you 3 variables, how do I describe the relationship between them? There are 3 variables. In the form of something like that is one way of doing it. Now, does that mean that in reality, as he might say, that there is a relationship between these 3 things? No. Correctly so, being precise. Maybe, I don't know, not necessarily. Correct. Not necessarily. So, when you do linear regression in the future, any regression for that matter, there will be 3 uses of it. Use 1, it is simply descriptive. It will simply describe the nature of the relationship to you. It will make no causal inference, no sense that this causes this. It will give you no predictive model. It simply describes, and we'll discuss how it describes. 2, it predicts. Predicts means when I put in another value of x and another value of x1 and another value of x2, I will get a different value of y, which means that I've looked at data from all of you and a new person comes into the room with a new x1 and x2 and I'll put then her number in and I will predict her y. That is the predictive use of a model. 3rd, prescriptive. In order to get a different targeted y, what changes should I make in my x1 and x2? To get different usage of the equipment, what behavioral changes do I need to make in people to get them to use more? An even more complicated use of the same thing. So the same model, the same principle can be used for different uses. I am using it simply as a description. Simply as a way to summarize not univariate, not bivariate, but trivariate or multivariate. I can do that with a 3x3 correlation matrix. But if I choose to do it this way, now what number am I looking for? Fitness is here. Average number of miles a customer expects to walk or run. Average number of times the customer plans to use. So I'm going to give it this variable and this variable and try and get an outcome for the middle one. Getting it, the way to do it is something that I won't talk about too much. So there's sklearn, which is one of the learning modules that they learn in the sense of supervised learning. Import linear model, regression linear model as a function, and the slightly irritating big function here called linear model, which is inherited from linear model. You're giving it a y. What is the y? The thing on the left hand side of the equation. What is the x? The thing on the right hand side of the equation. What is reg fit? Reg fit means regression fit. And this fits my x and y. And this outputs something. It doesn't output anything at this point in time. Now I have my regression coefficients. And my regression coefficients are 20 and 27. My regression intercept is -56. And my miles predicted is -56.54 plus 20 usage plus 27 fitness. How is this interpreted from a purely descriptive perspective? It means that, for example, if usage remains the same and my fitness goes up by 1 unit, then my miles goes up by 27 units. If my fitness remains the same and my usage goes up by say 1 hour or 1 unit, then my miles goes up by 20. What does -56 means? If you don't use it at all and you have 0 fitness, you have run -56 miles. Makes no sense, but neither does 0 fitness. So the model is not necessarily written in a way in which this intercept makes sense, which is why in the software the intercept is not treated as a coefficient. The intercept is a part of the equation, but is not one of the coefficients that you interpret. This is pure description. What does it do in case you are asking? And I hope you don't. What it does is this. What it does is, it looks at the data. And what is my data? My data is, say, y1, x1, x2. And it says this. It looks at yi minus beta naught minus beta 1 x1i minus beta 2 x2i whole squared. This is my prediction or the equation. Beta naught plus beta 1 x1 plus beta 2 x2. This is my actual. What prediction is the closest to my actual? In what sense? Find the difference between the prediction and the actual, square it, and then minimize it with respect to beta 1, beta naught, beta 1, and beta 2. So what are beta naught, beta 1, and beta 2? They're variables or they're parameters that are estimated in such a way that if I estimate it this way, this plane is the closest to the data. In what sense? In the sense that the difference between the predicted and the actual is the smallest. Don't worry, you will do this again. You will do this again. This is a very important thing in supervised learning. In prediction mode. In description mode, all that is necessary for this to happen is that it describes the nature of the relationship between miles, usage, and fitness. Describes in what way? In addition to the interpretation of the numbers, there's also something else interesting here, the positive sign. What does the positive sign mean? It means that as fitness goes up, miles goes up. As usage goes up, miles goes. I've summarized the relationship between three variables, treating one of them as a output. This is a descriptive use of linear regression as a way to describe data. Is the description real? To be decided, to be confirmed, to be analyzed, to be understood. Right? You do not know. It is empirical. It is based on data. Why is it necessarily true? Is there a logical reason why this is to be the case? Yes. You can do it with one. You can remove it. So if I remove it, what happens? So what would you do? You guys can do it if it's there. You'd move it here. Instead of usage and fitness, just have one of them there. I have not given you any idea as to whether the description is good. I have not told you whether this model is a good model or a good equation. In the same way that I did not tell you whether the correlation was good or whether the mean was good. I have not given any quality assessment to anything. These are ways to describe the quality of the model. How accurate is my mean? How good is my prediction? These are things that are going to be inference and prediction and will come. We can't answer those questions before we get to probability. In the middle here, sense of language on it. Yes. Fitness and usage as?
1 hour and probably 1
That's true. So you're saying that it doesn't make sense for certain values, which is true, which may well be. As I said, I am not saying that this is a good predictive model. What will happen is you will study a model like this and you will ask certain questions. What questions might you ask? For example, here's a question that you would ask. You would ask the question that if I fit a model like that, is this coefficient that is in front of this variable actually equal to 0? Because if it is actually equal to 0, then there is no relationship between the output and that variable. So what we do is we ask for a statement of this kind. If say yi is equal to beta naught plus beta 1 x1 plus beta 2 x2, I ask for the statement, is beta 1 equal to 0? And these are called hypotheses. Because if beta 1 is 0, then this number should not be in the model, and therefore this variable has no predictive power over this variable, which is where the analytics part becomes interesting. But to answer that question, I need to have a sense of how do I know whether this is 0 or not. And to answer that question, I need to have a sense of what the error around that number is. So this number is not 20. It is 20 plus minus something. In the same way that my mean of 28, age of 28 was not 28, it was 28 plus minus something. This is also similarly not 20, it is 20 plus minus something. And if that plus minus something includes 0, then I can't say that this is not 0. If on the other hand that plus minus does not include 0, I can say it's a predictive model. That's coming. But for now, this is simply a way to describe data. And like for means, like for correlations, like for standard deviations, and for linear regression, all of these, all will now see an inferential phase to them. The mean must see a plus minus. The regression coefficient must now see a test. Is it equal to 0 or is it not equal to 0? All these models, all these estimates will now be put into an inferential test, into a predictive test. How useful is it for new data? Because just describing current data is not going to be good enough for me. I'm writing an equation like this. I want to write this equation. I want to write miles is equal to beta naught plus beta 1 into usage plus beta 2 into fitness. I want to write this. The code now tells me what these numbers are. This number is minus 56, this number is plus 20, and the third number is plus 27. That's it. You can call it intercept based on whatever your term is. Yes. Yes. In X, just put in another variable, do comma another variable. It can be any number. Try it out. I mean, you can do it now. If I don't want to fiddle around with this, I won't plot it. My purpose is to, if I could plot it, I would. But remember, there are 3 variables. Why am I doing this? Because in 2 variables, I can plot it. I can also look at many variables at a time and see a correlation. But if I have 3 variables, plotting things becomes difficult. If I have 4 variables, plotting things becomes even more difficult. But you still do it. I think you have Tableau or in your curriculum, maybe, I'm not sure. But visualization techniques can still help you. But if you've got 10 variables, then plotting is not a way to do it. So how do I express the relationship between 10 variables? By arbitrary equations like this. What does it mean? This intercept is, if this is 0 and this is 0, what is this? But as we have said, this 0 doesn't make sense and this 0 doesn't make sense. But this is simply a line that goes through the data. If I have data that looks like this, for example, all it does is it fits this straight line. What is the intercept? Where it cuts this axis. Does it make any sense? Maybe, maybe not. This is the place where the data makes sense. But the equation is written so that it cuts the line here. Correct? If I find a relationship between height and weight, and I write the equation as y is equal to beta, or say weight, is equal to beta naught plus beta 1 into height. What is beta 1? Beta 1 is the weight of someone who has height 0. Makes no sense, right? But giving me the freedom to have a beta 1 here allows me to get a much better line, because I can move this line up and down in order to get the best fit. It allows me an extra flexibility. Don't worry. In fitting good models, you will have enough experience in doing this. My purpose is just to show you it as a way to describe 3 variables in one shot. I'm not building a model. So if I do it for 2 of them, just miles and usage, just 2 of them, this is an equation just of this kind. With 1 variable, you wouldn't do this, because there's nothing to model, right? There's no equation between 1 variable. Criteria for doing this, Remember, my purpose is not to use this to select which variables to model. When I'm calculating means and standard deviations and correlations, I'm not using them to select anything. I'm not saying that I will measure your mean because you're important, or I'll measure your standard deviation because you're low. I'm using this as a tool to summarize 3 or 4 variables. Which variables to use when in predictive mode, you can do. You can look at for high correlations, and there are many other techniques that you learn in order to figure it out. So just like a mean is a way to do analytics, correlation is a way to do analytics, standard deviation is similarly. So what we had done yesterday is we had spoken essentially about descriptive statistics, and descriptive statistics is the taking of data and to simply describe it with the later purpose of either visualizing it or writing a report or using it for inference and prediction in later courses or later applications. It is compared with predictive statistics or predictive analytics, and then prescriptive. Describing is simply a task of summarizing a given set of numbers. You'll do sessions in visualization in due course. Prediction is a task that is often in machine learning or a data mining professional's requirement to say that if something changes, then what happens. I should have made a comment that there are 2 English language words that mean more or less the same thing. One is forecasting and one is prediction. In the machine learning world, these words are used a little differently. Forecasting is usually in the context of time. So something has happened in the past, what will happen in the future? I'm giving you this week, what will happen next week? Forecasting in the future. Prediction is usually used without any sense of time. Prediction is like I'm giving you an X, you give me a Y. So I'm giving you one variable, you give me another variable. So predictive analytics doesn't necessarily forecast anything, despite the fact prediction itself is about forecasting. So the words mean slightly different things. It's a little like, price and worth mean more or less the same thing, but priceless and worthless mean different things. So the words are used in a slightly different context. So in descriptive statistics, we had looked at certain ways of doing things. For example, we had looked at what is called univariate data. Univariate means one variable. For the univariate distributions, we had seen certain kinds of descriptive statistics. Some of them were about, shall we say, location. Location meant where is the distribution, and we had seen, for example, things like means and medians, which talked about where is the distribution located. We talked about things on variation, where we had talked about standard deviation. We'll talk more about things like this today. Standard deviation, range, interquartile range. Here also we had terms, for example, like the quartiles, the upper quartile, the lower quartile. These are parameters that are used in order to convey a message to someone saying that what is the data about. So for example, a 5-point summary talks about the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Irrespective of the number of data points, you could have 10 of them, you could have 100 of them, you could have 1,000,000 of them, you could have 1,000,000,000 of them, it doesn't matter, it's still 5 numbers. Sometimes those 5 numbers tell a lot. They tell about location, they tell about spread, they talk about skewness. Is the distribution sort of tilted towards one side? Is there more data on this side than on the other in terms of the data spreading out towards the tails? So, and so there are plots associated with this as well. We talk a little bit about the plots later. Then we went towards the end, towards the idea of, let's say, bivariate data. Bivariate means that there are two variables in which we just didn't spend a lot of time. We talked about covariance and correlation. Covariance is a sense of variability of two variables together. Its univariate version is a variance, which is the square of the standard deviation. A scaled version of covariance is the correlation. If the correlation is close to +1, then it means that there is a strong positive relationship between the variables. Positive means if one goes up, the other also goes up. If one goes down, the other also goes down. Negative means the opposite. As one goes up, the other goes down. Correlation is not to be confused with causation. There is nothing in the descriptive world that says that this causes this. There is no science to this. This is simple description. The science to it and the logic to it and the use of it for inference, for business logic and things like that will come a little later. For now, we are simply describing. Then we have taken an even brief and perhaps even more confusing look at multivariate, our first multivariate summary, where we looked at the idea of a linear regression. A linear regression is an equation of the form y is equal to, say, beta naught plus beta 1 x1 plus beta p xp, where one variable is written as an equation of the others. This is merely done to describe the nature of the relationship between the variables. Correct? It can be used for prediction. It can be used for prescription if you wanted to, but that is not our purpose here. Our purpose is simply to describe a relationship. Why is this useful? Because let's say that you've got 3 variables, 4 variables, 10 variables. You need a mechanism to say how these variables are connected. How do you describe 10 things at a time? There are graphics out there. There are famous graphics in history where you have many variables being represented on one plot or one visualization. So visualizing things itself, so for example, we looked at a certain kinds of plots. We looked at, for example, histograms. We looked at box plots, sort of pairs, which were essentially what are called scatter plots. So these are for the human eye. These are things for the human eye to see data. And they have the limitations because we can only see data in a certain way. We can't see very high dimensional data. Visually, we can see up to 3 dimensions maybe. For those of you who are interested about such things, or any of you who are in the graphics world, etc., you spend a lot of time saying, how can I make people see things? So how many dimensions can you actually plot in? I mean, Python itself is good at it, but there are other devices. So for example, let's say that you're plotting, you can have, of course, one variable as x, one variable as y. Another dimension can be maybe the size of the plot. You know, if this is bigger, then another variable z becomes larger. It can be a color, like a heat map. A 4th variable, if it is low, can be blue, and if it is high, can be red. Another may be the shape of it. Lower values are circles, higher values are more pointy. So there are many ways in which you can get summarization to be done. So when you do visualization, if you do, you'll see other ways of summarizing it. But if you want to do it as a number, then something like an equation that looks like this is often a good representation. How one gets at these beta 1s and beta p's, I explained very briefly. What happens is you form this equation and you take those values of beta naught, beta 1 and beta p that are closest in some sense to the data. So if I draw a picture of, say, 2 of them, y on x, and I say give me a line, which line should I take? Take the distance from the line to the points. and make this distance the smallest. Get a line that goes through the data with the smallest distance to the points. How is small measured? Small is measured by the square of these distances, because distance on the above the line and distance in below the line are equivalent. So if this is my beta naught plus beta 1 x and this is my y, what I do is I look at y minus or yi minus beta naught minus beta 1 x I. I is equal to 1 to n, my n point, square it. This is the squared of the distances from the line, and then I minimize this with respect to beta naught and beta 1. That is how I get the numbers. But if you're simply interested in what Python or R does, then the program will simply give you what the number is.
So what those will give? This minimizing of beta 0, beta 1.
What? Sorry?
What I will get it from those?
You will get the value of beta naught and beta 1. Find the value of beta naught and beta 1 such that this is the smallest. For different values of beta naught and beta 1, this distance will be different. For different lines, this distance from the line will be different. Which line will I take? The line such that this is the smallest. How to get the beta? So, form this yi minus beta naught minus beta 1 xi squared.
On a plot, actually, that points are where the point exists.
The point is here. The points are here.
So these line is basically which.
The line is a line I'm trying to find. Here is a point. 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 Right? Let's say I have 5 points. I want to describe the relationship between these 5 points. Therefore, what I need to do is, I need to find a line that goes through these points. I want to write an equation of the type y is equal to, say, I'll remove the b and x, y is equal to a plus bx. I want a line like a plus bx going through those points. There are many lines. This is one line, this is one line, this is one line, this is one line, they're all lines. Which line will I use to represent the relationship between y and x? I need a criteria. So what I do is, I try to say, let me find a line, let's say that this is the line, and find out how good it is at describing the data. Now, when is it good at describing the data? When it passes close to the points. Because that is its purpose, to describe the data. Because I want to say that this line, without any data points, is a description of the data.
But how to get that line position?
That's what I'm talking about. So I need the value of A and B. Correct? So how do I find the value of A and B? For every such line, A and B, I find the distance of the points to the line. So if there are, how many points do I have here? I've got 5 points. So I've got 5 distances. What are the points? This is the point x1, y1. This is the point, say, x2, y2, x3, y3, x4, y4, and x5, y5. These are my 5 points. How far is the point x1, y1 from the line? This distance. And what is this distance? This distance is how much? This distance is, this point is y1 minus what is this point? A, so A plus B x1. That's the point on the line. Correct? Okay. I can stop here, but if I stop here, what will happen is that if this is the distance, then this will become a negative distance and this will become a positive distance, and they will cancel or neutralize, as you say.
Sir, A is which point, which is from that point to the line, actually that is the A distance.
No, A is this equation. A is the equation of the line. You want to know what the term A is? A is this point. B is this slope. And I want to find A and B. So this equation is A plus BX. So this point is Y, and this length of this line is Y minus A plus BX1 squared. Plus, for the second one, what is it for the second one? Y2 minus A minus BX2 whole squared. Do this 5 times. Correct? For every line, you will get this number. If you want to, you can take a square root. For every line, you will get this number. This number is the sum of squared distances of the line from the data. It tells you how far the line is from the data. The larger this number is, the further the line is from the data. The smaller this number is, the closer it is to the data. If the data is on the line, what is the value of this? 0. So if every point is on the line, or if the data is itself a straight line, then this will be 0. So I have formed this. Now I find the value of A and B such that that is the smallest. For every A and B, I will get the value like this. If I take another line, I will get another value of this. For every choice of A and B, I will get a difference distance from the data. Which A and B will I pick? That A and B such that this distance becomes the smallest.
So can we have an issue where the algorithm means computationally we don't find the value of which can kind of minimize, means the kind of
okay, so let me finish this. So choose A and B to minimize this, and that is the A and B that the software gives you. This is called a linear regression, right? Answer 2, does it have a least square? This is why Gauss was so successful and Laplace was not. You will get a unique solution. This is what's called a convex problem. And this is a convex optimization because of the squaring. If you have modulus values here, there is a possibility that you will not get a single answer. But because of this, and because of the square, and because of the nice bowl-shaped curve that the square function gives you, you will find a unique solution to this.
So how many times the system tries? The number of data points?
No, the system doesn't do it that way. The way the system does it is, the system differentiates this with respect to A and B, differentiates with respect to A, sets equal to 0, differentiates with respect to B, sets equal to 0, and solves those two equations. It doesn't minimize. It doesn't minimize. When this becomes very high dimensional, this minimization, this differentiation of solving it becomes a very interesting problem in mathematics and numerical analysis. To do that, you need typically to do linear algebra, and in courses such as this and in machine learning books, you will see at the beginning of the book, you will often find chapters on optimization and linear algebra because of this or something similar to this. That to represent a problem, you often need a matrix representation, and to get a good learned solution, you need an optimization. So most machine learning algorithms are built that way. Because, for example, as I was saying yesterday, that you're going to tell someone to do something. You're going to tell a car to behave itself on the road. Yesterday, while going back, today morning, I heard that, or I read that BMW and Daimler are setting up a, €1 billion R&D operation somewhere in Europe for self-driving cars, etc., etc. Two different industries are trying to go towards making cars that don't need people. The automobile industry is, as well as the ride-hailing industry. People like Uber and Lyft and Ola and these companies. So now you're going to figure out, the car is now going to have to be told when to go and when to stop. But how does the car know that it has a good rule? How does it know that it has learned? And what is good learning as opposed to bad learning? What is enough learning as opposed to not enough learning? A computer is stupid. All a computer can do is store a lot of data and do calculations quickly. Computers aren't intelligent. To make the computer intelligent, you have to give it an intelligent function. You have to say, okay, run your algorithm such that this thing becomes the highest it can be, or this thing becomes the lowest it can be, which is an optimization problem. So what machine learning algorithms almost invariably do is they say that here is an input and here is an output. Give me an algorithm such that based on the input, you can come closest to the output. For example, object recognition. If I'm teaching computer vision, or if I'm teaching text recognition, or any of these, let's say text recognition. So I'm trying to understand what the word is. So the computer is reading something, let's say in handwriting, and it's trying to identify that as an English language or a Kannada or a Hindi phrase. So it's going to write something down. You write this, and in my horrible handwriting, I'll write something, and that camera has to recognize what I wrote and transcribe it into something that you can read. Now, how does it know it's done a good job? What it needs to know is that this is what I think the word is, and this is what the correct word is. Now tell me whether I'm close. And if I'm close, I'm good. If I'm not close, I'm not good. But this has to work not just for one word, this has to work for thousands of words. So I must be close to thousands of words at the same time. Therefore, I need to measure the distance from my prediction and my actuality over many, many data points. So all these algorithms, what they do is they take your prediction and they compare with the actuality. And they find a distance between them. And they minimize the totality of the distance between the prediction and the actual. And an algorithm that minimizes that distance is a good algorithm. It has learned well. So they all do something like this. Where this is the prediction and this is the actual. And A and B are the parameters in the prediction. In other words, find a prediction such that it is closest to the actual. So this algorithm has become very popular. It's probably the single most popular fitting algorithm out there. This is called least squares. Least squares. This is called least squares. Squares. Here's a square. Least because you are minimizing. This is called least squares. And the least squares algorithm is a very standard way of doing things. This has nothing to do with the algorithm itself. The algorithm can be anything. This itself can be a neural network. It can be a support vector machine. It can be a random forest. It can be association rule. It can be any of your logics. But the question is, if you give me the program, how do I know whether the program is good? So I give it what's called training data. Training data means I tell it what the right answer is.
So sir,
yes.
This we can infer that this is the starting point of basically what the prediction and what actuality is that we are comparing, and
yes.
we are getting the result of that?
Yes. So this is the prediction. This line is the prediction if you want to think of it. The data points are the actuality. The problem is this. These data points are also not the actuality. The actuality is going to come in the future. It is a training set for the data. It is the data that has been given to the algorithm to train it. But it is not the algorithm, it is not the data that the data will actually run on. The car will run on the road. The car will see its data points its people and other cars and the cows and whatever for the first time. It will not have seen that data before, but it will need to know what to do.
Starting of learning basically.
Yes, so what do you do? So what you do is you train the algorithm. What does training the algorithm mean? Training the algorithm means you give it data for which the car is told what to do. In other words, you give it what they call ground truth. So you give it the why and you say, here is the data or here is the situation, please do the right thing. So please do it such as this. So here's a person who's crossing the road. Please stop. Here is another person crossing the road, but he's very far away. Calculate the distance, compare with your speed and decide what to do. He may be far enough for you to be able to see, but you may not stop. If you are driving a car, it's quite possible that you are seeing someone crossing the road, but maybe about close to 100 meters ahead and you're not slowing down. Because you're doing the calculation that I have a speed, the person crossing the road also has a speed, and by the time I get there, this person would have gone. Do not do this when doing a level crossing. But we all do this all the time. We do this when crossing the road. So I'm happily doing that. There is a car coming, but I'm still crossing the road. Why? Because I know that I'll be able to cross the road before I get there. So the car needs to be taught how to do these things. So this data, it's given data like this and says, for the training data, get as close as you possibly can to the training data. And then it's given what's called test data. And now the algorithm is told, oh, now I'm going to give you new data. And now you're going to tell me how well you did on new data. So suppose you were given a problem like this. I'm not supposed to talk about this. Your ML instructors are supposed to talk about this. But suppose you're given a problem like this. In other words, I've given you a data set and I'm going to tell you that your performance will be judged not by this data set, but on another data set that I am not giving you. What will you do? How will you make your program ready? Yes, so how will you make your program generalizable? So the usual way it's done is something interesting. You say that, okay, you want me to predict data that I have not seen. I will see if I can do that. So what you do is all the data that is available, you take a certain part of it and you keep it aside. You have it, but you don't use it. And now the remaining part of the data you build your algorithm on. And now you test it on the kind of data that you yourself have but have kept aside. This is called validation data. And now if your algorithm works on your own held out data, that data that your algorithm has not seen, you are more hopeful that it will work on somebody else's new data. This is called validation. And this entire cycle is often called test, validate, train, etc. Or train, validate, test, etc. And you will do this in your hackathons. But to do this, the algorithm needs to know as to how good it is. And it needs measures like this. There are other measures. So for example, if you're classifying an algorithm, good or bad, positive sentiment on tweet or negative sentiment on tweet, no numbers, then you do not need this. What you need is simply, are you correct or are you incorrect? If it is correct, let's say you give yourself 0 distance. If it is incorrect, let's say you give yourself 1 distance. In other words, you made 1 error. And you just count how many mistakes you made. But what is a mistake when it comes to estimating a number? Like say miles and things like that. There's no mistake. You're either close or you are far. So you need a measure of how close. That's a measure of how close. So this descriptive method is used as a criteria for building predictive models. This itself can be a predictive model, but very rarely is it good enough. Too few things in the world are this simple. Are there things in the world this simple? Yes. But as we said, as we discussed yesterday, even things like height and weight are not that simple. There are complexities to that. So for example, you can have theories which say, for example, you could say, let's say a savings rate. What's a savings rate? A savings rate is the proportion of money that you save. Now, if there is a savings rate, what that would mean is that if I take your income data and I take your consumption data, that should form a straight line. Because you're saving up the same proportion every month. But it's not. If you go home and month by month you figured out what your income was fairly precisely from your salary or from other sources, etc., etc., and you also plot again fairly precisely as you can how much your household spent that month, it will have an increasing effect probably, but it's very, very unlikely to be a straight line. In certain things you may be going after a law of physics, but the law of physics may hold for gravity, may not hold for anything else. I remember trying to apply this, so one day cricket sort of became popular when I was in school or thereabouts, and one calculation was done as to how to figure out whether a team is doing well or how well is a chase going. So one possibility is to simply track the score. The other possibility is to say that if you know how many runs you're going to get, you tend to begin slow, protect your wickets and you accelerate. So what you do is you build models for that. You build models for saying that let me assume that the team is going to accelerate constantly, which means that every over that comes later it's going to get better. Its run rate is going to keep increasing steadily. Now if its run rate keeps increasing steadily, then when will it reach the halfway point? That is the same thing as asking the question that if I take a ball and I drop it, how long will it take to get to the halfway point? And there's a square root term there, and the answer is about 50 divided by the square root of 2, about the 37th over or something of that sort. So effectively the logic was, if you have reached halfway point below, let's say, the 37th over or so, you are on track. If not, you need to accelerate a little faster. That's using a physical law to try and predict something that is not a physical law. I mean, the laws of physics do not apply to cricket, at least not in this way that I am describing. So therefore, these laws will get you somewhere, like a straight line, etc., but they are approximations. And so what you will do is you will build better versions of this when you use it for an actual prediction. But the same argument holds for things like mean, standard deviations and many such things. If there's a specific problem you need to solve, you may or may get a better estimate for doing it. Yes, someone was asking a question.
The question is that we calculated y minus a plus
yes.
x1. That is basically the distance.
Yes.
Right? What we are talking
yes.
about on the line.
Yes.
Then what the b is actually that is what we talked about.
So there are many ways to do that. One is you just put it in, you find for different values of a and b, you find what that number is, and then you solve it. If you want to do it the hard way, you can still do it the hard way, and the hard way will end up being something like this. I'm minimizing, and I should not be talking about this. Say yi minus beta naught minus beta 1 xi whole square. I was using a and b, right? So say a and b whole square. I'm going to minimize this with respect to a and b. So essentially what I'm going to do is I'm going to call this, let's say, L of a and b. And I will say DDA of LA is equal to 0. DDB of LB is equal to 0. And I will solve these, and this will give me two interesting equations. And my answers will be this. I'll tell you what the answer is. Your B hat, your estimate of B will be this. Summation xi minus x bar yi minus y bar divided by summation xi minus x bar whole square. And your A will be this, y bar minus b hat x bar. So if you want formulas, these are your formulas. Because I'm minimizing something. To minimize something is the same thing as setting its derivative 0. Now that is also the same as maximizing something, but this is where convex optimization comes in. That this will have a minima, but won't have a maximum. So by setting it equal to 0, I'm going to arrive at the minimum.
So,
yes.
The minimum will come with respect to A, right? Not with respect to X and Y.
Yes, X and Y are fixed. The data is fixed. The parameter is varying.
The range is fixed.
X and Y are fixed for my data, correct? So my B is written in terms of A and. So this is a formula. If you want to close it, this can also be written as the covariance of X and Y divided by the variance of X. So if you want to calculate it for two variables, what you need to do is you need to calculate the covariance and divide by the variance. And here y bar minus bx bar, this means that the line passes through x bar y bar, the line passes through the middle of the data.
So with the derivative, the minimum will be, we are minimizing A, right?
We are minimizing with respect to A. A is a variable.
So how come this equal to 0 will minimize the distance? And
how it will do this? So for different values of A and B, the distance will look like this. There's a particular value of A and B in which the distance will be this. There's another value of A and B in which the distance will be this. There's a particular value of A and B in which the distance will be this.
That is corresponding to the axis.
This is my summation yi minus A minus B xi whole squared. This value. For different values of A and B, I will get this. So when I minimize this, now to do this, you don't need to do it. All you need to do, if you want to do it, is this. If you want to do it, do this. Do you have yesterday's code? Open it. You can do it. Then right now, that's it. You stop. It's like saying I get the mean, then what? One use of it is to predict. Another use of it is to prescribe. There are many uses of it. A third use is to do nothing, but simply to use it to visualize or to summarize the relationship between two variables. Correct? And we do this all the time. So for example, how do you measure how price sensitive your product is? Do you understand the question? You're trying to change the price of your product. Why would you want to change the price of your product? Profitability. Maybe you want to increase it so that you get more money. So people in marketing often want to understand how sensitive my sales are to price. Now to do that, they come up with various kinds of measures. One particular measure is what is called the elasticity of demand. Elasticity of demand means this: if my price changes by 1%, by what percentage does my sales change? Well, if my price goes down, I would expect my demand to go up. But by how much? Now there are certain assumptions to this. For example, it's assumed that the same number works if it increase price as well as you decrease price. So this is called the elasticity of demand. So therefore, to get the elasticity of demand, but what is the elasticity of demand? The elasticity of demand is essentially a slope. A slope that relates something like this, that if I have demand on this side, let's say sales on this side and price on this side, I have this negative slope. The slope of this is what the elasticity is. So very often you do equations like these in order to simply get at a number that has a certain meaning for you. So the slope of a linear regression between log sales and log price is the elasticity of demand for that product. I mentioned log sales and log price because the elasticity is done in terms of percentages. A percentage increase in price and a percentage decrease in sales. If I don't do it as a percentage, there's a problem. Now my measure depends on my units. Is it 1000 units per rupee? Or what? It depends on what I'm selling in one currency. And that's not a good measure. So I measure it as percentages. But when I measure it as percentages, I have to measure on the log scale. So there are many models like this, where the equation itself is used to simply describe a parameter. Something that tells you a little bit about the market. Like an elasticity of demand. You're not using it to predict anything. You're simply using it as a descriptor. So you say that this is an inelastic product. If this is an inelastic product, what does that mean? It means that if you change its price, there won't be too much of a change in its demand. Classic examples of that, for example, are salt. If you change the price of salt a little bit, at least certainly domestic salt, there won't be too much of a change in demand. There might be a little bit, but there are certain things that are highly inelastic. You change it a little bit and the demand will change a lot. And marketing people are very sensitive to this idea, saying that is my demand elastic or is it inelastic? If I want my prices to go up, then I want the demand to be inelastic, because I don't want my demand to go down. If I want my prices to go down, or if I'm pulling my prices down, then I want the demand to be elastic, because I want people to say that your prices are going down, therefore I will buy more. So marketing analytics is very concerned with things like this. So therefore, sometimes an equation of this kind is built just to describe something. Right? So what I'm going to do is, let's go down. And since we are going to do this just on 2, let's pick it just on 2. So let's change this to maybe miles, and let me remove this. So what I'm going to do is, I'm just going to do it on one of them. I suspect one parenthesis might then work. I suspect this might work.
2 params.
X has to be in 2 simply because of the way it's entered. Because I have not done anything on this data set now. This one is a comment. So what do I have on the coefficient here? 36 and 22. So what is my equation based on this? Miles is equal to minus 22 plus 36.29 whatever into usage. Okay? Alright. Now let's try to do this manually if you want to. If I want to do this manually, so I need to get at each of these things. So now I need to find, for example, let's say the covariance between miles and usage. How do I do that? Tell me. No, not a sample. The data is present in me. So now I have things like, for example, my data, miles. Correct? So I can calculate things on this. So for example, I can do this. This is the mean. I can do calculations on this. Okay. So now if I do say what is the standard deviation syntax? ST, not DV. Okay. This is standard deviation. Okay. Let's try one more. This is the variance. What is the variance? The square of the standard deviation. Okay. Now I want to find the covariance of these. How will I find the covariance? Not necessary. Remember, I have the correlation function. How did I find the correlation function here? I found the correlation function from here. So I've got a number of ways to potentially do this. One is I can do it with the correlation function or the covariance function. In other words, so for example, I can try doing this. How do I write it here? My data dot this thing here was the correlation. This gives the covariance matrix. This gives the covariance matrix. Okay. Now, what is the value of B according to my formula? So, covariance of which variables now? Which are my two variables? Miles and usage. Where is that covariance? Is it this number? 42.71, right? Okay. Divided by what? Variance of what? No. Variance of usage. Why? Not y as in y, but y as in question mark y. So my data dot usage dot var. Is this also here in the data? It is, because what is the what is the diagonal element of this? What is this number? Usage dot. This is usage 1.17. This number here. This number here is the variance. Okay. What is the equation? Usage. This is my x. This is my y. This is my x. So covariance of xy divided by the variance of x. So based on this, what is my answer? My answer is going to be the answer for my coefficient is going to be, where is the covariance? Here, 42 point, I can do it, manually, almost 42.71 divided by, where is the variance? 1.17, say, 6 or something of that sort. 36.318. Where is my value of B? Here. This is my slope. Right? How do I get my intercept? Mean of y. So my data this is the mean of all of them. So what do I want? Which mean do I want? Mean of, what is my y here? Miles. Where is my mean miles? Let's say 103, say say 19, minus, what is my slope? Say 36.32 or something of that sort, star, what is my x? Usage, which is 3.45, so 3.45, 3.3.45 or something like that, right? Will star work that way? Minus 22. What is my coefficient? Minus 22. So if you want to, you can do this from first principles by using that formula.
So now that you understand the foundation of data science, let's look at how we can implement it in Python. Here are some of the topics we will cover. First, we shall discuss the basics of Python. Understanding data structures is vital for data science, so we will go into how they are implemented in Python. Then, we will understand the flow of control statements in Python. We will also dive into some object-oriented programming, a core characteristic of Python. From there, we'll delve into numerical computing with NumPy libraries in Python. We will also cover data manipulation with the Pandas library in Python. Then, we'll show you how data can be visualized in Python using Matplotlib. We will then get into some learning algorithms like linear regression algorithm and logistic regression algorithm. The second half of the course will be taught by Mr. Mukesh Rao. He is an adjunct faculty at Great Lakes for Big Data and Machine Learning. Mukesh has over 20 years of industry experience in market research, project management, and data science. He has conducted over 100 corporate training sessions. Let's get this started. And remember, it's all about great learning.
So let's start off by installing Python, and we can install Python from this website over here, www.python.org. So I'll click on this. Right, so you see that you have the latest version of Python over here, Python 3.8.0, and you can download the Python version with respect to whatever operating system you're using. So if you have a Windows system, then you can download Python for Windows. If you have a Linux or Unix system, then you can download Python for Linux or Unix. And if you have a Mac operating system, then you can download Python for Mac operating system. And since I have a Windows system, I'll download it for Windows. So I'll just click on this over here, and you see that the download has started. Right. So now I actually have Python installed in my system. So once the installation of Python is done, we need something known as an IDE. So IDE basically stands for Integrated Development Environment. And Integrated Development Environment basically makes your work much easier while programming. So it gives you certain prompts and you have all of the tools present in the IDE. And one such IDE, which is very famous for Python, is PyCharm. So we can install PyCharm from this site over here, jetbrains.com/PyCharm. So let's just wait till the site opens up. Right, so you have the download button over here. You just click on this. And for our programming purpose, we'll just download this community version over here, right? So for pure Python development, you click on download and the download would start. And again, since I'm using a Windows system, so this is for the Windows system over here. All right. Now, Anaconda is a Python distribution which basically provides you all of the packages inbuilt. So you have packages such as Matplotlib for visualization, Pandas for data manipulation, and NumPy for numerical computing. So you don't have to manually install all of these packages. So when you actually install Anaconda, all of these packages are actually pre-installed in Anaconda. And for doing all of your coding, you have something known as the Jupyter Notebook. So first to use the Jupyter Notebook, we would need Anaconda. So let's go ahead and install Anaconda. Right, so this is anaconda.com, and I'll just click on download now. So we need the Anaconda distribution. And again, I'll click on download, right? So we've got Windows, Mac OS, and Linux. And this is the latest version of Python 3.7. So that is what we had downloaded earlier. So this was the older version of Python 2.7, but everyone has moved on to Python 3.7 now. And that is why we'll also be downloading Anaconda for the latest Python version, which is Python 3.7. So it'll automatically start the download for 64-bit operating system. So once the download for Anaconda is done, we need something known as the Jupyter Notebook, which I've already told you. So as it is written over here, Jupyter Notebook is basically a browser-based interpreter that allows us to interactively work with Python. And this is how your Jupyter Notebook looks like. So let me go ahead and open up Jupyter Notebook. Right, so let me open up Anaconda prompt first. So I'll type in Anaconda prompt. So this is the command line interface. Now to open up Jupyter Notebook, I'll just type in Jupyter space notebook, and let me wait till this opens up. Alright, so this is the Jupyter Notebook over here, right? And this is how it looks like. Now to open up a new notebook, we just have to click on new, and we'll click this new Python 3 notebook, and we have successfully opened our new Python notebook. Let me just rename this to Python programming. Now once this is done, let's go ahead and write our first Python program. So we'll just use the print statement. So you just have to type in print, and inside this I'll type in, let's say, this is Sparta, and all you have to do is click on run, and you have your first program ready. You have successfully printed this is Sparta on the console. Well, you've just taken the first step to hacking NASA, right? So you just have to take the baby steps and you'll be an expert at Python programming, and you have successfully started with your first Python program. All right. So now that we have written our first Python program, the question which needs to arise in your mind is, every programming language needs to deal with a lot of data. So where do we actually store this data? Well, this is where variables come in. So let's say you have to store the names of all of the students present in a classroom. So let's say the names are John, Sam, Matt, Bob, Anne, Julia, and so on. And you have 50 such names. And you have to store all of these names somewhere. So how do you do it? Well, all you have to do is take a variable and store all of these names in a variable. Now, you must be thinking, what exactly is a variable? So let's understand that with this example. So simply put, variables are basically temporary storage spaces where you can store data or values. Now let's take this example over here. So consider this folder to be a variable. So what you do is you store this value temporarily inside this folder. So this value is John, which is the name of the student. So you've taken this value and place inside this variable for a certain amount of time. Now after that, since this is only a temporary storage space, you can take out this variable and replace it with Sam, right? So now this variable holds the value Sam. And after some time, again, you decide that Sam is not the name which I want to store and I want to store the name Matt. So again, you take out the name Sam and store Matt inside this folder. So this is how variables work. They are temporary storage values where you can keep on changing the values inside it. So now that we know what exactly are variables, let's go to Jupyter Notebook and work with variables. So again, I'll open up a new Python 3 notebook over here. So now to assign a variable, I'll just create a new object over here and I'll name it as var1. I'll use the assignment operator and I'll give in the name. So the first name would be Bob, and to print it out, I'll just type in var1 over here again. Right, so we have successfully stored the value Bob inside var1. Now I'll change the value inside this variable. So what I'll do is I will actually store the value Sam inside this var1 and let me print it out again. So now var1 stores Sam. So initially var1 had the value Bob and after some time I had replaced the value with Sam. Now again, let me change the value. So inside var1 I will be storing Matt and let me print it out again. So this time it has the value Matt. So as you see, variables are just temporary storage spaces where the values can be changed. Now every variable is actually associated with a data type. So there are different types of data which a variable can hold. It can be of integer type, it can be floating or decimal type, it can be a boolean, it can be a string. So when it comes to integers, so you basically have numbers such as 10, 500, 1000, -10, -27 and so on. And floating are basically decimal point numbers, so 3.14, 15.97 or -2.1678. So any such decimal point number would be a floating point number. And then you've got Boolean values or basically logical values, and true and false are basically your Boolean values. And then you finally have the string values. So a string is basically a set of characters enclosed together, right? So Sam is basically a set of characters, it is a string. And then you have Matt, which is basically a set of characters, it is a string. And strings are generally enclosed within double quotes, single quotes or triple quotes. Right, now let's assign some different types of data to our variables. So let me create a new variable A and I'll store the value 10 inside this. Now I'll go ahead and check the type of this. So the type of this variable would be int. Now inside A, I'll actually store a decimal point number. So this time I'll store 13.4 and then let me check the type of it. So type of A, again I'll click on run. So this time we see that there's a floating point number. So what you can basically notice is the type of the variable would depend on the type of the data which you are actually storing inside the variable. So if you store an integer type data inside the variable, then the type of the variable would be integer. And if you store a floating point or a decimal type data inside the variable, then the type of the variable would be floating type. Now similarly, let me go ahead and store a Boolean value inside this. So I'll store true inside this. Let me check type of A. So the type of A is bool. Now let me store a character value. So I'll type hello world. Let me remove out this W over here. And then again, I'll check the type of this. So type of A. And then the type of A is string. So finally, we have one more type of data, which is basically complex number. So complex numbers, you basically know that it has a real part and an imaginary part. So let me just type it out. So 4 plus, let's say 8j. Now, normally in mathematics, it is actually represented as 4 plus 8i. Now, when it comes to Python programming, we represent the imaginary part with j. So 4 is the real part over here and 8j is the imaginary part over here. So just to confirm it, I'll again check the type. So type of A. The type of A is complex. So all of these are the different types of data which we can work with in Python. So going ahead, we'll work with operators in Python. So we've got arithmetic operators, relational operators, and logical operators. So let's start off with arithmetic operators. I'll head on to Jupyter Notebook over here, and arithmetic operators are basically the normal mathematical operations which you do. So that would be addition, subtraction, and then you've got division, and then you've got multiplication. So these are the different symbols which you'll be using to perform these operations. So we'll start off with addition. So let me just add in a comment. So to add in a comment, you will use this hash, and then you'll type in whatever you want to add. So comments are basically statements which are not executed by the Python interpreter. And these are only to help the coder or the learner. Right. So I'll execute this cell over here. So I'll have one variable and I'll store 10 inside this, and I'll have another variable B. I'll store 20 inside this. I'll click on run. All right. So I'll start with addition operation. So I'll just type in A plus B and you get the value of 30. Well, this is quite simple. So this is the basic addition operation which you've been doing since your kindergarten, right? And also we'll be doing some similar operations. And then I'll go ahead and perform A minus B. So what do you think is the answer? Well, it's minus 10, because when you subtract 20 from 10, you'll get a value of minus 10. Now let's also multiply these two numbers. So I'll just type in A cross B. So that would be 10 into 20, which will give you 200. And then finally, I'll just type in A divided by B. So you'll get a value of 0.5. So 10 by 20 gives you a value of 0.5. So these were the basic arithmetic operations. Now we'll go ahead and work with some relational operators. So I'll just type in relational operators over here. So again, I'm putting down a comment. So relational operators. And relational operators basically help you to understand the relation between two variables. Now, what do I mean when I say it helps us to understand the relationship between two variables? So let's say when you have two variables, the value in one variable could either be greater than the value in the second variable, or it could be less than the value in the second variable, or it could be equal, or there might be no relation at all between these two variables. So this is where we'll have relational operators to find out what is the exact relation between two operands. Right. So again, I'll just type in A equals 10 and B equals 20 over here. I'll click on run. Right. So I'll start with the less than operator. So I'll type in A less than B. So over here, I'm just checking if the value of A is actually less than the value of B. So we get a value of true. This means that 10 is actually less than 20. Now let me check if A is greater than B. Now we get a false value because 10 is not greater than 20. Now I have the double equal to operator. So with the help of the double equal to operator, we check if both of these values are equal to each other. Again, we get a false value because 10 is not equal to 20. Now there is the not equal to operator. So A is not equal to B. So A, I'll give in this exclamation mark, and then I'll give in this equal to symbol, and then I'll give the second operand, which is B. So we see that A is obviously not equal to B, or in other terms, 10 is not equal to 20. So these were some basic relational operators. And then we'll go ahead and work with the logical operators. So I'll type in logical operators over here. So the two basic logical operators are AND, OR. And this is how you represent the AND operator, and this is how you represent the OR operator. Now we'll actually start with the AND operator. Now, AND operator is used to check the condition or the logic between two variables. And this is how the AND operator works. So if both of the operands are true, only then the final result will evaluate to true. And if either of the operands is false or both of the operands is false, then the final result will be false. So I'll just create two variables over here, and this time I'll be storing the value true inside A, and I'll be storing false inside B. So I'll just execute this over here. All right. So now I'll type in A and B. So we are basically checking true and false. So what do you think will be the result? We get a false value because we need two trues. And only when we have two trues, that is when we'll get the true value. Now we'll check B and A. So when it comes to B and A, we are basically changing the position of these operands. That's it. So now it becomes false and true. And the answer is false. Now let me check A and A. So this will be true and true. So when you compare true and true, you get a true value. And finally, let me check B and B. You get a false value. So this is how the AND operator works. Now let's go ahead and work with the OR operator. So when it comes to the OR operator, if either of the operands is true or both of the operands are true, then you get a true value. And only when both of the operands are false, that is when you'll have a false value. So this time I'll type in A or B. This would mean true or false, and obviously we have a true value over here. Then I'll type in B or A. So this would mean false or true, and we obviously have a true value. Now let me go ahead and check A or A. So this would mean true or true. So when you have two trues, obviously it's a true value. And then finally, let me check B or B. And we have a false. So this is the only condition where you'll get a false value when it comes to OR. Right, so those were the basic operators in Python. Now let's head on to Python strings. So Python strings are the most widely used data types when it comes to Python. And as I've already told you, strings are basically sequence of characters which are enclosed within single quotes, double quotes, or triple quotes. And triple quotes are used to denote multi-line strings. So as you see this example over here, I am going to France tomorrow. So you have triple quotes around the string because this is present in multiple lines. So hello world is present in single quotes. This is a string. This is Sparta is present in double quotes. And again, this is a string. But when it comes to I am going to France tomorrow, this is a multi-line string. So that's the basic premise for strings. So now let's go to Jupyter Notebook and work with these strings. Alright, so I'll create a new variable over here and I'll store a string inside this. So I'll put in the string Joey doesn't share pizza. I'll click on run. Alright, so obviously no one likes to share their pizza, do we? Right? So now let's go ahead and work with the string. So let's say I'd want to extract the first character, which is J, from this entire string. Now when it comes to Python, the indexing starts from 0. So J is basically present at index number 0. So if I want to extract J, I'll type in A1, I'll put in square braces, and then I'll type in 0. And I have successfully extracted the first letter. And similarly, if I want to extract the last character from this entire string, so for that, you'd have to put in -1. And when I click on run, you get the value A. So this is how you extract the last character from the entire string. Now let's say I want to extract a sequence of characters. So I'd want to extract this entire word, which is doesn't. So 0, 1, 2, 3, 4, 5. So the index starts at 5 and it will go on to 6, 7, 8, 9, 10, 11, and 12. So let me type in 12 over here. I'll click on run, right? Now over here I've given 12 because when it comes to the second term over here, it is exclusive. So 5 is inclusive, 12 is exclusive. So 0, 1, 2, 3, 4, 5. D is present at index number 5. Then 6, 7, 8, 9, 10, and 11. So T is present at index number 11. But if you only given 11 over here, then you'll get dozen, right? So what you have to keep in mind is when it comes to the second indexing term, it is exclusive. So that is why you'd have to go in till 12 and you'll get the entire word, which is doesn't. Now let's see how can we check the length of a string. So to check the length of a string, we have this length function. So inside len, I'll just pass in this variable, which is a1. And we see that the length of the string is 24 characters. Now when you say 24, so this would include all of the spaces and all of the apostrophes and full stops and all of those characters as well. All right. Now let's go ahead and work with some of the inbuilt functions of strings. So if I want to convert all of these characters into uppercase, so I'll just have to type in A1 and then I have this function upper. So I'll click on run, right? So I have successfully converted all of these characters to capital. Now similarly, if I want to change all of these to small case, so I'll type in A1 dot lower. So everything is turned to lowercase. Now similarly, if I want title case, so I'll type in A1 dot title. Right, so I have successfully changed all of these words to title case. So J is capital, D is capital. So over here, since apostrophe is taken as another character, that is why T is also given capital. And then we have S as capital and P as capital. Right, so these were some basic functions when it came to strings. Now let's go ahead and work with some non-primitive data structures in Python. So the main non-primitive data structures in Python are tuple, list, dictionary, and set. So when it comes to all of these data structures, so you can store multiple elements inside one data structure. So till now we've worked with only variables, and when it came to variables, we could store only one value in one variable. Now let's say if you go to a music concert and you'd have to store the names of all the people attending the music concert, and the strength of the audience would be around 10,000. So to store the names, you would require 10,000 variables. Now that's a lot of variables, and you'd have to manually store all of these names inside 10,000 variables. So that's a humongous task, and that's a tiresome task. So this is where you would need these data structures, where you can store multiple elements inside one single data structure. So we'll start off with the first data structure, which is basically tuple. So when it comes to tuple, it is an ordered collection of elements enclosed within round braces. So we have Curious Jason over here, and he'll be coming in between to give us some pointers. So Curious Jason tells us that tuples are immutable. Now, what does he mean when he states that tuples are immutable? So basically, when you go ahead and create a tuple, so let's say you add 5 elements inside one tuple. Now, you can't change or modify the tuple which you have created. So that would basically mean that, let's say if you have 5 elements, then you can't change the value of the second element or the third element, or you can't add another element inside the tuple which you have already created. So this is basically the immutability nature of tuples. And this is how you can create a tuple. So you will use these round braces over here, and inside these you will given the values, right? So as you see, tuple is actually a heterogeneous data structure. So over here you are storing a numerical value, a character value, and a Boolean value. Right, so let's go to Jupyter Notebook and work with tuples. So let me create a tuple. So I'll name the tuple as tup1, and I'll give in the values. Right, so this is our tuple tup1. Let's see how can we access individual elements from this tuple. So accessing elements from tuple is the same as accessing elements from a string. So all you do is, given the name of the tuple, which is tup1, you given this square braces, and then if you want to extract the first element, which is basically present at index 0, you will type in 0 over here, and you have extracted the first element, which is 1. Similarly, if you want to extract the last element, you have to type in -1, and you have extracted the last element, which is 23. And if you want to extract a sequence of elements, so let's say I want A, true, and B. So this would be from index number 1 going on till index number 4, because we'd want 1, 2, and 3. So I'll type in 1, 4, right? So I've extracted A, true, and B, right? So this is how you can extract individual elements from a tuple. Now, as I've told you, a tuple is immutable. So let me go ahead and try to change the value which is present inside a tuple. So I'll type in tup1, and let me change the value which is present at 0th index, and I'll change it to, let's say, 100. And we get an error over here. So the error is tuple object does not support item assignment, and that is because tuples are immutable. Now let me try to add a new value inside this. So we've got 1, 2, 3, 4, 5. So that would mean this is index number 4. So let me try to add something at index number 5. I'll type in Harry Potter. Again, we get the same error. So tuple object does not support item assignment because it is immutable. Now we'll head on to the next data structure, which is a list. So lists and tuples are quite similar. The only difference is lists are mutable while tuples are immutable. Now, what do I mean when I say lists are mutable? So this means that lists can be changed once they are created. So if there are 5 elements in a list, so the second element or the third element can be modified. And again, since I've said that there are 5 elements, so another 5 elements can be added inside this list. So this is the basic difference between lists and tuples. And this is how you can create a list. So you'll basically given square braces, and you'll given all of the values inside the square braces. So let's head on to Jupyter Notebook and work with lists. So I'll type in L1, and I'll give in some values over here. And then I'll print it out. Right, so this is a list over here. And accessing elements from the list is same as tuple. So if I want to access the first element, I'll type in L1, I'll give in square braces, and then I'll give in 0. So I have extracted the first element. Now let's go ahead and access a sequence of elements. So I want to access these 3 elements over here, true, 2, and b. So this is index number 2 and then going on till index number 5. So L1 and 2 colon 5. Alright, so true, 2, and b. So we have successfully extracted these 3 sequence of elements. Now let me go ahead and actually change the values inside this list. So I'll change this value 1 to 100. So I'll type in L1 0 and I'll assign the value of 100. Now let me print out L1. So as you see, initially the value of this element was 1 and then we have changed the value to 100. Now let's say I want to add a couple more elements inside this list. So I'll type in L1.append and I'll add an element and name it to be, let's say, sword. And then let me print out L1. Right, so I've successfully added a new element. So now I can actually add a list inside a list. So let me again use the append function over here. And then I'll add a list inside this. So I'll type in 1, 2, 3, 4, and 5. So let me again look at L1. Right, so I successfully added this new list inside this list. Now we can also go ahead and remove these elements. So to remove the last element, we've got the pop function. So I'll type in L1.pop. So as we see, this last element has been popped out. Now again, let me type in L1.pop and let's see what will be popped out. Right, so this time this element sword has been popped out. Now let me have a look at the modified list. Right, so we are only left with these values because sword and this list has been popped out. So this is how we can work with lists. Now let's head on to the next data structure, which is a dictionary. So dictionary is actually quite different than a list and a tuple because it consists of key value pairs. And these are actually unordered collection of key value pairs which are enclosed within curly braces. And again, dictionaries are mutable. So this is how you can create a dictionary. So you'll put in curly braces over here. So first you'll put in the key. So over here the key is apple and then you'll give in a colon and then you'll give in the value. So for the key apple, the value is 10. And then you'll give in the next key value pair. So after comma, the next key value pair is orange 20. So orange is the key and 20 is the value. So let's go ahead and create our own dictionary. So let me create the dictionary over here. I'll type in D1 and then I'll give in these curly braces over here. So I'll just give in some names of fruits. So let's say the first key is mango and the price of the fruit would be the value. So mango costs 45 bucks. And then we've got apple. So let's say apples cost us 30. And then we've got orange. And then orange costs around 77. After that, we've got guava. And then this would cost around 125. Now let me print it out. So this is our dictionary. Now what we have is key value pairs. So if I want to access only the keys, then we have the keys function. So I'll type in d1.keys. So I'll give in the name of the dictionary and then I'll follow it up with the keys function. d1.keys, right? So I have extracted all of the keys, which are mango, apple, orange, and guava. Similarly, if I want to extract all of the values, which are basically the price of all of these fruits, I'll type in d1.values and I have extracted the prices of all of these fruits. Now let's go ahead and modify some of these elements. So I want to change the cost of mango. So I'll type in D1 and then I'll give in the name of key. So the name of the key is mango and the cost would be 100. And then I'll type in D1. So initially the cost of mango was 45 and then I've altered it to be 100. So this is how we can work with dictionaries. And then we've got the final data structure, which is a set. So a set is an unordered and unindexed collection of elements enclosed within curly braces. So what do I mean by unindexed? So when I say unindexed, this basically means that sets don't have any index to it. So we can't really access the elements with respect to their indexing. And also another thing to be noted is sets do not allow duplicate values. So let's say if you add a value 10, then you cannot add the same value again. So it will take the value only once. And this is how you can create a set So you'll have curly braces over here, and then you'll give in all of the elements inside it. So let me create my final data structure over here. So I'll type in 1, A, and then I'll give in a floating point value, let's say 3.78. Let me print out the set. So this is our set over here. Now what I'll do is I'll copy this and let me try to add some duplicate values. So I'll add 1 all of these times, and then I'll also add A. Now let me print out S1 and then see what value do I get. So we see that duplicates are not allowed. 1, even though I have given around 5 or 6 times, it has been taken only once. And A I've given 2 times, but then again it comes only once. So obviously set does not allow any duplicates inside it. Now let me go ahead and add some new values inside the set. So I'll type in s1.add hello world. Right, so I've added this new element. And if I want to add more than one element at a single time, then we've got this update method. So I'll type in s1.update and I'll give in a list of values. So I'll type in, let's say, Sparta, and then I'll type in 123. Then I'll give in, let's say, 3 plus 9j. Then let me print out s1. Right, so all of these elements have been added. Again, you see that the order of these elements is not preserved. It is random, right? So 3 plus 9j comes over here, and then we've got 1, 123, right? So the random is not at all preserved. Right, so we are done with the basic data structures in Python, which were basically tuple, list, dictionary, and set. So now we'll head on to the flow control statements. And in flow control statements, we'll start with the if statement. So in real world, you will come across a lot of situations where you'd have to make a decision on the basis of a condition. So let's say if this happens, then you'd have to perform a set of actions. Else, you'd have to perform a different set of actions. So let's take this example to understand this better. So let's say it's raining and you'd want to play football. So if it's raining, then you can't do anything and you just have to sit inside. Else, so if it is actually not raining, then you can go out and play football. So these are some of the real world situations which can actually be represented in programming with the help of if-else statement. So let's go to Jupyter Notebook and work with if-else. So here I'll create 2 variables. So I'll give in the value of 10 to A and I'll give in the value of 20 to B. And then let me check if the value of B is actually greater than the value of A. So if B is greater than A, then I want to print out B is greater than A. So since this condition has been evaluated to true, that is 20 is greater than 10, and since this is true, this statement has been executed. So we get B is greater than A. Now let me actually flip it. So I want to check if A is greater than B, and if this evaluates to true, I want to print out A is greater than B. So we don't get any result, and that is because this condition has been evaluated to false. And since this condition has been evaluated to false, this statement has been skipped. So this is where else clause comes in. So let me use else over here. Now I'll type in if A is greater than B, then I'd want to print out A is greater than B. Else I'd want to print out B is greater than A. Right? So here the first condition evaluates to false, and that is why it is kept. And then we given the else clause, and this condition is printed, B is greater than A. Now let's say if we have multiple conditions. So if we have 3 numbers and we want to check which is the greatest out of those 3 numbers. So this is where we would need if, else. So let me actually assign the values again. So I'll assign 10 to A, 20 to B, and I'll also assign 30 to C. So now I'd want to check if A is greater than B and A is greater than C. So I'll type in if A is greater than B and A is greater than C. And if this evaluates to true, I want to print out A is the greatest and this evaluates to false, then I'll type in elif, which stands for else if. So I'll give in the next set of conditions over here. So I'll type in B is greater than A and B is greater than C. And here I want to print out B is the greatest. So B is the greatest. And again, if this evaluates to false, I'll finally put in else and I want to print out C is the greatest. So here the final result is C is the greatest. Now let's understand this whole thing properly. So first we come to the if statement and then we check if A is greater than B and A is greater than C. That is 10 greater than 20 and 10 greater than 30. So both of these are false, and false would evaluate to false, and that is why we'll skip this statement over here. Then we'll come to else if, and we are checking if B is greater than A. So 20 is greater than 10, which is true. Then we'll check is 20 greater than 30, which is actually false. So true and false will evaluate to false, and again this is skipped. And finally we'll come to else and we'll print out C is the greatest. So this is how we can work with if else. Now let's use the if statement with a tuple. So let me create a tuple over here. So tup1, and let me give some values. A, B and C. So I have created this tuple. Now after this, I want to check if the element A is present in this tuple. So if A and tup1, then I'd want to print out A is present. Alright, so since this condition is evaluated to true, that is, the element A is actually present in this tuple, and that is why we print this out. Now let me just check if the character S is present in this, and if it is present, I want to print out S is present. So this condition evaluates to false and nothing is printed out. Now similarly, let me go ahead and work with if and list. So if with list, and then I'll go ahead and create a list. So L1, and then I'll give in a bunch of values inside this. So 10, 20, 30, 40, and 50. Now I want to check if the first element in this list is actually 10, and if the value is equal to 10, then I want to change it to 100. So if L1 of index 0 is actually equal to 10, then I'd want to change this to 100, and then I'll finally print out this list. Right, so initially the first element in this list was 10. With the help of the if statement, I've changed it to 100. Now similarly, let me go ahead and work with if and dictionary. Dictionary with if. I'll create a dictionary, D1, and then I'll give in a bunch of key value pairs over here. So I'll type in the name of the fruit, which is mango, and then I'll assign the value, which is 10. And then the next fruit would be apple. And then the cost would be 20. And then the final fruit would be banana. And then the cost would be 30. Alright, so now I want to check if the value of mango is 10, and if it is equal to 10, then I'd want to add 100 more to this value. So if D1 of mango is actually equal to 10, then I'd want to add 10 more to this. So D1 of mango would be equal to D1 of mango plus 100, and then I'll print out D1 over here. Right, so initially the cost of mango was 10, then using the if statement, I have incremented the value to 110. Right guys, so this is how we can work with the if statement. Now let's head on to looping statements. So looping statements are basically used to repeat a task multiple times. So let's understand looping statements with this example. So you have a bucket and you'd want to completely fill it up with a mug of water. So the condition is, while the bucket is not full, you will keep on adding a mug of water to it until it is full. So here the repetition task is, you will have a mug of water and you will keep on pouring that into the bucket until it is full. So you're repeating a task until the final condition is met. And this is how the while loop works. So, and in looping statements, you basically have while and for. So we'll start with the while loop. So let's go to Jupyter Notebook again. So let me initialize a variable first. So I'll type in I equals 1 and then I'll use the while loop. So the condition would be while I is less than or equal to 10, I'd have to print out I. Now after this is done, I have to increment the value of I with 1. So let me print this out. So this is the result. Now let's understand this better. So initially I have a variable I and I have initialized it with the value 1. Then I'll start this while loop. So over here, I'll check if I is less than or equal to 10 and initially I's value is equal to 1. So is 1 less than or equal to 10? So it is true. And since this is evaluated to true, I'll come inside the while loop and I'll print out the value of I, which is 1. Then I'll increment the value of I. So 1 plus 1 would become 2. Again, I'll check if 2 is less than or equal to 10. And since 2 is less than or equal to 10, I'll again come inside the while loop and then I'll print out 2. Then again, I is incremented, I's value would become 3. So I'll check if 3 is less than or equal to 10. Again, it evaluates to true. I'll print out 3. And then this loop repeats itself until I's value becomes equal to 10. Right? So the final value would become equal to 10. And then I's value would become 11. So here I'll check if 11 is less than or equal to 10. And that condition would fail. And when the condition finally fails, we will come out of the loop. So this is how the while loop works. So now using the while loop, I want to print the 2 table. That is 2 cross 1 equals 2, 2 cross 2 equals 4 and 2 cross 3 equals 6 and so on. So I'll have the first variable initialized, which is I equals 1. And then I'll type in n equals 2. So I have my variables initialized over here. Now I'll start the while loop and this loop will go on till I's value is less than or equal to 10. Now inside this, I want to print out. So n and then cross I is equal to, I'll just put in n cross I. So let me print this out. So after this, I have to actually give in one more condition, which is I equals I plus 1. So if I don't increment the value of I, then it will go into an infinite loop. So I'll hit run. So we have this 2 table over here. So let me explain this properly. So initially I's value is 1. So I'll check if 1 is less than or equal to 10, which is true. So I'll come inside this and I'll print out 2 cross 1 is equal to 2. And then I'll increment the value of I, which is 2. Then I'll check if 2 is less than or equal to 10, which is again true. Then I'll come inside and then I'll print out 2 cross 2 is equal to 4. Then again, I's value is incremented. It becomes 3. Then I'll check if 3 is less than or equal to 10. And since this is true, I'll again come inside and then I'll print out 3 cross 2 is equal to 6. And this goes on until the I's value is equal to 10. And then I'll print out 2 cross 10 is equal to 20. And when we increment I's value again, it becomes 11. So is 11 less than or equal to 10? Well, it evaluates to false because 11 is greater than 10. Right? So this is where the loop ends and we have the final value, which is 2 cross 10 equals 20. Now let's use while loop with a list. So I'll basically create a list with a bunch of elements inside it, and with the help of while loop, I want to add 100 more to each of the value inside the list. So let me create the list over here, L1, and I'll add in a bunch of values over here. So 1, 2, 3, 4, and 5. So the list has been created now. Now I'll go ahead and initialize the variable I to be equal to 0. So this is also done, and then I'll start the while loop. So inside the while loop, I will basically check till I is less than. So let me remove these brackets over here. So while I is less than length of L1. So length of L1 would be 1, 2, 3, 4, and 5. So I would go from 0 to 4. And then I basically want to increment each element inside this list. So L1 of I would be equal to L1 of I plus 100. And then I also have to increment the value of I. So I would become I plus 1. And then finally, I'll print out the value of L1. right? So initially the values in the list were 1, 2, 3, 4 and 5, and after running the loop the values became 101, 102, 103, 104 and 105. So let's understand this loop. So initially value of I was 0 and I am checking if 0 is less than 5, which is true. So I'll come inside and I'll assign L1 of 0 to be equal to L1 of 0 plus 100. So it'll be 100 plus 1, which is equal to 101, right? So 1 would become 101 and then I's value is incremented by 1. So I's value is 1 now, and then again I'll check if I is less than 5, which is true. So I'll come inside and then I'll assign L1 of 1 is equal to L1 of 1 plus 100. So I'm adding 100 to this element 2. So it becomes 102. And similarly, this will go on till index number 4. And when it becomes 5, so 5 is not less than 5, and that is when we'll come out of this loop. So this is how we can work with the while loop. Now we'll head on to the for loop. So for loop is used to iterate over a sequence. So that sequence could be either tuple, list, dictionary, set, or even a string. And this is the syntax of for loop. So for value in the sequence, and then we'll give out the body. Now this might seem a bit vague or difficult to understand. So let's directly head to Jupyter Notebook and go ahead with the code. So let me start off by creating a list. So I'll type in L1 equals, and then I'll give in a bunch of colors inside this, which would be equal to blue, green, and then I'll just assign red to it. Now once this is done, let me use the for loop and iterate over this list. So for I in L1, I'll just print out I. Right, so I have printed out each individual element of this list. So for I in L1, right? So when I say I, this value of I initially would be blue. So for I in L1, so L1 has these three elements, blue, green, and red. And initially I's value would be blue. So I'll come inside this list and I'll print out blue. And now it's incremented and I'll go to the next element in the sequence, which is green. So I will have green inside it. I'll come in and I'll print out green. And then I'll go ahead to the final element inside the list, which is red. So again, I'll come inside and I'll print out red. So this is how the for loop works. Now we can actually create nested for loop. So that would mean a for loop inside a for loop. So for this, let me create two lists and two separate for loops. So I'll create, let's say, color, and I'll assign some values. So the values are green, yellow, and pink. And then I'll also add another list, and then I'll name the list to be equal to item. And I'll add a bunch of items to it. So let's say the first item is chair, the second item is book, and the third item is phone. Now I'll start a for loop. So for I in color, I'll add another for loop over here. So for J in item, I will print out I, J. And this is what we have. So let's understand this. So we'll start with the outer for loop, which goes through this list over here, which is color. So for I in color, so initially I's value would be green. Now when the I's value is green, we'll come inside the for loop and we'll start the inner loop for J in item. So initially J's value is chair. So I'll print out green chair. Now again, I'll go back and increment the value of J. So then we have book inside J. So I'll print out green book. Then again, J's value is incremented. It becomes phone. I'll print out green phone, right? So now the inner loop is also done. I'll go back to the outer loop and then I'll increment green to yellow. So now I's value is yellow. So again, I'll come inside the loop and then I'll print out yellow chair, yellow book, and yellow phone. Again, I'll go back to the outer loop and then the value of I is pink. Then I'll come inside and then I'll print pink chair, pink book, and pink phone. So this is how you can work with nested loops. So now that we're done with the flow control statements, we'll head on to functions. So what exactly is a function? To simplify this, what we are basically doing is we are taking in a bunch of code, putting it in a simple module, and we can invoke it whenever we want to perform a specific task. So let's take this example of an ATM. So over here, depositing money inside the ATM would be one function, withdrawing money would be another function, and checking balance would be another function. Now, let's say if you want to deposit money and you would have to write around 100 lines of code to deposit money. And let's say if you want to deposit money around 100 times, then you'd have to write this 100 lines of code 100 times. Now, instead of this, it would be wonderful if we just had one deposit function and all we did was invoke this deposit function and we could deposit our money happily, right? So this is where functions come in. Similarly, when it comes to the withdraw function, we'll just have to add one function where we'll write in all of the bunch of code only once, and whenever we want to withdraw money, we'll just invoke this function. Similarly, whenever we want to check the balance, I'll just invoke the balance function and I can happily check the balance. So let's go to Jupyter Notebook and work with functions. So to create a function in Python, we'll be using the def method, and then after the ef, we'll give the name of the function. So I'll just create a very simple function and I'll name that function to be hello. And this needs to be followed with a parenthesis. So after this, I'll give in a colon and then I'll give in the body of this function. So this function just prints out hello world. So hello world, right? Now, if I have to invoke this function, I just have to type in hello with these parentheses. Alright, so if I want to print out hello world, all I have to do is copy this, paste it over here. So all I have to do is invoke this function and then I can happily print hello world how many times I want. Now after this, what I'll do is I will create a function where I'm taking an input value and adding 10 more to it. So I'll type def and I'll name the function as add 10, and this basically takes in a parameter value. So if you see this previous example, you see that I did not pass anything inside this parenthesis, but we can actually pass in a value inside the parenthesis, and I'm passing in x, which basically could be any arbitrary value. And I'll put in a colon over here. Now what this does is this returns 10 plus x. So it takes in x, adds in 10 to it, and then returns the final value. This is the function. So let me invoke this. Let me pass in 5 inside this function. So when I pass in 5, it will add 10 to it and it will return the final value, which is 15. Similarly, let's say I'll add an 100 inside this. So it will return a value of 110. So this was another example. Now going ahead, we'll check if a value is even or odd using a function. So I'll type def and then I'll just name this function as odd even. And again, this takes in a value. So I'll use the if condition and I'll check if x, and I'll check if x %2 is double equal to 0. So whatever input value is given, I will divide it with 2, and if the input is equal to 0, then I will just print out x is even, else I will print out x is odd. So I have created this function. Now let me invoke it and pass in a value. So I'll pass in 9 and let's see what is the result, right? So this function tells us that 9 is an odd number. Let me again pass in a number inside this. So I'll pass in 4. So this time this function tells us that 4 is even, right? So this is how we can create functions with Python. Now we'll head on to a major part in Python, which is object-oriented programming. Now when you actually look around you, what do you see? You are surrounded with objects, aren't you, right? So you might have a laptop in front of you, you have a phone in front of you, you have a bike, you have a dog. So all of these are real world objects. And if you want to represent these real world objects in programming paradigm, then you would need something known as object-oriented programming, right? So simply put, you have all of these real world objects around you. And if you want to represent all of these real world objects in programming paradigm, that is where you'll go ahead and use object-oriented programming. So now when it comes to object-oriented programming, you basically need to understand two particular concepts, which are basically classes and objects. So as it is stated over here, a class is basically a template or a blueprint for real world entities. Now, what do I mean by it? So when I say template, a template would comprise of two things. One is properties of the object and the next is behavior of the object. So let's take a phone. Now a phone would have certain properties associated with it and it will also have certain behavior associated with it. Now the properties of a phone could be its color, its cost and its battery life. So what is the color of the phone, how much does it cost and how long does the battery last? So these are some properties which are associated with every single phone that everyone has. And then all of the phones have certain behavior common to all of them. So you can make calls with a phone, you can watch videos in a phone, and you can also play games in a phone. Right, so these are the properties and behavior associated with a phone. Now a class basically combines these properties and behavior in one single template. So that is a class. Now let's understand what exactly is a object. So objects are basically specific instances of a class. So as I've told you, a class is a general template. And when you want a specific instance of that general template, that is when you have an object. So when I say phone, that phone would be your class. And the objects of that phone would be Apple, Motorola, and Samsung, right? So Apple, Motorola, and Samsung would have the general template of a phone. So they will have the general properties and they will also have the general behavior. So if these objects are of the same phone class, then you'll get those same properties, which is basically all of these phones would have color associated with them, cost associated with them, and then you will also have battery life associated with them. And when it comes to behavior, these three phones would have those functionalities common, right? So in all of these three phones, you can make phone calls, you can play games, and you can also watch videos. So this is what I mean when I say objects are specific instances of a class. All right. So now that we know what exactly is OOPS and what exactly are classes and objects, let's go ahead and perform some object-oriented programming. So let's go ahead and create our first class. And to create a class, we will have to use the class keyword and then we'll give in the name of the class. And by convention, the first letter of the name of the class needs to be capital. So I'll type in capital P and then I'll follow it up with HONE. So it is phone. And then inside this, I will give in the properties and the behavior of the class. So a phone, basically with the help of a phone, you can make phone calls and you can play games. So I'll start off by creating methods. So the first method is to make a phone call. So I will name this method as make call. And then this will have something known as self. So this self basically means that this method belongs to the instance which invokes it. So this might be a bit confusing, but once we actually create an instance of this class, it will become very clear to you. So we have created this method, and when someone invokes this method, I'll just type in making a phone call. And then I'll give in the second method, which is play game. Again, this will have this self attribute. So again, the self attribute basically stands for whichever instance invokes this method, it belongs to that. All right. So I will print out playing game. All right. So I have created this class, which is basically the general template of a phone. Now I will go ahead and create the object. So to create an object, I will type in P1, which is basically the instance or the object of this class. And I will have to type in the name of the class followed by the parenthesis. And I have successfully created the instance of this phone class. Now, if I have to invoke these methods from this object, so I will type in the name of the instance. I'll use the dot operator and then I can directly give the name of the method in this class. So if I want to make a phone call, I just have to type in p1.makeCall. So p1 is the name of the instance. After that, I'll give in the dot operator and then I'll give in the name of the method inside this class, which is makeCall. Right? So now I have successfully invoked this method of this class. So P1 is an instance of this class and I'm able to access this method with the help of this instance. Similarly, I'll type in P1.playGame. Right. So now I have started playing game. right? So this is how we can create instances. Now let me actually go ahead and add some parameters to the methods inside this. So again, I'll create a new class, or basically I'm modifying this class. I'm not creating a new class. So I'll type in class. So this will be phone, and then I'll create a new method, and this will be basically to add the color of the phone. So I'll type in add color. So now every method inside the class needs to have this self attribute, and then after that I'll give in another parameter which is basically color, and inside this I will set self dot color equals color. Now you have to understand that this self dot color and this color are actually different. So this color is the value when someone gives while invoking this method, while this self dot color is the inbuilt attribute inside this class of that particular instance. So if this seems confusing, let me repeat it again. So this color which you see, it is basically the parameter or the value when someone gives in while invoking this method. And the self dot color is the value which is being assigned to the color attribute of the instance which is being invoked. So let me actually go through and this will become very clear to you, right? So I have created this method, and then similarly, I'll add another method called as add cost. So again, this will have two parameters. First is self, and then next would be cost. And then I'll type in self dot cost equals cost. So this is also done. So going ahead, I will create one more method where I'd have to show the color and show the cost, right? So till now I have only taken the color from the user and taken the cost from the user. Now I also have to print it out. So I'll create a new method called as show color. This would have self, and this would basically return the color. So self dot color, and after this I would have show cost. Again, the parameter would be self, and this would be returning the cost. So that would be self dot cost. All right. And then I'll again create those two basic functions which are basically making a phone call and playing a game. So definition of make call, this would be self. I am just printing out making a phone call. After this, I'd have to create the final method which is play game. Again, this will have the self attribute, and then I'll print out playing game. Right, so I have successfully created this class. Now I'll go ahead and create an instance of this class. So I'll type in p2 equals phone. Now let me go ahead and add the color and cost of this phone. So I'll type in p2 dot color. Now let me go ahead and add the color and cost of this phone. So I'll type in p2 dot color, and now let me go ahead and add the color and cost to this phone. So I'll type in p2 dot add color, and the color of this phone is, let's say, blue. Now similarly, I also want to add the cost of this phone. So p2 dot add cost, and the cost of this phone is, let's say, $200. Right. Now I have assigned the color and the cost. Now let me show out the color and the cost. So I'll type in p2 dot show color. So we see that the color of the phone is blue. Now let me also print out the cost. So p2 dot show cost. So we see that the cost of the phone is 200. All right. So now what you see is this self dot cost equals cost, or self dot color equals color. So this color is basically this value which we are passing in when we are invoking the function, right? So this blue is going over here, and this is being assigned to the attribute color of this class phone. So to make it more clear, let me actually create one more instance of this class, and let me add the color to that. So p3 equals phone, So I have created this, and then I'll type in p3 dot add color, and the color of this phone would be red. Now let me show this out, p3 dot show color. So the color of this instance of the phone p3 is red. Now let me type out p2 dot show color, which is blue. All right. So this self, what you see, this basically denotes the instance which is invoking the method, right? So over here, when we invoke the add color with the p2 instance, this self attribute was with respect to the p2 instance. And similarly over here, when we were invoking the add color with respect to the p3 instance, the self attribute was of the p3 instance. This is how we can add parameters to our methods and invoke them through our objects. Now let's head on to an important concept in object-oriented programming, which is inheritance. So what comes to your mind when you hear the word inheritance? So simply put, inheritance basically means that when something acquires the properties of someone else's or something else's, right? So let's say you are inheriting your features from your father, or you are inheriting the land or the property from your ancestors, right? So either it could be materialistic inheritance, or it could be the features or the looks from your parents, right? So inheritance is basically acquiring properties from another person or another thing. And when it comes to object-oriented programming, it pretty much means the same thing. So over here, you will have two classes or more than two classes. One class inherits the features or the properties of another class. And that is pretty much the concept of inheritance in object-oriented programming. So let's again head back to Jupyter Notebook and start with inheritance. So to show inheritance over here, I'll just create an extension of the original class. So what I'll do is I will create a new class, and I'll name this class as iPhone, and this iPhone will be inheriting from the base class phone which we had created earlier, right? So this is the base class, and this new class iPhone would be inheriting from this base class. Now this would have one extra method, which is cure cancer. Now, as you know, iPhone is very famous, and it's famous because it can actually cure cancer. So that is why it costs so much. So that is amazing, isn't it? So cure cancer, I'll give in the self attribute, and then I'll just print out I can cure cancer. So I have created this new class. Now let me create an instance of this. So IP1 equals iPhone. So I have created the instance. Now let me go ahead and invoke the methods. Now as you can see, this class or this instance of the class has the methods add color and add cost. Now even though I have not explicitly stated these methods inside this class, they are still a part of this class because it is inheriting from the base class, which is Python. And since these two methods are part of the base class, I can automatically invoke these two classes. So let me assign a color to this phone. So the color of iPhone is gray. Now I'll go ahead and also set in cost. So IP1 dot add cost, and the cost of iPhone would be, let's say, $899. And then let me invoke the method which is only there in the iPhone class. So IP1 dot cure cancer. All right, so I can cure cancer, right? So this is how inheritance works in Python. Right, so we're done with object-oriented programming as well. Now we'll go ahead and work with some packages in Python. So we'll start off with the NumPy package. So NumPy basically stands for numerical Python and is the core library for numeric and scientific computing. So that's too much of information. So simply put, NumPy basically has a multi-dimensional array. Now to process those multi-dimensional arrays, you have certain functions and you have certain operations pre-built in the NumPy package. And that is how you can work with these NumPy multi-dimensional arrays. So you can perform all sorts of numerical and scientific operations on this NumPy array. So let's go to Jupyter Notebook and work with this very famous package called as NumPy. So to start working with the NumPy library, you'd have to first import it. So you'll type in import NumPy as NP. Now this is just an alias so that I can keep invoking this package whenever I need, right? So NP is the alias. Now before you can actually go ahead and work with this library, you'd have to install it. So to install it, since we are working with Anaconda, let me open this up, right? So to install this, you would have to type in pip install NumPy, right? But then again, if you're working with Anaconda, NumPy, Pandas, and Matplotlib, all of these come pre-installed in Anaconda. But then again, if you're working with PyCharm or if you're working with any other Python IDE, then you'd have to manually install NumPy. All right. So NumPy is already installed and I have successfully imported NumPy into my system. Now it's time to go ahead and create my first multi-dimensional array. So once you install NumPy and you invoke the library, you have to create a NumPy array. And you can create both a single dimensional array as well as a multi-dimensional array in NumPy. So to create a NumPy array, you just have to type in np.array. So as I've already told you, np is basically the alias for NumPy. So you'll type in np.array, and this basically takes in a list of values or a list of lists. So to create a single dimensional array, what you'll do is you will pass in a list inside this np.array, and this will give you a NumPy array. Similarly, to create a multi-dimensional array, you will pass in a list of lists, right? So this is one list, and inside this you've given two lists, right? So the first list comprises of the elements 10, 20, 30, and 40. And the second list comprises of the elements 40, 30, 20, and 10. So let's go ahead and create our first NumPy arrays. So I'll create a single dimensional NumPy array first. So let me just add in this comment, single dimensional NumPy array. So as I've already told you, to create a NumPy array, we'd have to type in np.array, and inside this I'll give in a list of values. So let's say the list of values are 10, 20, 30, 40, and 50. So I'll type in 40 over here and 50 over here, and I'll store this in a new variable and name that variable as n1. Now let me print out n1 over here. So this is our NumPy array. Now let me also check the type to be sure. So type of n1, and this shows us that this is a NumPy nd array or n dimensional array. Now let's go ahead and create a multi-dimensional array. So I'll type in multi-dimensional. So over here I'll be storing this value in n2. So np.array. You have to keep in mind that you pass in a list of lists over here. So I'll create one list, and inside this I'll create the first sub list, and the values would be 10, 20, 30, and then I'll create another sub list. The values I'm giving are 30, 20, and 10. Now let me print out n2. So this is my multi-dimensional array, which comprises of 2 rows and 3 columns. So the first row comprises of 10, 20, and 30, and the second row comprises of 30, 20, and 10. Now again, let me check the type of this. So type of n2. So type of n2 is again NumPy n-dimensional array. And this is how we can create NumPy arrays in Python. So guys, this is just the starting, and you can do a lot of stuff with these NumPy arrays. All right. Now we'll go ahead and see how can we initialize a NumPy array with all zeros. So let's say if we want to create a simple row array which comprises of 2 zeros, then we have this zeros method. So np.zeros, you are invoking this zeros method from the NumPy package. So when you type in np.zeros, and then you have to give in the dimensions of it. So the dimensions of the NumPy array are 1 cross 2, and then you'll get this. Similarly, if you want to create a 5 cross 5 NumPy array which comprises of only zeros, then you just type in np.zeros, and inside that you will give in the values. So let's initialize our NumPy array with zeros over here. I'll type in n1 and then np.zeros. So I want the size of the NumPy array to be 1 cross 2, and then I'll print this out. Right, so I have successfully created my NumPy array of dimensions 1 cross 2, which means 1 row, 2 columns, and the values are just zeros. Now similarly, I'll create another NumPy array. So n1 equals np.zeros, and I want this to be a, let's say 6 cross 6 NumPy array, which comprise of only zeros. Again, let me print in the value of n1. Right, so I have created this NumPy array, which is of dimension 6 cross 6, and it comprises of only zeros. Now, similarly, let's say if you want to initialize a NumPy array with the same number. So this is where we have the full method from NumPy. So we have to type in np.full, and this takes in two parameters. So the first parameter is the dimension of the NumPy array, and the second parameter is the value with which you'd want to fill up your NumPy array. So over here, I am creating a NumPy array of dimension 2 cross 2, and the value which I'm filling it up with is number 10. So let's create this. So I'll name this as n1 again, and I'll type in np.full. I'll give in the dimension. I want to create a 3 cross 3 NumPy array, and I want to fill it up with the number 7. And then let me print out n1 over here. So we have created this 3 cross 3 NumPy array where all of the elements are just 7. Again, we can initialize our NumPy array in a different way. So if you want to initialize our NumPy array with a particular range in mind. So let's say I want my NumPy array to be filled with all of the values from 10 to 20. So basically the interval is 1, or the skip value is 1. So I'll have 10, 11, 12, 13, 14, 15 going on till 19, right? So I want to fill up my NumPy array with a particular range. So this is how I can do it. Now, another form is I basically give a skip value. So when we don't give the third parameter, a range automatically takes the skip parameter as 1. So when we look at the second example over here, the range is basically from 10 to 50, but the skip value is 5. So your first number would become 10, second number is 15, 20, and then this goes on till 45. So you have to keep in mind that this last number which you see, this is exclusive. It is not inclusive. So when you add 5 more to 45, if it is less than 50, only then you'll get the last value. If it is equal to or greater than 50, then you will not get that value. All right, so let's go ahead and initialize our NumPy array with a particular range. So again, I'll type in n1. So this would be np.aRange, and inside this, I will basically give in the range with which I want this NumPy array to be filled with. So I want this to be filled starting from 1 going on till 11. And then let me print this out. Right, so this NumPy array, the values start at 1 and go on till 10. Now similarly, let me create another NumPy array with a specific skip value. So n1 equals np.aRange, and let's say I want the range to be from 100 and going on till 300, and I want the skip value to be equal to 50. So let me just print out n1 now. Right, so this is my NumPy array. So 100 is the starting value, 250 is the last value, skip value is 50. So that is why I get 100, 150, 200 and 250. And when you add 50 more to 250, it becomes 300. And since 300 is not inclusive, that is why you will not have that number over there. Now let's see how can we initialize our NumPy array with random numbers. So if you want to initialize our NumPy array with random integers, then we've got this randint sub method from the random method. So again, you will set the range of the numbers from which you want the random numbers over here, right? So the range of the numbers is 1 and 100. So starting from 1 going on till 100, you will choose 5 random numbers. So let's go to Jupyter Notebook and work with this. So n1 equals np.random.randint, and then inside this, let's say I want 10 random values, and the values would be coming in the range between 100 and 200. So I want 10 random values. Let me print out n1. Right, so these are the 10 random values between 100 and 200. So that was how we could initialize our NumPy array in a lot of different ways. Now let's see how can we check the shape of our NumPy array. So checking the shape of our NumPy array would basically give the number of rows and number of columns present in the NumPy array. So all you have to do is create a NumPy array first and then use this shape method. So when you use the shape method, this will tell you the number of rows and number of columns present in this NumPy array. Now, with the help of this shape method, you can actually change the shape of your NumPy array. So initially when you are initializing it, this NumPy array had 2 rows and 3 columns. But with the help of this shape method, you can change it to 3 rows and 2 columns. So let's go to Jupyter Notebook and let's see this visually. So again, n1, and let me create a NumPy array over here, np.array. Let me give in some values. So let's see 1, 2, 3, and 4. And I actually have to give in a list of lists. So let me cut this and paste inside this. And then my second sub list would be 5, 6, 7, and 8. So I have created n1 over here. Let me check the shape, n1.shape. So the shape of this NumPy array is 2 cross 4. This would mean we have 2 rows and 4 columns in this NumPy array. So that would basically amount to 8. Now, instead of 2 cross 4, I want this NumPy array to be of the shape 4 cross 2. Or in other words, I'd want to have 4 rows and 2 columns. So all I have to do is type in np.shape equals 4 cross 2. So this is done. Now let me print out n1. Right. So initially this was our n1 array, which was of the shape 2 cross 4, and then we reshaped it. Now this is how it looks like. Now, once we know how to initialize our NumPy arrays and how to check the shape of our NumPy arrays, let's go ahead and perform some simple mathematics on top of these NumPy arrays. So we'll look at some basic addition operations. So to add two NumPy arrays, we will just use the sum function from the NumPy package. So over here, I am creating two NumPy arrays, n1 and n2. And when I use the sum method over here, I'll pass in n1 and n2 as a list, right? So this will add all of these individual elements from both of these NumPy arrays. So when you add 40, 30, 20, and 10, it will give you a complete value of 100. Now, you can also set the axis. So if you don't set the axis, then it will add all of the individual elements which are present. So when you set axis to be equal to 0, then it actually does vertical addition, right? So what I mean by vertical addition is it would add the individual elements of each index of this array. So index is 0 over here for n1 and n2. When you add 10 plus 30, it would become 40, and that is what you have. Similarly, when you come to index number 1 and you add 40 plus 20, you get 60, and that is what you have. Now, instead of axis to be equal to 0, when you set the axis to be equal to 1, you basically are doing horizontal addition. That is, you are summing up the values which are present in one individual NumPy array. So here 10 plus 20 becomes 30, and that is what you have. And over here, when you add 30 plus 40, it becomes 70, and that is what we have over here. All right. So let's go to Jupyter Notebook and perform these methods. So again, let me create a new NumPy array. I'll call it A over here. So it will be np.array, and I'll pass in a list of values over here. That would be 10 and 20. And then I'll create another NumPy array. So I'll type in np.array again, and the values inside this would be 30 and 40. So I have successfully created my two NumPy arrays. Now going ahead, let me use the sum method. So it would be np.sum, and inside this, I'll just pass in a comma b, which are basically the NumPy arrays which I've created, and I get a complete value of 100. Now let me go ahead and set the axis. So np.sum, I'll type in a comma b, and then let me set the axis. So I am setting the axis to be equal to 0. And when I set the axis to be equal to 0, as we have already seen, we have vertical addition over here. So 30 plus 10 gives you 40, and 40 plus 20 gives you 60. All right. Now let me go ahead and set the axis to be equal to 1. So I'll pass in a comma b, and I'll set the axis to be equal to 1. Right, so 10 plus 20 becomes 30, and 30 plus 40 becomes 70. So those were some basic addition operations on top of the NumPy arrays. Now let's see how can we join different NumPy arrays. So we've basically got these different methods. We've got vstack, which stands for vertical stack. Then we've got head stack, which stands for horizontal stack. And then we've got column stack. So when it comes to vstack, what we do is we join these NumPy arrays row-wise. So over here we have two NumPy arrays, n1 and n2. And when we use vstack method upon these two NumPy arrays, we are basically joining these two NumPy arrays row-wise. Then we have the head stack function. So when it comes to head stack function, we are combining these two NumPy arrays column-wise. So when I say column-wise, we will take in this first NumPy array and then we'll attach the second NumPy array to the back end of this. Then we have column stack, where we basically take in two single dimensional NumPy arrays and then we stack them column wise to create a two-dimensional array. So as we see over here, we've got two one-dimensional arrays, right? So n1 and n2, and when I use column stack on top of this, I get a two-dimensional array. So over here, these two are stacked column wise. All right. So let me go ahead and use these three functions. So let me create n1 over here. So n1 is equal to np.array, and let me give in the values 10, 20 and 30. Then n2 would be equal to np.array, and the values inside this would be, let's say, 30, 40 and 50. So I have created n1 and n2. Now it's time to use vstack on top of them. So I'll type in np.vstack, and inside this I'll pass in n1 and n2. So let me get the result, right? So I have horizontally, so I have stacked these two columns row wise. Now similarly, instead of vstack, let me use horizontal stack. So I'll type in head stack over here, right? So when I use head stack, I get this. So I'm horizontally stacking these two NumPy arrays. And then finally, let me use np.column stack, and I'll pass in n1 and n2. And I have taken these two individual single dimensional arrays, so 10, 20, 30, 30, 40, 50, and I have stacked them column wise to create a two-dimensional NumPy array. Right, so this brings us to the end of this NumPy module. Now let's go ahead and work with another interesting package in Python, which is Pandas. So Pandas stands for panel data, and it is the core library for data manipulation and data analysis. So as NumPy provides us a multi-dimensional array, similarly, Pandas provides us a multi-dimensional data structure for performing various data manipulation operations. So it provides us both a single dimensional data structure and a multi-dimensional data structure. So as we see over here, the single dimensional data structure is called as the series object, and the multi-dimensional data structure is called as the data frame. And we'll mostly working with the data frames in Python. So data frames become extremely important when it comes to data science operations. So all of the machine learning algorithms which you apply, linear regression, logistic regression, decision tree, and so on. So all of these are applied on data frames. And this is because all of the data sets which you have, all of the CSV files which you have, text files which you have, they can be converted to a data frame in Python, and all of the manipulations can be done on this data frame. All right, so let's start off with the Pandas series object. So as you see over here, a series object is basically a one-dimensional labeled array. So the difference between this and a NumPy array is, when it came to the NumPy array, it was not labeled, but the series object is a one-dimensional labeled array. And this is how you can create a series object. So before we go ahead and create a series object, first we'd have to invoke the Pandas library. So we'll type in import pandas as PD. And PD again over here is just an alias for pandas. So after we invoke pandas, we'll type in pd.series. So over here, you'd have to keep in mind that S is capital. And inside this, we'll pass in a list 1, 2, 3, 4, and 5. And we have created this series object. So let me start off by importing pandas. So I'll type in import pandas as PD. So let me just wait till this package is loaded. So that is done. Now again, since I'm using Anaconda, Pandas comes pre-installed in it. So if you have to manually install Pandas, this is what you have to do. open up Anaconda prompt, and then you'd have to type in pip install pandas. So once you do that, pandas will be installed. Alright, so I have imported the pandas library. Now let me go ahead and create my first series object. So I'll name this object as S1 and I'll type in pd.series, and inside this I'll basically pass in a list. So the list would comprise of the values 10, 20, 30, 40 and 50. So let me print in S1 over here. So this is my series object. So as you see over here, these are the values, and these values are of type integer 64. So integer 64-bit, and these are the labels associated with each of these values. So 0 is the label associated with 10, 1 is the label associated with 20, 2 is the label associated with 30. So you can either call these index values or the labels associated with these numbers. So now you must be thinking that, is there a way that we can actually change the index of a Pandas series? Well, you can. So all you have to do is include this index attribute and then give the labels which you want for these. So as you see over here, initially the labels were 0, 1, 2, 3 and 4. Now after that, you just use this index attribute and then change these values to A, B, C, D and E. Right, so let's perform this. So let me go ahead and add the index to this. So as you see over here, initially the labels were 0, 1, 2, 3 and 4. Now let me go ahead and change the index. So this time I'll set the index to be A, B, C, D and E. Now let me print out S1. So as you see over here, these were the initial index values and I have changed them to these over here. So we saw how to create a series object from a list. Now let's see how can we create a series object from a dictionary. So as you see over here, we'll just pass in this dictionary inside this series object. And one thing to note over here is, if you don't specifically set the index values, the key automatically becomes the index and the values would automatically become the actual values inside the series object. So I'll reiterate it. The keys would become the index values and the values would become the actual values of the series object. So let me create a dictionary over here. So D1, and I'll set the key to be equal to K1 and the value to be 10. Then I'll set the key to be K2 and the value is 20. Then the key is K3 and it is 30. I have created this dictionary. Now again, let me go ahead and create a series out of this. So pd.series, and I'll pass in the dictionary inside this and I'll store this in S1. So let me print out S1 again. Right, so this is my series object which has been created from this dictionary. So as we see over here, the keys have become the index values. So K1, K2, K3 are the index values and 10, 20 and 30 are the actual values of the series object. Right, so that was all about the single dimensional data structure series. Now we'll head on to the most important data structure in Python, which is a data frame. So as it is stated over here, a data frame is basically a two-dimensional labeled data structure and it comprises of rows and columns. So this, what you see, so you've got 3 rows over here and 2 columns over here. And normally when it comes to a data frame, all of the elements inside one column would have the same type. So as you see, this is the name. And the names are normally strings. So Bob is a string, Sam is a string, and Anne is a string, right? And then we've got marks. So marks is another individual column. And when you look at the values inside this marks column, you see that 76, 25, and 92, all of these are integer values, right? So this is how a data frame looks like. And to create a data frame, this is how you can do it. So all you have to do is use the pd.dataframe method, and then you can create it from a dictionary over here, right? So the key becomes the column name over here, and these values become the row values over here. So let me create a data frame. So I'll name this data frame as student, and the first column would actually be the name of the student. So I'll type in student name. So this is actually the key, and then I'll give in the list of values. So the list of values would be Bob, and then we've got Sam. After that, we've got Julia, and then we've got Charles. So these are the student names, and then let's go ahead and give in some marks to these students. So I will create the next key, which would be student marks. So I'll type in student marks over here, and then I'll give in a list of values. So let's say Bob has scored 87 and Sam has scored only 13 marks. Then we've got Julia, who has scored an impressive 99. And then we've got Charles, who has scored an average 67. So I have successfully created this dictionary. Now it's time to create a data frame out of this dictionary. So I'll type in pd.dataframe, and inside this, I just have to pass in this dictionary. I'll click on run, and I have successfully created this data frame where the key over here becomes the column name, and these list of values for a particular key become the row values for that column. So Bob, Sam, Julia, and Charles are the list of values or the row values for this key student name, which is the column name. Similarly, 87, 13, 99, and 67 are the row values for this key student marks. So now that we know how to create a data frame, let's go ahead and perform some inbuilt functions on top of this data frame. So we'll be working with these basic functions such as tail, head, shape, and describe. So to work with all of those inbuilt functions, we'll start by reading a CSV file as a data frame first. So again, let me perform the basic steps. So I'll type in import pandas as pd. Now to load a CSV file, I'd have to type in pd.read_csv, and inside this I'd have to give in the name of the file. So we'll be working with this iris.csv file, and I'll be storing this in a new object, and I'll call that object as iris. So now I want to have a glance at the first 5 records of this iris data frame. So to have a glance at the first 5 records, I'll just type in iris.head. Right, so I've got this first 5 records of the data frame. Now let's understand this data frame properly. So this has got 5 columns, which are basically sepal length, sepal width, petal length, petal width, and species. So these are basically the different features of the species of the iris flower. So you've got 3 different species: Setosa, versicolor, and virginica. And for all of these 3 different species, we've got the sepal length, sepal width, petal length, and petal width. So as we already saw over here, the head function helps us to have a glance at the first 5 records of this data frame. Now if I want to have a glance at the first 10 records, then all I have to do is type in 10 inside this head function. Then we'll have a glance at the first 10 records of this data frame, right? And if I want to have a glance at, let's say, the first 100 records, then I'll just type in iris.head 100. Right, so these are the first 100 records where the index value starts at 0 and it goes on till 99. Now analogous to the head function, we also have the tail function. So I'll type in iris.tail. Now this tail function would give me the last 5 records of this data frame. So this starts at index number 145 and goes on till index number 149. Similarly, if I want to have a glance at the last 10 records, then I'll just pass in 10 over here. Right, so these are the last 10 records of this iris data frame. Now, these are the head and tail functions. So there is also this describe function. So I'll just type in describe over here, and let's just see what it does over here. So this would basically describe this entire data frame in terms of all of these different measures. So we've got count. So this count is basically the number of records present for each of these different columns. So there are 150 records for sepal length, similarly 150 for sepal width, petal length, and petal width, right? So these are basically the different count values of all of these columns. And then we've got the mean value. So this is the mean value of sepal length, sepal width, petal length, and petal width. And similarly, we've got the minimum value, standard value, 25 percentile, maximum value, and so on. So these are some basic functions which can be implemented on top of any data frame. So now going ahead, we'll see how to access individual rows and columns from our data frame. So to do that, we've got the iLock and the LOC methods. So let's start with the iLock method. So first we'll give in the name of the data frame and then we'll just type in .iloc. So this .iloc basically stands for index location, and this is how we can extract some specific rows and columns from this entire data frame. So over here what we are doing is we are extracting the first 3 records from this data frame and the first 2 columns, right? So the index values go from 0 to 3. So 0, 1, 2, and then the column values are 0 to 2, right? So 0 and 1, sepal length and sepal width. So this is how we can extract a subset of the data frame from this entire data frame. So now let me again print out the head of this. So iris.head. This is my data frame over here. Now let's say I want a subsection which comprises of the row numbers starting from, let's say, 99 and going on till 126. And I want only the petal length and the petal width column. So to do that, I'd have to type in iris and then I'll type in LOC. I'll give in this square braces over here. I'll put in a comma. Now, whatever you given on the left side of the comma, that would denote all of the rows which you'd want to extract. And whatever you put in on the right side of the comma, that would denote all of the columns which you'd want to extract. So as I've said, the row numbers which I want to extract are from 99 to 126. So indexing will start from 99 and go till 127. And then the column values would be 0, 1, 2, and 3. So this will go from 2 to 4. So I'll just put in 2 to 4 over here and I'll store this in a new data frame and I'll name that to be iris1. So let me print out iris1 over here. Right, so this is our data frame iris1, which comprise of only the columns petal length and petal width, right? And the row numbers start from 99 and go until 126. Now, similarly, let's say if I want to extract all of the records starting from row number 10 and going on till row number 20, and I want only these 2 columns, the sepal length column and the species column. So let me show you guys how it's done. So this time I'll name the data frame as iris2 and I'll type in iris dot, I will type in iloc over here, and this would go from 10 to 21. And after this, I will just give in the column values. So again, I will take in a list over here, and inside this, I will give in the index of the first column, which is basically 0. And then I'll give in the index of the final column, which is 4 over here. I'll click on run and let me print out iris2 over here. Right, so this is my subsection of the entire data frame where I have row numbers starting from index number 10 going on till index number 20, and these are the 2 columns which I've extracted. So sepal length and species. So this is how I can work with the iloc method. Then analogous to the iloc method, we also have the loc method to extract individual rows and columns. So the only difference is, instead of giving the index values over here, we give in the labels of the columns over here, right? So over here, when it comes to rows, we'll similarly give in the index values of the rows. And over here, when it comes to columns, I will give in the names of the columns. So let's work with iloc. Now let me print out the head again, iris.head. Right, so this is my data frame over here. And this time I want all of the records starting from row number 33 and going on till, let's say, 44. And I'll store this in iris3. So this will be iris.loc, and inside this has to go from 33 to 44, and then the names of the columns which I want to extract would be sepal width and petal width. Now you have to keep in mind that you given the column names properly, right? So if you make a spelling mistake, then there would be an error over here. So I'll type in sepal width and then I'll give in the name of the next column, which is basically petal width. Now let me print out the subsection. So I'll just print in iris3, right? So these are all of the records starting from row number 33 going on till row number 44. And these are the 2 columns which I've extracted, sepal width and petal width. Right, so till now what we did is we extracted some individual rows and columns with the help of .loc and .iloc. But now we'll actually perform data manipulation operations where we'll be extracting records on the basis of a condition. So let's go ahead and do that. Now the condition which I want to specify is I want only those records from this data set where the sepal length is greater than 5. So let's see how can we do that. So first I'll give in the name of the data frame, which is iris, and I'll put in quotes over here, and then I'll give in the name of the column, which is basically sepal length. So I want to extract only those records where the sepal length is greater than 5. So I will basically give a condition that this sepal length has to be greater than 5. Now let me click on run and let's see what do we get. So we basically get a bunch of true and false values. Now what does this mean? So this means that wherever you have the true label, this condition has been satisfied, and wherever you have the false label, this condition has not been satisfied. So we have the true label for the 0th record over here, and that is because the sepal length is greater than 5. Similarly, we have a true value over here, and that is because the sepal length is greater than 5, right? So wherever you have the true value, that is where you have the sepal length to be greater than 5. Now we've done this. Let's go ahead to the next part where we actually have to extract those records. Now we just have a bunch of true and false values. So to extract the records, again I'll type in iris, I will give in braces, I will cut this and I will paste this inside this iris data frame. So what I'm doing is I will be extracting only those records where this condition evaluates to true. I'll click on run, right? And this is what we have. Now, if you look at the sepal length column, then you'll see that all of these values are greater than 5. So what we basically did is first we started off by giving the condition, and then we put in this condition again inside this iris data frame. So this gave us only those records where this condition was satisfied. Right, now let's go ahead and perform similar operations. So this time I want only those records where petal length is greater than 2 and the species is equal to Virginica. So let's check that out. So let me cut this first and given the condition. So the first condition would be iris, and then we want the petal length to be greater than 2. So I'll type in petal underscore length, and this has to be greater than 2. Now I will enclose this within round brackets. After that, I will give in the AND operator because I want both of these conditions to be satisfied. So I'll go ahead and give in the second condition. So the second condition is iris, and this time the name of the column is species. So this has to be equal to Virginica. So I'll just set Virginica over here. Right, so these are the two conditions. Now I will cut this out, and again I'll type in iris and paste it inside this, and I will store this in a new data frame and name that to be iris final. Now let me check the head of this. So iris final dot head, right? So we see that we have extracted only those records where the petal length is greater than 2, right? So here you see petal length is greater than 2 and the species is equal to Virginica. So we have given multiple conditions to extract these records. Now similarly, we can give as many conditions as possible. You can give 2, 3, 4 or 5, as many conditions as you want. So let's complicate this a bit and we'll give in 3 conditions over here. So this time I want the sepal length to be greater than 6, sepal width to be greater than 3, and petal length to be also greater than 3. So let's give in all of those 3 conditions and let's see what do we get. So I will type in iris, and my first condition would be sepal length has to be greater than 6. I'll put in braces, and this is my first condition. After that, I'll give in the AND operator. And then given the second condition, I'll type in iris, and the sepal width has to be greater than 3. So I'll type in sepal width. This has to be greater than 3. And then I'll give in the final condition, which is basically the petal length has to be greater than 6. So iris, and then I'll give in petal length over here. This has to be greater than 6. Let me cut all of this. Let me paste it inside this. Alright, so I have given my 3 conditions over here. Let me cut this entire thing out. Let me type in iris over here and I'll paste it over here. Alright, I will store this in, let's say iris random. So this would become iris random dot head, right? So we have these records where the sepal length is greater than 6, the sepal width is greater than 3, the petal length is greater than 3, and the petal length is greater than 6, right? Now let me actually remove this head and let's see how many actual records satisfy this. So see that there are only 3 records out of these 150 records where these 3 conditions are satisfied. That is, the sepal length is greater than 6, the petal width is greater than 3, and the petal length is greater than 6. Right, so these were some different data manipulation operations which we could perform on the iris dataset. So that was data manipulation. Now we'll head on to data visualization. And to perform data visualization, Python provides us a package called as Matplotlib. And with the help of Matplotlib, you can create beautiful graphs such as bar plots, scatter plots, histograms, and a lot more. So let's go to Jupyter Notebook and work with these graphs. So we'll start off by importing the pyplot submodule from the Matplotlib library. So I'll type in from Matplotlib import pyplot as plt. So I have imported this, and we also have to create some NumPy arrays. So for that purpose, I would also have to import NumPy. So I'll type in import NumPy as np. So we have imported the required modules. So now that we have the required packages, our first plot which we'll be making is a line plot. So to create this line plot, we would require x and y values. So let me start off by creating the x values. So x would be equal to np.aRange, and I want the value starting from 1 and going on till 10. Right, so let me just print this out first. So I've got my x values ready. Now let me also create my y values. So y would be equal to 2 times of x. So let me also print out y. So I also have my y values ready. Now it's time to finally make the line plot. So to make a line plot, all we have to do is type in plt.plot. So this plt is basically the alias for this pyplot submodule. Now whatever plots you're making, that all of them you'll be making with this pyplot submodule. And to make a line plot, you will be using this plot method from the plt submodule. So you'll just put in this round braces over here, and then you'll pass in the x and y values as the initial parameters. So you'll type in x, comma, y over here. After that, just type in plt.show, click on run, and then you successfully have created your first visualization. Now, isn't this a beautiful line plot? So over here, what we basically have is the x-axis, this is the y-axis, right? So when you have the x value to be equal to 2, the y value is 4. When you have the x value to be equal to 4, the y value is 8. And that is what this line plot is telling you. Now, wouldn't this be even better if we add title, x label, and the y label to this? So let's go ahead and do that. So let me add the title. So to add the title, you have to type in plt.title. And let's say the title which I'll be giving this is line plot. Now let me give it the x-axis label. So this would be plt.xlabel, and I'll just simply put in x-axis over here. Now let me also put in the y label. So I'll type in plt.ylabel, and inside this I'll type in y-axis. Right, so we have added the title, we have added the x-axis, and we have also added the y-axis. Now let's say I want to change the color of this line. So I don't really like blue, maybe I want green color or red color. So how do I do it? So over here, so I would have to go inside this main function, which is plt.plot, and I will use the color attribute and I will set the color. So I want this to be green, so I'll just type in green over here, right? So now I have changed this color to green. Similarly, if I want this to be orange, I can just type in orange over here and the color becomes orange. Now I can also play with the line width and the line style of it. So I'll just type in line width over here and let me set it to be equal to, let's say, 2. Let me click on run. So let me remove this underscore over here. Right, so I have increased the line width. So to make it more obvious, let me make it 5 over here. Right, so this has become thicker. So you can give it whatever value you desire. I'll give in 50. Right now this has become quite thick over here. So let me change it back to 2. 2 seems quite good for this. Now I can also change the line style of this. So I'll type in line style and I'll set the line style to be equal to colon. So when you put in colon, this is what you get, right? So you have a dashed line over here. So this is how you can basically create a line plot, right? So first you will type in plt.plot and then you will give in the x values and the y values. Now after that, if you want to describe the plot more, you can add the title, you can add the x label and also the y label. So let's say if you also want to add a grid to this. So all you have to do is set in plt.grid. So this has to be small g over here and you'll just type in true inside this, right? So you have also added a grid to this. So this is how you can add a line plot. Now let's say I want to add 2 lines inside this one single plot. So what I'll do is I will actually add one more y value. So my y1 is 2x over here. Similarly, I'll also create y2. So I'll set y2 to be equal to 3x. So let me print out y1 as well as y2. Right, so this is y1 and y2. So I will be making 2 plots over here. So first is with respect to y1 and x. Next would be with respect to y2 and x. Right, so now we have 2 lines over here to distinguish them. Let me give it a different color over here. Let me change this to, let's say, back to blue again. Right, so this is the line which denotes y is equal to 3x and this is the line which denotes y is equal to 2x. So this was a line plot. Now let's go ahead and create a bar plot. So I'll just give in a comment over here, bar plot. Now to create this bar plot, I would need a dictionary first. So let me again name this dictionary to be student over here. And I'll have some names of students and the marks of the students. So let's say the first student is Sam again and he has scored 30. Then we've got Bob who has scored 50. And finally, we've got Julia who has scored 70. So we have created this dictionary over here. Once this dictionary is done, I'd have to extract the keys and store it into a separate variable and extract the values and store it into a separate variable. So I'll take this new variable called as names and I will extract only the keys of it. Now, once I do this, I would need the list of the keys because the plt.bar function only takes a list of values. I'll cut this and I'm pasting this inside this. Similarly, also extract the values. So I'll be storing that in the marks object. Again, let me do the same thing. So this will be student.values. So let me print out names and marks over here first. Names and then I've got marks. So I have extracted the names and then I've also extracted the marks. Now to make a bar plot, I just have to type in plt.bar. So first I would have to give in the categorical values which are stored in names. And then I'd have to give in the corresponding numerical values with respect to those categorical values which are stored in marks. Let me also put in plt.show over here. Right, so this is my bar plot. So this graph basically tells me that there are 3 students. First is Sam who has scored 30 marks. Then there is Bob who has scored 70 marks. And then there's Julia who has scored 70 marks. Now again, if I want to change the color of this bar, all I have to do is use this color attribute and give it a different color. So let's say I want to give it yellow color. So I'll set yellow over here. Right, so I have changed the color. Again, if I want to give the x-axis label, y-axis label, and the title, it does the same process again. So I'll type in plt.title over here, and I give the title as marks of students. After that, I'll set in the x-axis label, so plt.x label, and that would be equal to names of students, and then plt dot y label, which would be equal to just marks. Right, so marks of students is the title, marks is the y-axis label, and names of students is the x-axis label. Again, if I want to add a grid, it will be plt dot grid, and I'd have to just set in true over here. Right, so this is my bar plot. There is also something known as a horizontal bar plot. So over here we have these bars stacked vertically, but instead if you want to see these bars horizontally, then we have this bar h function from the pyplot module. So the only difference which we'd have to do is, instead of plt.bar, we just have to put in plt.bar h. And when you do this, this is what you get. So initially these bars were stacked vertically. Now when you use bar h, these bars are stacked horizontally. Now let's go ahead and create a scatter plot. Let me add the comment over here. All right. So first I'll go ahead and create two lists over here. So I'll name the first list as X again, and I'll give in a bunch of random values over here. So I'll take in, let's say, 6 random values. So 1, 2, 3, 4, 5, and 6. Now similarly, I'll take another list. I'll name it to be Y1. Now you have to keep in mind that you take the same number of values in X and Y, because a scatter plot, it basically gives you a point for a specific position of X and Y coordinates, right? So again, I'll give in some random 6 values. So 9, 1, 2, 6, and 4, and 9 again. So we've got the X and Y values ready. Now to make a scatter plot, all you have to do is just type in plt.scatter and then pass in the X and the Y values. And this is what you have. Let me also add the grid. So plt.grid, I'll make it to be true. Right, so this is what you have. So this is the first point where the X coordinate is 1 and the Y coordinate is 4. Right, so this is the point which it is denoting. And then we've got 3, 2. So 3, 2 would be this point. Then we've got 4, 9. So 4, 9 would be this point, right? So this is how a scatter plot looks like. Now let's say if you want to depict 2 different point themes on the same scatter plot, then all you have to do is create a new list. So I'll name this to be Y1. I'll set it to be Y1 over here. Let me again create a new list, which is Y2. Let me give in a bunch of random values again. So 4, 7, 8, 1, 2, 6, right? So I've got my bunch of 6 values over here. Let me create another scatter plot over here. So this time it'll be with respect to X and Y2, and I will give it a different color. So the color would be red. Right, so I have added 2 different theme points on the same graph over here. Now let's head on to the next plotting, which is a histogram. So histogram basically helps us to understand the distribution of a continuous column. So for this, we'll be actually loading the iris dataset again and understanding the distribution of some of the continuous columns of that dataset. So again, I'll load up the dataset. So I will type in pd.readcsv. And now I'll give in the name of the file, which is iris.csv. And I'll store this in iris again. All right, so let me have a glance at the head of this again. So iris.head. Right, so this is our data set. Now I want to understand the distribution of this sepal length column. So for that, what I'll do is plt dot, to make a histogram, we've got this hist function. And inside this, I'll just give in the name of the column. So iris, and I'll give in the name of the column, which is sepal length, and then I'll just put in plt.show. So this is the histogram, and this shows us the distribution of the sepal length column. Now to increase the distribution of these bins over here, we've got the bins attribute. So I'll just type in bins. So let's say I want 20 bins. So I'll just type in bins. So I'll just set the bins value to be equal to 20. So the inference which we can draw from this plot is, so let's say if we take this particular bin over here, then this tells us that there are around 16 records where the sepal length of the flower is exactly around 5. Then we've got this over here. So this bin tells us that there are again around 16 records where the sepal length is 6.5. And if we take this bin over here, so there are very few records. So this would be, let's say there's just one record where the sepal length is somewhere between 7.5 and 8. So again, if we take this bin, so there would be around 4 records, or there are just 4 flowers whose sepal length is 4.5. So this is the sort of inference which we can draw from a histogram. And the basic difference between a histogram and a bar plot is, so a bar plot is used to understand the distribution of a categorical variable, while a histogram is used to understand the distribution of a continuous variable. Now similarly, if I want to understand the distribution of, let's say, petal width, so I'll change this over here and I'll just put in petal width. Right, so this is the distribution of petal width. So there are around 34 records whose petal width would be somewhere around 0.2 or 0.3. So those constitute a lot of flowers, right? And if we take this bin over here, so there would be just one record, or there's just one flower where the petal width is 0.5. And this seems to be the maximum petal width, which is around 2.5. So the maximum petal width of 2.5, there are around 5 records. Right, now let's again understand the distribution of sepal width. So I'll change this and I'll just put in sepal over here. Right, so we have a big peak over here. So there are 25 records where the sepal width is 3, and there is just one record whose sepal width would be around 4.3 or 4.4. Right, so this is histogram. So now we'll go ahead and make some box plots. So box plots are used to understand the distribution of how does one continuous variable change with respect to a categorical value. And again, we'll be building box plots on this iris dataset. So I'll type in iris.boxplot. And this basically has two parameters. So the first parameter is the column where we'll assign the y values, or the continuous value. And the continuous value which I'd want to give in is sepal length over here. So I'll type in sepal length. And then I'll map the categorical value onto the x-axis. So for this, I've got the by attribute, and we've only got one categorical variable over here, right? So the species column is the only categorical variable which you've got. So I'll type in species over here. I'll hit on run, and this is the box plot which you get. So what you see over here, so this line which you see in the middle of this box, this is known as the median line. This is the 25 percentile line, and this is the 75 percentile line. Let's just focus on this median line over here. So this tells us that if the species of the flower is setosa, then the median sepal length of the flower would be around 5. And again, let's take this box over here. So if the species of the flower is versicolor, then the median sepal length would be around 5.9. And let's take this. So if the species of the flower is virginica, then the median sepal length over here would be 6.5. So this is the inference which you can draw from a box plot. Now similarly, if I want to understand how does petal width vary with species, let me just put in petal width over here. Right, so again we have 3 boxes over here, 1 box each for the different species of the iris flower. So over here, it seems that the median line would be somewhere over here. So if the species of the flower is setosa, then the median petal width would be around 0.3 or 0.4. Then we've got versicolor over here. So if the species of the flower is versicolor, then the median petal width would be 1.2. So the basic inference is virginica over here would have the maximum petal width, and setosa would have the minimum petal width. So that was the same case which we saw with sepal length as well. So Vojanica had the maximum sepal length and Setosa had the minimum sepal length. If we want to make this plot even more beautiful, we can use the Seaborn library. So let me just import the Seaborn library. I'll type in import Seaborn as SNS. Then we've got the boxplot method from this. So sns.boxplot. Now what I'll do is I have already loaded this iris dataset. So onto the x-axis, I'll be mapping the species column. So iris, and I'll type in species, and onto the y-axis, I will basically map the sepal length column. So again, iris. So the name of the column is sepal length. Alright, so this is a much more beautiful plot when compared to this. So again, the inference is pretty much the same. Alright, so Vojanica over here would have the maximum sepal length, or the median sepal length would be maximum for Vojanica, and the median sepal length would be minimum for Setosa. So these are the inferences with respect to box plot. Now we'll go ahead and work with the final plot with respect to visualization, which would be a pie chart. So before we make this pie chart, we have to create two lists over here. So I'll create first list with the name fruits, and I'll just add some names of fruits. So the first fruit is apple, second fruit is mango, then we've got orange, and then we've got banana over here. So I've made the first list, and then I will give in the cost of fruits over here. So I'll just give in some random values. So 76, 45, 90, and let's say I'll give in 85 as well. Right, so I've got the fruits list ready, and I've also got the cost list ready. Now all I have to do is map these two into a pie chart. So I'll type in plt.pie, and inside this I will first map the numerical values. So I'll type in cost, and then I'll map the labels. So we've got the labels attribute over here, and for this labels attribute, I will map this list to the labels attribute. So I'm mapping fruits onto labels over here. Again, I'll just click on run. So beneath this, I'll put in plt.show. Right, so this is my pie chart over here. So this basically tells us that the maximum distribution, or the maximum percentage, is mostly of orange and banana, and that is actually true. So orange, if we see, the value is 90, and banana, if we see, the value is 85. If you want the actual percentage, we have something known as the auto PCT attribute. So let me add in the auto PCT attribute over here, and I'll put in single quotes. I'll put in a percentage symbol, and then I'll type 0.2. I'll type in F, and then I'll give in 2 percentage symbols over here. Right, so we've got the percentage values over here. Now what does this exactly mean? So this 0.2 basically denotes the decimal value. So if I put in 2 over here, then this will show 2 decimal values. Let's say if I just put in 1 over here, then you've got 1 decimal value over here. Right, now I can also add a shadow to this. So I'll just put in shadow equals true. And this is my pie chart over here. So this shows us that the maximum percentage of the fruits belongs to orange. We've got 30.4%, and then we've got banana 28.7, followed by apple, and then the least is mango. Now let's say if I want to increase the size of this plot. So we have something known as plt.figure. I'll type in plt.figure, and inside this we've got the attribute fig size. So I'll give in the value 6,6 over here. Right, so I have increased the size of this. Now similarly, let's say instead of 6,6, I put in 10,10. Then this would be enlarged even more. Right, so this is our final pie plot. Right, so guys, this brings us to the end of the visualization module.
So in linear regression, it's one of the most popular algorithms in production because it can be used for classification, it can be used for regression. It also happens to be one of the core algorithms that is used by many other algorithms. Logistic regression is a linear regression based model, right? If you take support vector machine, another very famous algorithm in data science, it's a linear model. Or if you take, if you do linear models using binned data, what you call bin, B-I-N, binned data sets, then the model that you get behaves like a decision tree, right? So many of the other algorithms which are very popular in the industry, internally they're linked to linear models. You can spend your entire lifetime studying linear models. It has so much of depth and breadth that it takes a lot of time to actually get used to all these things. So today I'm going to start by introducing you to simple linear models, the core concepts, and then subsequently I'll leave some advanced discussions for the next visit where we'll be covering FMT, feature engineering model tuning. There we'll discuss some further advanced concepts of linear models. All right. So I hope these people have loaded my team has loaded the data set, everything. I'm going to give you 3 codes today, of which I'll cover 1 in the class. The other 2 is for you to go and explore further, okay? Based on what we discussed in the class. This PPT is accessible to all of you. Can you access this PPT? I think she's gone to, you can? You can? Okay. The code is also available. The PPT, the code, the data set. You should have received 3 codes. All right. Let's start. As the name suggests, this algorithm is called linear regression. And the reason why it's called linear regression, as the name suggests, is it's based on the concept of a line, a plane, a hyperplane. We call it by these names. Okay. So to begin with, I need to ask you whether you know how a line is represented. Line in mathematics. Are you all comfortable with this? All right. So let's start. Imagine I give you 2 dimensions. This is x. X is one of your independent attributes. We call it columns in our data frame, right? So I have loaded a data from a table into my data frame, and one of the columns in the data frame I call it x. This is my independent variable. The other column which I want to predict, the target column, I call it y. Could be anything. Y could be the miles per gallon, and x could be the weight of the car. The more the weight of the car, the less the miles per gallon, right? So y is my dependent variable, x is my independent variable. Imagine this x has 4, 5, 6. These are the units, 1, 2, 3, 4, 5, 6. These are the measurements of x. And let's assume, for sake of discussion, let's assume that whenever x is 1, y is also 1. So whenever x is 1, y is also 1. That is what you're seeing in the data. You take another record, there you see x is equal to 2, then y is also equal to 2. Take the third one, x is 3, y is also 3. So when you try to draw a line, a relationship between them, you see it's a straight line. The straight line tells you the relationship between x and y. How are these two related to each other? We in data science call these things as models. Models are nothing but surfaces in your feature space. What is a feature space? Feature space is collection of your independent attributes and the dependent attribute. You are trying to explore how this y and this x interact with each other. That interaction is what we represented as models. So models are nothing but lines, surfaces, hypersurfaces in your feature space. So when you build k nearest neighbors, okay, In k nearest neighbors, you have different classes of data points. Suppose these are different classes, okay? And okay, let me make it slightly more complex. What k nearest neighbor does is, we call it breaking your mathematical space into regions. It breaks your mathematical space into regions. So it says this region belongs to the circular point, this region belongs to the triangular point, and you have things on the wrong side. K nearest neighbors splits your mathematical space into regions. Those regions are called Voronoi regions. So this imaginary surface is the model in k nearest neighbor. So in linear regression, this line which represents the relationship in x and y, this line is my model. So I want to predict the value of y given the value of x. What the line is saying is y is equal to x. So the prediction is whenever x is some value, y will also be the same value. Can I write this expression as y equal to 1x? Does it make any difference? 1 into x. This 1 in mathematics, it has a meaning. This 1 is nothing but this angle that line makes with the x-axis, the tan of that angle into x. Whenever y is equal to x, this angle will always be 45 degrees. Okay? And in trigonometry, tan of 45 is always 1. Now you might be wondering, what is this trigonometry, tan, theta, and all? These are all jargons. Actually, it's all common sense. Look at this. When we studied in school, we came across trigonometry. In trigonometry, we came across sine theta, cos theta, tan theta. What are these sine theta, cos theta, tan theta? What are these things? These are names given to certain ratios. So tan theta is, tan means the ratio between, we show it as dy by dx. How much y changes whenever x changes by 1 unit? That ratio is called tan. How much y changes when x changes by 1 unit? How much y changes in this graph when x changes by 1 unit? So 1 by 1 is equal to 1. dy by dx, how much y changes by small change in x, 1 unit change in x, that ratio is called tan theta. Sounds very hi-fi, but that's what it is. Okay? So whenever both of them synchronize, whenever x changes by 1, y changes by 1, it will always happen when this angle is 45. So we say the tan of 45 is 1. So when you say tan of 45, dy by dx will be 1 by 1, it will always be 1. Alright? Let me modify this a bit. So right now, this expression is represented as m. Okay, this is a standard practice where we represent it as m. So y equal to mx is the expression, mathematical expression of this line. Suppose I put a line here, okay, and it's parallel to this line. It's parallel to this line, okay, which means this line is also making 45 degrees to the line parallel to x-axis. I'm not going to show this line here, okay, just to make it less cumbersome. So I have another line here. This is L1, this is L2. Now can I say y equal to x? When x is 0, y is not 0, y is 2. Correct. When x is 1, y is not 1, y is 3. When x is 2, y is not 2, y is 4. So we add a constant to this. this constant is equal to 2 right now for this line. This constant is nothing but what is the value of y when x is 0? What is the value of y when x is 0? That is called c. It also goes by the name of intercept. Where in your mathematical space on the y dimension, where on the y dimension does the line intercept or cut the y-axis? So this is the generic equation of a line, y equal to mx plus c. It tells you how y and x are related to each other. If you look at this line L1, then this becomes 0. So y equal to mx. If you look at L2, this becomes not 0 but 2. So this relation continues to remain same. In both the cases, the m is same. M is nothing but tan of the 45 degrees. We call it slope. Right? So this is the generic equation, one way of representing a line, y equal to mx plus c. So in this expression, y is given in your data set, it's the target column. X is given in your data set, it is the independent columns, the independent attributes. From this data that you have given to the algorithm has found out for you the m and the c. We call these coefficients. Coefficients of the model. This m and the c, they reflect the relationship between y and x in your data set. So the m and the c is what forms the model for you. Shall I complicate it a bit more? We'll complicate it a bit more. Suppose instead of having 1, or let me just continue with this only. So you have one target variable y, one x. In this case, tan of 45 happened to be 1. But suppose your line is like this. It's a straight line, but it's not at 45 degrees, it's at 15 degrees. Right? Then in that case also the equation of the line will be y equal to mx. The reason why I'm not putting c is 0 here. C is 0. You can put c, but c is 0. And this angle m, this value of m, will not be 1. It will be 1 only when it's 45 degrees. It's less than 45 degrees, so tan of 15 degrees into 1 into x plus c. This will be equation of this line. What is tan theta? Tan theta is nothing but how much y changes for 1 unit change in x. We call it tan. Okay. All right. Let's complicate this a bit more. Suppose instead of only one variable x, now you have x1 and you have another variable x2. And you have only one dependent variable y. In such case, the algorithm will find out the relationship between x1 and y, x2 and y. So it will express that relationship as y equal to m1 x1 plus m2 x2, and there will be only one constant term, because now instead of having a line, you will have a plane where the plane goes through the y-axis at some point, it cuts the y-axis at some point. So now you have two edges. One edge is on x2, the other edge is on x1. The two edges may have different slopes, different angles with x-axis. Those are reflected over here as M1, M2. The C continues to be the same C. Where is the plane cutting the y-axis? Which means, what is the value of y when x1 and x2 are 0? That is called the intercept.
So we're going to have only one plane, like we can't have a multiple plane, like in case of a 3D.
In case of?
Like if we have a Z also, so then will be having a...
It will be called a hyperplane. We don't know how it looks, but it will be only one. Yeah. So human minds can imagine only 3 dimensions. But suppose they go beyond 3 dimensions, there also the linear models work. Those planes are called hyperplanes. Hyperplanes, how do they look? We can't imagine. So we don't know that, but they will also be one single plane. And there will be no ups and downs, no curves, nothing. It will be a straight plane. What do you mean by straight plane in 4 dimensions? No idea. It will have the same properties as the properties of a plane in 3 dimensions.
So these x1 and x2 need to be in the same plane, or it can be in a different plane, like x1 is in one plane and x2 in different plane. Is it possible?
They will be in the same plane.
Yes.
They can't be in different. Right? And
actually, x1 is one axis and x2 is another axis, and they are like separated with some angle.
90 degrees. This angle in linear models, this is a 3-dimensional isometric view. This angle is always 90 degrees. We say that they are orthogonal to each other. Look at this laptop. Okay, in this laptop, now this is my x1 dimension, this is my x2 dimension. There is a plane. This plane is your model. This plane is making some angle. I can't make it right now. I can't, right? It will make some angle with x1 axis. It will make some angle with x2 axis. This is my M2. This is my M1. So at what angle the plane is to x2 and x1 will decide the value of y. Okay. In this case, the value of C will be 0 because the plane is touching the y-axis. Y-axis is perpendicular like this. It's touching the y-axis at the origin, the 0 point. So imagine I can remove this. If this was a yoga tablet, I could remove this. Okay, and imagine I'm putting it in some angle, cutting the y-axis at some point. Then this angle is my M1, M2. The point at which the plane cuts the y-axis is my C. We cannot imagine beyond 3 dimensions how the planes will look, but they will have the same mathematical properties as a plane in 3 dimensions. A point that you should probably keep in mind, it will become useful to you down the line when you do deep learning and so on and so forth. The number of dimensions of a model, this is the model right now, the surface. The number of dimensions, how many dimensions is this model? 2 dimensions, length into breadth. The model is only 2 dimensions. The feature space is 3 dimensions. So the number of dimensions in a model will always be 1 less than the number of dimensions in the feature space. Right? All right. You can call it anything you like. That's not a problem. X, Y, Z. Okay, that's what they're saying. You want to call it Z, you call it Z. Doesn't matter. It just replaces the Z. Basically, these are independent variables. This is the target variable. So we are trying to understand how the target variable is influenced by these.
Say you have 3 x1, x2, x3. So how in that case the model dimension will be, so still the model dimension will be 2 only, right?
No, x1, x2, x3 are 3 independent variables. So therefore one target variable also. No? So that makes it 4. 4 dimensions.
4 dimensions. What is the dimension of the
model will be 3 dimension in that case. I mean, however it looks, I don't know how it will be. How will it look? It will have three edges. We don't know how it looks, so that's why we don't talk about it. But the properties of that model will be similar to properties of a plane, a line, so on and so forth.
So don't imagine, you can't.
So independent variable we have to always consider as the orthogonal in nature.
That is what the algorithms assume. All the algorithms assume that your independent variables, okay, suppose you have a data frame. In the data frame, you have multiple columns. These are independent variables, IV1, IV2, IV3, and this is my target. All algorithms assume that independent variables are independent of each other. They don't influence each other. They only influence the target. That's what they assume, but in real world, that is not true. Suppose I want to predict miles per gallon of a car, given the weight of the car, given the horsepower of the car, we know that they are related. So we can build a model, but we also know that horsepower and weight are also related to each other. More the weight of the car, more the horsepower. They're positively related, but the algorithm assumes that they are not related. This problem in linear models, it's called the problem of collinearity, where assumption is each dimension is independent of the other, but in reality they influence each other. That problem is called collinearity. Okay? This collinearity, where independent dimensions interact with each other, they're not independent. This collinearity can lead you to a problem when you productionize your models. The models may be less effective, less predictive power than required to be because of the collinearity. So one of the things that we do when building models is we see what the collinearity is between the dimensions. If the collinearity is very strong, they're very strongly related to each other, the independent variables, then we may have to resort to some techniques. Suppose this is my horsepower and this is the weight of the car, and if I plot a graph between these two, can you tell me how that will look? This is weight of the car, this is horsepower of the car. If I plot a graph between these two, take all the data points, you will see some linear trend. Okay, all of you know what is R value? Coefficient of correlation, R value. Statistics, you've done statistics, right?
Hey, come on.
Okay, R value of measurement of how these two variables relate to each other, how strongly, you will see that R value comes very close to +1 in this case. The maximum it can be is 1. So it will be very close to +1. Okay? Which means these two variables are not truly independent of each other. But the algorithm wants all the dimensions to be independent of each other. So in such cases, we resort to a technique called dimensionality reduction, which is not simply dropping the dimension. I may convert them into a composite dimension. Both the dimensions put together, I create a synthetic dimension. And I use that synthetic dimension in my model building rather than these two.
Just a question. In this case, the horsepower and the weight of the engine is the same, almost same. Like it's increasing the same in non-linear line. It means, well, if I put both of them, it will have the same effect in the model. If I remove one of them also, then it will have the same effect in the model. The model will not change anything.
If that removal is an option to you when the relationship is absolutely a line, but you will see that it's generally not a line, it's a spread, and the spread is also curved. So which one should I drop? Should I drop this or this? That depends on which dimension is more prone to errors when you're capturing the data. So instead of doing all that analysis, I might convert into a synthetic dimension using a technique called PCA, Principal Component Analysis.
One question. So in the previous example, we took two variables, independent variables, x1 and x2, and they are separated by 90 degrees, right? Yeah. So in that case, we can have only 4 independent variables. Because 90, 90, 90.
No, that's what I'm saying. That is our brain. Our brain can see only 3 dimensions. But the algorithm can work in 300 dimensions. All the 300 dimensions mathematically will be orthogonal to each other.
What is the problem if these variables are actually very collinear and very collinear? So why is that problem?
Okay. You please keep this question parked for a minute. I want to cover some ground before I answer that question because that's a very important question you asked. All right, let's move on. The term regression indicates that we're going to predict some values. Whenever you build models to predict values, we use the word regression. The term linear, now you understand where it comes from. So your linear model is nothing but a combination, addition of weighted variables. This weighted variable, this is another weighted variable, you're adding the two to predict the value of y. It's a linear combination of one or more variables with weights. The weights are called coefficients. Okay, so once again I repeat, what is this M1? M1 is how much y changes whenever x1 changes by 1 unit, keeping x2 constant. What is this M2? M2 is how much y changes whenever x2 changes by 1 unit, keeping x1 constant. Okay, so this is the relationship between x1 and y. This is the relationship between x2 and y. The relationship is how much y changes whenever input changes by 1 unit. That is a relationship, and that relationship is what we call linear models. We already seen this. I'm going to move on. So before we start building our models, we actually need to analyze our data set. And what I mean by this is, suppose this is my data set. I will go and analyze between this IV1 and target, IV2 and target, IV3 and target, which one of these is strongly related with the target. If suppose IV2 and the target, the distribution is scattered all over the place. It's like a cloud. The data points are spread like a cloud. There's no trend you are seeing in that spread. Then in that case, IV2 is not a good predictor of the target. How can you say that? Take any value of IV2. Draw a straight line. For that value of IV2, you have multiple values of target. Which one should I take? I don't know which one to take. So we say that we say that IV2, independent variable 2, is not a good predictor of the target. On the other hand, if suppose between say IV1 and the target, we see the data points scattered in some form of a trend, then we say that IV1 is a good predictor of the target. So the first filter that you will apply in your data set is, of all the columns given to you, which columns strongly relate to the target. Those columns which don't relate strongly with the target, you are going to drop them from your analysis. You are not going to build your linear model on them. Okay? So the relationship could be positive or the relationship could be negative, it could be downwards also. I want a strong relationship. Doesn't matter if it's this way or that way, I don't care. But I don't want to include any columns in my model which have this kind of a spread versus the y. Okay?
Sir, but it has to be linear. Like it cannot be a parabola or something like that. Suppose there exists a strong
It should not be parabola. It should not be parabola. Linear models are built only when you see linear relationships. If you see non-linear relationships, then you might want to resort to non-linear models. Okay, linear models, they expect a linear relationship between y and the independent variables. Then your model's predictive power will be very high. However, as you will see now, those are all very perfect conditions. In the real world, we hardly have such perfect conditions, right? So sometimes, even when the relationship is not linear, we go up, build a linear model. We'll see that down the line. Okay, how do you measure the strength of the relationship between independent variable and the target? For that, we use a metric called coefficient of correlation. how these two variables, the target and the independent variable, how they correlate, how they relate to each other, which we express using a character called R. I'll tell you what this R is. This R metric can have a value of +1, -1 to +1 in this range. The least it can have is -1, the max it can have a value is +1. It cannot be beyond this range. R value can be 0. It can be 0. When you have it spread like this, your R value will be very close to 0. When you have a spread like this, your R value will be very close to -1. When you have a spread in the other way, your R value will be very close to +1. Okay? So R value is an indicator of how strong the relationships are. So let's understand this R value slightly more detail. The formula for R value is this. This is a formula for R value, okay? So, shall we begin? Don't worry about the formula. Don't worry about the formula. Understand the concept. All the formulas are there in the library. We just need to call those functions and get our things done. But get the concept in place. Yeah.
If I have different units of measurement, independent and independent variables, how does the R value then in that case work?
Doesn't matter. R value is a measurement based on the spread of the data. Now, have you heard of scaling? Scaling? Linear model is one model, linear regression, where scaling has no impact. Whether you scale the data or not, it's going to give the same result. All of you know the formula for variance? What is the formula, please?
Square standard.
What? Variance. Variance. X minus mean. Xi minus x bar, you can call it mu, the whole square n. Okay? I is equal to 1 to n. Let's keep it n, but otherwise we use n minus 1. If sample size is less, we use n minus 1. Okay? All of you okay with this? Don't worry about these things. What is this variance? That's what you need to understand, not the formula. Thank you. I know it's spread. What is it telling you?
It means how from the mean, how the data, what is the distance of the data and how it is.
I know, but what is it telling you?
How is it related with the data?
The distance between
how it varies with
how it varies.
What is the similarity?
What is central value? What is x bar or what is mu? What is the central value? Don't give me the formula. Don't give me the formula. I know the formula. Central value is a value which represents all the data points that you have. Okay? So if I take all your heights, add it up, divide by a number of students in the class, that will be average height of a student in this class. Now, how good this average is? First of all, why do we take averages? Why do we need mean and median and all? Why do we do all these things? There are many. That is statistical answer. Yes, you're right. But many times in data science, you will come across a situation where you have a function and the function takes as input only one value to predict something. Now, which one of the values should I put? There are 30 students in the class, each one has a different height, right? I want to say order some kind of a code for all the students in the class, a great learning stamped code. Now, what size should I tell the manufacturer? I can't give different sizes and one unit of every size. So I have to give some size which will represent all of you so that all of you can fit in comfortably, right? That is the idea, okay? In such situations, we need to input only one value. So what we do is we find the x bar or the mu. But the question is, how reliable is this x bar? Suppose the average height of the student in this class comes to 5.5. Some of you might be 6-footers, you might get offended, you will say, boss, I'm 6-footer, how can you say I'm 5.5?
Depends on how spread this particular, what is the difference between mean and
exactly. So how reliable your central values is based on which you're going to do further actions. How reliable your central values is, that reliability is given by the measure of variance. If the variance is too large, the central value is not reliable, right? So the variance gives you the reliability of the central values, how reliable the central values are. So the formula for variance is this, right? Just look at the numerator. Just look at the numerator. This is the case when you have only one variable, x. Now I have two variables, x and y. I want to see how they vary together, how they influence each other, vary together. That is called covariance, which is given by xi minus x bar. We don't square it into yi minus y bar. So we find out xi minus x bar multiplied by yi minus y bar. That tells me how the data points in the feature space, they vary together. That is called covariance.
So they should not vary together to have high covariance.
Independent variables. Independent variables. Independent variables should not have covariance. Target variable and independent variable should have strong covariance. Otherwise, you don't use those independent variables. When you're building linear models, the target variable, the y, and the independent variables, IVs, should have very strong covariance. But within the independent variables, the covariance should be 0. That is an ideal situation. Practically, it never happens. All right. Now, given this covariance, now look at the formula for R. Okay. On the top, in the numerator, you're seeing covariance, right? And if you look at it carefully, the units on the top and the units on the denominator are the same. This is also xi minus x bar, this is also xi minus x, this is yi minus y bar, this is also yi minus y bar. It is squared term, but there's an under root. This is also squared term, but it's an under root. So both numerator and denominator are going to have same units of measurement, agreed? So if I have a kilogram by kilogram case, then the units cancel each other out. It becomes a unitless quantity, it is a ratio, R value is a ratio. Okay. Now, when you have a diagram, when you have a plot like this between two variables, could be independent variables, target and independent, could be anything. When you have this kind of plot, you will see that R value is close to 0. We'll see why this happens. When you have this kind of a plot where you see a trend, but as x increases, y decreases, they are going in different directions. X increases, y decreases, they're opposing each other. Then we'll have R value close to -1. Whenever they go hand in hand, when x increases, y also increases. They go in the same direction together. Then R will be close to +1. And it's not very difficult to understand why. Let's look at this particular case closely. I'm going to look at this particular case closely. Yeah, this is my mathematical space or feature space. Both x and y have some x bar and y bar, the average, right? X bar, y bar. Keep in mind, all linear models that we build, linear regression models, they will always go through the point where x bar and the y bar meet. So the linear model that we saw a few minutes ago, this model will always go through wherever the x bar and the y bar meet. It will be hinged onto that point. That point will act as a fulcrum. All right? There's one particular point that linear regression models will always go through x bar, y bar. I'm really surprised and I find it very difficult to understand why this is not told. Now look at the points over here, okay? Let's look at these points carefully. Take any point, let's take this point. For this point, what is xi minus x bar? Xi minus x bar is this distance. This is my x bar, the vertical line. Xi minus x bar is this distance. Agreed? All of you agree? What is yi minus y bar for this point? It is the distance between this point and the y bar. Agreed? Xi minus x bar is positive, yi minus y bar is positive. So when you multiply these two, it is like finding the area of a rectangle. Length into breadth. So xi minus x bar into yi minus y bar for this point is nothing but the area it covers over here. This is the area. This area is a positive area. All of you okay? Let's take another point at the bottom of the screen, say this one. For this point, xi minus x bar is greater than xi, so xi minus x bar is negative. So for this point, xi minus x bar is negative, yi minus y bar is also negative. Negative into negative becomes positive. So all the areas over here will be positive, all the areas over here also will be positive. Agreed? Take this point. Xi minus x bar is negative because xi is less than x bar, negative. Yi minus y bar is positive. So positive into negative will give you negative. All these data points will have negative areas. All these data points will have negative areas. When you total this up, sigma, you see sigma over here? Sigma means sum up all the areas. When you sum up all the areas here, all the positives and the negatives will cancel each other out. The reason why they will cancel each other out is each quadrant has same density of these points. The points are distributed like a symmetrical circle. So whenever r value is close to 0, that is because your numerator is becoming 0. Numerator becoming 0 means your distribution is like this. For a given value of x, I have multiple values of y. Which y should I take? I don't know. So we say that x is not a good predictor of y. On the other hand, if you take this plot, if it becomes tighter, then positive areas is greater than the negative areas. So r value will be close to +1. It will become 1 only when all the data points lie on a straight line, which will never happen. If this plot was this way, all the negative areas will overwhelm the positive areas, then r value will be close to -1. Right? All of you okay? So this is the concept of r value. So what we do in linear models is we test the r values of every independent dimension with the target variable. We select only those whose r value is either close to -1 or +1. Any dimension with r value close to 0, that dimension is a useless dimension. How close to 0 is useless? That depends on your particular problem statement. So generally, any r value greater than 7.7 minus or plus, it's considered as a good variable. Any variable with r value between 0.5 and 0.7, it requires further research whether this relationship is real or is it a fluke by chance that you're seeing in your data set. Any r value close to 0, not worth considering.
What about the second case you told, fluke? What does it exactly mean? I don't understand. Why you said fluke?
Okay. It could be a sampling error. The way you selected your samples from the population, that leads to the R value. Okay. Now observe this. Since you asked this question, let's discuss this out. For R value to be 0, okay, if this is my x and this is my y, this is x bar, this is y bar, okay? X bar, y bar. I'm not showing you the coordinates. For R value to be 0, the data points, suppose I give you 10 data points, the data points have to be absolutely symmetrically distributed for R value to be 0, absolute symmetrical distribution in all the quadrants. What is the probability that when you're doing random sampling, you'll get data points in such a way that they get symmetrically distributed around this? What is the probability? Probability is 0. That particular configuration of data points that you want from the universe which symmetrically distributes itself around these two x bars and y bars to give you the R value of 0, that probability is 0. It will never happen. So even in the real world, if there is no relationship between x bar and y bar, because of your sampling, sampling brings in some asymmetry in the distribution. There will be some asymmetry in the distribution. You will end up with an R value greater than 0. This R value, we call it statistical fluke. So when R value is very close to zeros, it could be by chance sampling problem. It may not be a real relationship. So you have to go and further investigate whether the relationship is real, it might be real, or is it fake?
It might be possible also R value is greater than 70, but it might be a fluke.
Probability is very low.
Yeah, probability.
That will happen when your sampling is completely gone case. You have done some mistake in sampling. Then it can happen. All right. Shall we move on?
One question. So what is the application of this? So one thing is when we have independent variables, how they are closely related, so that we can come out with composite.
Yes. You're talking about R value.
Yeah. Another thing is finding the relationship between how independent is closely related with the target. So in both cases we can use.
Yeah, in both cases we have to use this. We have to use for both the situations to select the independent dimensions. And within the independent dimensions, knock out those which are very strongly correlated.
So is this the only Pearson only the way to find out?
No, there are other methods. Carl Pearson is the most commonly used for coefficient measure. There is one more available. There are many such available. But this is one which we mostly use in our cases. Shall we move on? Okay.
Now, this algorithm that we are going to use, what this algorithm will do is, given the data set you have, okay, suppose this is the distribution in x and y. In your data set, you have only one independent column and the one target column. And you see, notice the distribution is like this. So this is a good predictor of this y. But let me understand in precise terms, what is the relationship between y and x? I see that there is a relationship, but what exactly is that relationship? Precisely, I want that. That precise relationship between y and x will be your model, represented by a line in this case. Okay. The algorithm, what this algorithm will do is, it can find out multiple lines here. Multiple lines can be shown here, right? What the algorithm will do is, it will start with some random m and random c. Y equal to mx plus c. Y equal to mx plus c is the expression. Hey guys, I'm talking to you, not to them. Y is equal to mx plus c. So by changing m and c, whenever I change m and c, the relationship between x and y changes, which means the line changes. The line represents a relationship. So whenever I change m and c, the line will change. Okay? This algorithm will start from some random m and random c. And it will evaluate the different possible lines before it finds what is called the best fit line. Okay. Now, what is this best fit line? Amongst all the lines possible that it has checked, best fit line is that which goes through the maximum number of data points. It can't go through all of them. It goes through maximum number of data points, and at the same time, it minimizes the distance between other points and the line. The distance between other points and this line, this distance, you see the distance over here, this distance is called error. What it means is, for a given value of x, your line says the value of y should be this, but your data available in your data set is saying the value is this. The blue line here is the predicted values for the different x. Actual values are the black dots. So whenever you have a black dot above the line or below the line, that means there is a difference in prediction and actual. That difference is called error. Okay? Don't mistake the word error. Error doesn't mean anything negative, but it's used for something that you already know. I'll tell you what it is. So amongst all the different possible lines, there will be only one line which minimizes the sum of all these errors. If I sum up all these errors across all the data points, the minimum sum error will be given to you by only one line. That line is called the best fit line. The algorithm will find out for you from infinite number of possibilities the best fit line for you. It's like looking for a needle in a haystack. And to do this, it makes use of a process which is called the gradient descent. All algorithms use under the hood a learning process, a process which they make use of to find the best model for you in the given data set. That process in this case is called gradient descent.
So the errors that we're talking about, basically that will be very significant to what our alpha level is.
What is alpha level?
For example, if I'm taking that as the level of significance that I'm taking, I'm deciding for business, that I can have maybe 5% of errors there and there. And 95%
You're talking about type 1, type 2 error. That comes in classification. This is regression. However, the same concept will come into play here also in a different way. I'll tell you what that way is. Yeah. So we'll see that way. So again, once again, you have to park your question. We are too far away from those points, right? Shall I move on? Any questions? Yeah.
So the number of points is the priority to the distance is more than the number of points, right? Distance, there are two things you told: the maximum number of points it should go through, and also the distance. But the distance is the most priority because the errors will be less.
Yeah, error will be less when the points sit on the line, no? So it has to be taken together. Both of them are equal priority, but there's only one line which is satisfy that condition. The driving condition is the error should be minimized. That is only condition, okay? So there are no two-step process here. It's only one step. So let me explain this to you. If I plot, okay, equation of a line is y equal to mx plus c. I'm going to take one simple case, mx plus c, where in your original mathematical space you have x, you have y. One independent variable, one dependent variable. Okay. So now we have two parameters that we can modify, and whenever I modify m and c, I'll get different lines. This is m1 and c1, this is m2 and c2, this is m3 and c3. I'll get different lines. Each line has its own m and c, right? But not all lines are good lines. So if I have this line, for example, this is L1. If I take the L1 is made of M1, C1. I see that many of the data points are away from L1 on both the sides. So the error E1 is very high. If I take, say, the next one, L2, I'll call this L2. I call this L2. I see that L2 has its own slope, its own this intercept, and it also does a lot of errors, but not as much as E1, E2. I try out various lines, then I come to LBF, best fit. Best fit line is this, which has its own M, best fit, C, best fit, and E, best fit. And of all these errors, this will be the least. E, best fit, will be the least. Now the question is, by changing my M and C, but just a small minute amount, I'll get a different line. So there are infinite lines possible, which you will have to evaluate. Out of the infinite lines, you have to find the best fit. Brute force will not work here. You can't use brute force.
So when you talk about gradient descent, right? Say I'm actually trying out, or say I started with a particular MNC, and slowly I moved on. I'm correcting my errors, so errors are getting reduced. All of a sudden, it again started increasing.
That will not happen, right? Except for when you cross the best fit point.
I'm coming to that now. Okay. So instead of looking at this mathematical space, I can actually look at another mathematical space, which is related to this. that mathematical space is between M and C, and this dimension is error, where error means sum of all the errors put together. Okay? In linear regression, this error is calculated as y hat, that is predicted value of y, minus y actuals, okay, raised to power 2 divided by n. N is the number of data points. I is equal to 1 to n. We call it squared error, sum of squared errors. Sum is sigma, squaring the errors. So the error done by model is nothing but a sum of squared errors. N is the number of data points you have. Isn't this formula for variance? So error is nothing but variance. How data points vary, scatter across the best fit line. The lesser the variance, more reliable the central value is. The lesser the variance of the points across the model, the better the model is. Same concept comes to you in a different way. So sum of squared errors is nothing but variance, variance of the data points across the model. So I want to find that model where the variance of the data points across the model is the least.
So slightly confusing. See, when you say covariance, right, and you said like if you have more value of covariance, then it is better for dependent versus independent. Right?
More value of R.
That is not
R is measurement of degree of covariance.
Okay.
Okay. The stronger the R is, the better the predictor is.
So degree of covariance should be higher, whereas variance should be lower.
Variance in individual dimension should be low.
That is comparing with some other box model.
That is also
always we are we are omitting the outliers and all. So in the data which we are collecting, we are removing the outliers. It will always in the like a group of data which is affecting the some model. So always it will be in the linear model, right?
Yeah, I didn't get your question. Come again. Yeah, you said box plot, you identified outliers, you removed
So
outliers.
we are removing it. So we are collecting the data which is affecting, which is going to affect the model. So if you are plotting in the any linear regression model, it will be always in the linear model.
Not necessary.
Even if we can have outliers, maybe some points on the
Varun, I'll take your question. I'll just hold on a minute. I'll take the question here. Within 1.96 standard deviation on this side and this side, the data points might still have noise in them, which causes a spread across the model. You're talking about outliers, which is lying 1.96 standard deviation greater. So by removing that, yes, you're cleaning the data, but within the 1.96 standard deviation, still you have noise. That noise will appear as scatter around the models. It will appear as variance around the model.
But once we are omitting the unwanted data, so it will be in the like linear regression model, but with some noise.
It will never be one single line kind of thing.
Actually, no, you have asked a very, very important question, which I will just answer this because this is a very important question which will be helpful down the line. Just hold on a minute. I'll answer the question first. Okay. Now, if I take any axis, any variable x, it has a spread. Okay. This spread, variance, what you call variance, there are two types of variances. One is called stochastic variance, which means nothing but probabilistic variance. The other one is called deterministic variance, which means variance that happens for reasons that I know. I know why that variance happens, okay? That is called deterministic. But variance also happens in your data set for reasons that I don't know. We call them noise. Okay, that is called noise, all right? Now, if I have a plot like this, a linear model, and I have distribution of the data points around this, okay? For a given value of x, now look at this. Actual value is this, in your data set, but the model is saying it is this. Similarly, there's another actual value which is this. Why is this variance occurring? I don't know. I don't know why that variance is occurring. This is called, I don't want to use the words right now, I'll use it down the line. This variance that you see, for a given value of x, you have multiple values of y, but they're very close, but still there is a variance in them. That variance is called stochastic noise. Okay? For a given value of x, the fact that value of y is spread around its central bar, this is deterministic. We know that this is going to be this way. All right? So when you address the outliers, outliers is something which is lying 2 standard deviations away or 1.96 standard deviation away. You're addressing the outlier, okay. But you're not addressing the random variance which exists in the data points within the 1.96 standard deviations. Those will cause a scatter of the data points across the model.
You were talking about the real actual data point or the prediction point?
Prediction is your line. Actual is the black data points. Between the actuals and line, there is a gap. That gap is my stochastic. Unexplained variance. I don't know why it happens. Yeah, in the actual data. Deterministic is, I already know my y bar has this spread and my x has this spread. This spread is also variance. I already know it has this spread. I know it will be like this only. I have no reason for worrying about that. What I'm worrying about is, for a given value of x, why are there multiple values of y?
That is stochastic. We don't know why it happens. That is what we call noise.
Is it because of lack of domain expertise? Nothing to do with
even the domain expertise will have this problem.
So when we have a multi-dependent variables, right? So here we are talking about trying to find out the only one and then y. Okay, but maybe when we are we have to analyze it in the togetherness
multivariate analysis.
Maybe that is creating this kind of noise because we are trying to target on a single one, right?
That can happen. That can also happen.
When the different variables actually interact with each other, there's collinearity in your data set. You can have trouble with this noise. That can happen. The noise may get cancelled out, or the noise may get magnified.
What can happen?
One more question. So we are looking for best fit line which give us the least error.
Least sum of square errors.
What is the definition of least? Mean
I'll tell you what is least. That's what I'm going towards now. Okay. So I have different combination of M and C. So I moved away from my original mathematical space into another mathematical space where the dimensions are the different slopes and different intercepts, different lines. Okay. Each line gives you some error. Okay. The formula for this error is the sum of squared errors, which is nothing but variance across the line. Whenever you have a squared term, this is called quadratic equation in mathematics. All quadratic equations, they have a property. The property is called, they are convex functions. Convex functions means when you plot them against their independent variables, M and C, they will always acquire a bowl shape. 3-dimensional bowl. Such functions which acquire this kind of a shape, a bowl shape in the 3 dimensions, such functions are called convex functions. They are guaranteed to have one absolute minima. Parabolic structure. One absolute minima. So for some combination of M and C, I'll get the least error. That combination of M and C, which gives me the least error, is my best fit line. So the algorithm will start from some random M and C. So maybe this is the random M and C. This is my random M and this is my random C. When I use this, I get a line, but the sum of squared errors across the line is very high. So each point here is one line in the original mathematical space. So in the original mathematical space, between X and Y, if this was my L1, maybe this is the L1, it had some M and some C. That M and C is this point represents this line. This line had some sum of squared errors. The sum of squared errors is this.
So you talked about 1M, but if it is multiple M, still it will be like similar?
Still 100%, guaranteed.
Okay. But we can't visualize.
We can't visualize. Okay?
All right, no kidding. Let's move on. Now what this algorithm does is, it starts from some random MNC and it uses a concept called gradient descent. Descent, as the name suggests, we have to descend. Okay, gradient descent algorithm, which internally makes use of what is called partial derivatives. Partial derivatives. And this term partial derivatives, I'll tell you what it is. It's not a rocket science. It is dy by dx. It's exactly dy by dx. What it does is, for a small change in m in this direction or this direction, for a small change in m in this direction or this direction, from the first m, the random m, for a small change in m in this direction or this direction, dx, how much the error drops or increases. So when I change it in this direction, I'm going further up, the error increases, dy increases. Whereas if I go in this direction, I reduce my m, my dy decreases. So it notes down that I have to move in this direction. But you have taken only m right now. How about c? So do the same thing with c. If I increase the c slightly here, what happens to my error? If I see it slightly here, what happens to my error? I'll go in that direction where my error decreases, descent. So using this concept of partial derivatives, which is nothing but dy by dx applied on individual dimensions one at a time, that's why it's called partial. It finds out, it moves from this line to the next line to the next line to the next line until it reaches this point. At this point, what will happen is, whichever direction you move in beyond this, the error is only going to go up. Whether you go this side or that side, error is not going to come down further. So it realizes that it has reached the global minima.
This is your best fit line.
Which is the relation between M and E plus C.
Correct. M, C and E put together. This is the best fit line. That best fit line happens to be this line, BF.
So it does not evaluate infinite lines. It uses this gradient descent concept and finds out for the next best fit line, next, and reaches the global minimum.
So is there a chance of jumping that?
Yeah, there is.
And there can be local minimas as well in case of...
Not in quadratic functions.
So in linear regression, we'll never have local minimas.
You'll never have. If you use neural networks, you can get stuck in local minimas.
Okay.
Linear regression, the error function being quadratic, it guarantees you will reach absolute minimum. Okay, but in the process of jumping, there is something called learning step. Okay, we are too far away from this, so I'll just tell you the concept, which is used along with this partial derivatives. If the learning step, the amount of change that you do in dy and dx, if the learning step is too high, you might jump and oscillate. You might jump the global minima, go on the wrong side, and keep oscillating backward and forward, infinite loops. So the learning step is adjusted. As it keeps jumping down, the learning steps become smaller and smaller. There are various ways of handling this to prevent the oscillation. One of the ways is, as you jump towards your objective, the goal, the steps become smaller and smaller. This algorithm is called bold driver algorithm, which is part of your gradient descent, one variant of gradient descent. When you do deep learning, this partial derivatives will become very important for you to understand how the neural networks work, how the back propagation of errors happen. Those things will come into play. Okay, but we still have a lot of time before we reach there. So hopefully I'll spend some time on this one day and tell you what this is.
Both in bold driver as well as gradient.
Yeah.
In both we can.
Yeah, you can. Yes.
But you have various other algorithms now which have come up, which is apparently better than this. Okay, we'll talk about those things down the line. Shall I move on? All of you? Okay. Your questions are still parked, right? The two questions. What are those two questions?
One is the standard deviation, like one is talking about error data.
He doesn't.
So basically the first one was the collinearity between that got answered. Okay. Within the variables, within the set of the dependent variables, why there should be no collinearity.
Why should there be no collinearity? What happens if there is collinearity? That was one of the questions which came up. I remember that. Good. So my strategy worked. Okay, let's move on. We'll discuss those things in detail, right? Okay. So keep in mind, we are looking at these data points closely. The distance between the actuals and the line is the predicted values. For a given value of x, the predicted value of y is the blue line. The distance between the actual, which is shown by the black dot, and the line, that distance is shown by yellow dashed lines. This distance is a measurement of error. Okay. The objective is square of these errors, all these errors squared, that sum should be minimized. Okay. Which is not very difficult to conceptualize once again. So if I have my linear model drawn like this, best fit line, the data points are scattered around this. You look at the data point from this angle. When you do that, you will see a spread. This variance is called sum of squared errors, which is nothing but xi minus x bar. X bar here is your predicted lines. So formula remains same. That variance is called sum of squared errors. That variance we have to minimize. The minimal the variance is, the better your model is. All right. So let me explain this to you, because you're going to come across these terms down the line. So let me explain this to you in slightly more detail. We're looking at this model, and the distribution of the points, the red points is given to you. The blue lines are x bar and y bar. And keep in mind, your model, the best fit line, will always go through the point where x bar and y bar meet. Always. Okay. Now look at this. Don't worry about these terms. It's all, not very difficult to conceptualize, visualize. What happened? Yeah, there you go. Now, if I take the red point is the actual point in my data set. So in your data set, in your data frame, there is a record with value of x, and its corresponding value y is red, the P1. But the model, the best fit line, says the value should be yellow, P2. The distance between P2 and P1, this is what we call error, the variance. This is what we call sum of squared errors. Okay. I'm showing you only one data point here, but you have to imagine there are multiple data points here. Sum of squared error applies all together. Okay. So this contributes to the sum of squared error. There is another term that we use, which is called total error. Total error across all the data points put together. The total error is nothing but the difference between y bar, the expected value of y, and the actual value of y. In your data, there is a distance between the actual value of y and the predicted value, the expected value of y. Expected value is y bar. That distance is called total error. Of the total error, your model has captured this much. Your model is a regression model, hence the name given to this is regression error. Of the total error, your model has predicted this much error. Of the total error in your data set, your model has predicted this much. The difference between predicted and the y bar. This distance is called regression error. What it has not been able to explain is this. This is called sum of squared errors. Sum of squared error has another term which is called residual errors. Residuals are those things which we don't have a reason for. We don't know why they occur. They're called residuals. Sum of squared errors is also known as residual errors. So when you build these models, especially when you go to your deep learning part and all these things, you'll come across these terms. Total error is the distance between your actual data point and expected value. Okay? So if the average height of this class is 5.5, the difference between your height and 5.5 is the total error. Now you built a model to predict the height of a person in the class based on the characteristics of the person. So your model predicts some value for you. So the model predicts the height to be 5.3. Your actual height is 6. 6 minus 5.3, that is 0.7. 0.7 is the distance between, 0.7 is this distance. Your actual height minus predicted height. Right? The distance between your height and the class average, that is the total error. Okay? So you'll come across three terms: total error, sum of squared errors, and regression error. Keep in mind, regression error and residual errors, these two together is your total error. And don't mistake the word error. Error means variance. Error means variance. Of the total variance in your data set, I told you one part of the variance is caused by the deterministic, the other part of the variance is caused by the stochastic, non-deterministic. Same thing. Non-deterministic is your residual errors, sum of squared errors.
So also you told this, see, total error or regression error, what a residual, is particular to particular point, right?
No, in this case, I'm showing you only one point, but you have to imagine all the points together because this SSE, SSR, they're across all points put together. What I'm saying is what contributes to SSR and SSE. That's what I'm showing you. So you have to imagine all the points here. That becomes too cluttered. That's why I'm not showing that. What contributes to SSR, what contributes to SSE, that's what I'm showing over here.
So least error is belonging to SST, right?
Yeah. Least error is belonging to SST means?
I mean, we are talking about total error.
Total error is this. I want to minimize this. Unexplained error. That is what my objective is. The gradient descent works in finding the best fit line for you, where best fit line is that line where this error is minimized. Because I don't want a model which is not able to tell me why. I want a model which tells me why this error.
So you will not try to reduce the regression error?
No, we will not try. We will not do that. Because that is deterministic. I know why it happens.
It's because of the variance of the...
It's because of the natural variance in the process. Okay, when you're running a process, many things come into play, factors come into play, because of which the values change here and there around the expected value. That is okay with me. But for a given value of input, there are multiple values of y that I don't understand. So for given value of input, there should be only one value of y. Why are there multiple values of y? That I don't understand. That part is my unexplained error. I want a model which unexplained error is minimized. I don't want a model where unexplained error is very high. What is the use of that model? It will not predict anything.
Okay.
When you say given value of x, you have one value of y. So in this case, in this case, the P2 is that one value. That's what you're talking about.
P2 is predicted value, but you have multiple values of P1s spread around the line. That gap is unexplained. That variance is what we call stochastic, random variance. We don't know why it happens. So basically the idea is to minimize SSE, that's all. The bottom line is minimize SSE. So increase the SSR to SST ratio. That is what our objective is. Yeah. All right, let's move on. So before you build the model, you have to evaluate each independent dimension and see what is the R value. R value, coefficient of correlation, comes into play to help you identify good predictors given the target. Okay. Once you build the model, I want to see how good the model is, how reliable the model is. For that, we use another metric. That metric is called coefficient of determination. And this is represented as R square. But before you jump to it, I should caution you, R square is not always R into R. R is a coefficient of correlation. So natural to think that R square will be R into R. That is true only when you build a simple linear model between one dimension, one target. It's only true at that point. In multi-dimensional, multivariate analysis, where you have more than 2-3 dimensions, you can't say R square is R into R. Okay? So R square is just a symbol which represents another metric called coefficient of determination. How much of the total variance in your Y has been explained by your model? Keep in mind, the total variance in Y is consisting of two components: deterministic, non-deterministic, stochastic, random. How much of this total variance in your Y has been explained by your model? That measure is called coefficient of determination. Obviously, a model which explains maximal of the variance in Y, it leaves behind very small residuals, that model is the best model. So R square, it ranges between 0 and 1. 0 means your model is not able to explain anything. Absolutely useless. 1 means your model is able to completely explain all the variance in your target. There is no residual. Such models don't exist. We can never build such models. Usually R value will be between 0 and 1. The closer they are to 1, the better the model is. Because in simple linear models, it's a squared term, it can never be negative. But keep in mind, in multivariate analysis, it's not just a square term. It's something more than that. So it'll always range between 0 and 1. Are you all okay?
How much variance in Y is like?
If say this is 0.8,
that means your model is able to explain 80% of the total variance in your Y. Total variance, which includes stochastic and deterministic. Right? So your R square should be as close as possible to 1, your model will be good. So this metric is used to evaluate the performance of the model, while R is a metric which is used to evaluate the independent dimensions when you're building the model. Geometrically, okay, if you take one simple linear model of one X and one Y, okay, that's what I'm showing here. So this is where your X bar and Y bar meet. Please look at this carefully. This is my Y bar, this is my X bar. Okay, so there is an actual data point. Xi minus X bar is this, Yi minus Y bar is this. That gives us an area, a rectangle. We saw that earlier, right? That area represents the total variance in your data point. The total variance in this data point, the covariance in this data point because of X and Y. This is that area, the light gray area. The light gray area is this. It's behind this dark gray. Okay, the light gray area is this. That light gray area is a geometric representation of the total variance because of X and because of Y in this data point. Of this total variance, for a given value of X, your model is predicting a value of Y to be this. So this predicted value of Y minus Y bar, X bar, this dark area is the explained variance. How much of this total variance has been explained, captured by your model? R square is the ratio of the dark area to light area. What you're seeing on the top, this is the residuals, unexplained variance. So R square is again a ratio, where the ratio is between the total variance in the data points and the variance explained by your model. That ratio is called R square. Obviously, the lesser the residuals, unexplained variance, the better the model is.
So we want more R square.
Yes, exactly. But there's a problem. There's a problem here. The problem I can explain to you in simple terms.
The problem is, go back to our discussion on R, where I told you, if there is no relationship between these two, the target and the independent variable, you have to get a perfect symmetrical distribution. But the probability of getting a perfect symmetrical distribution is 0, which means you're going to get some asymmetrical distribution. The moment you have asymmetrical distribution, your R value will be greater than 0. Magnitude, this way or that way, which means R square will be greater than 0. R square is not considered as a very good metric for evaluating the models because it is easily impacted by fluke relationship. So we make use of another metric that is called adjusted R square, which is nothing but R square minus fluke. There is a formula for this. How do you find out the fluke content? Which I am going to avoid right now because it's too detailed to discuss. In case you're interested, let me know, I can share it with you. Conceptually, it's easy to understand, but the argument is very lengthy. We won't have time for that. That's why I'm going to ignore it right now. So the metric that we'll make use of to evaluate our models is adjusted R square, not R square.
But in real time, we don't calculate this fluke.
We do. It calculates, algorithm does automatically.
Automatically. We do.
Okay. We know.
The beauty of adjusted R square is, whenever in your model building exercise to predict your target, when you include useless variables which don't really have any significant impact on the target, but their relationship is statistical fluke. When you use such useless variables, R square will keep on going up and up and up. It will come closer and closer to 1. But adjusted R square will go down. It will decrease. So when you include useless variables in your model, adjusted R square will go down. It will reduce. Whereas R square is likely to go up. Adjusted R square will go up only when you include good variables in your models. Good variables are variables whose relationship is significant, strong. So we use adjusted R square for evaluating our models. One thing that you need to keep in mind, conceptually get it clear, any attribute that you use in your model building, any attribute, that attribute will always have both the components, good R and fake R. It will have both the components. But in a good attribute, the percentage of this will be very, very high compared to this. In a poor attribute, useless attribute, percentage of this and this will be almost similar. That is why when R value is close to say 0.5, 0.6, part of it will be caused by fake R, part of it will be real R. How much is real, how much is fake, I don't know. That's why it calls for further investigation before you decide to use that in your model. When R is close to 0.5, 0.4, 0.3, we don't know how much of that is fake, how much of that is real, we don't know. That's why you need to further investigate.
Before you include or exclude from your models.
How we get the explainability of the fake? What is actually causing fake?
Randomness in your sampling techniques itself will bring in fake.
When you use random function to sample from population, since you asked this question, whenever you do sampling, any technique you use, clustering, layered sampling, mixed sampling, whatever you do, Your sample will never be a true representation of the real population. It will never be. So its distributions will be slightly different from the distributions in the population. That change in distribution is what will introduce fake R's.
So only sampling which introduces fake?
Sampling is the source of this.
Okay.
Did I show you that video where I showed you universe to be under flux, continuously changing? It's never static, whereas your sample is a snapshot.
A frame in the video.
Variance error and this error keep changing.
It will keep changing, right? Shall we move on? Okay.
I'm just taking you through the concepts. I'm not telling you what is the formula for all these things. They'll become too heavy for you right now. But I will eventually take you through in case you're interested. Some assumptions that this linear regression models make. We already discussed this. Assumption of linearity. The relationship between the target and the independent variables are expected to be linear. Oh, that brings me to another point. Please be careful. When your R value is close to 0, what does it mean?
Okay, I think that's what I ended up saying.
There is no linear relationship between x and y. Okay, when R value is close to 0 between y and x, that means there is no linear relationship. That does not mean there is no relationship. For example, if I give you a distribution like this is x and this is y and this is parabolic. There is no linear relationship. When you find R value for this distribution, it will come close to 0. But they are related. There is non-linear relationships. So whenever you do this analysis, R value is close to 0, go back and check your pair panels, pair plots. Is the relationship non-linear? If the relationship is non-linear and you're building a linear model on that, you're doing a mistake, a fundamental mistake. Okay? Same way, if you have a distribution like this, R value will come to 0. But there is a relationship between y and x, A sine omega t. A is the amplitude. Sine theta, you know what theta is. So when R value is close to 0, that does not mean there is no relationship. It means there is no linear relationship. If you have such attributes in your dataset, then you may have to think twice before you use linear models.
So unless we draw this pair plots, right, we will not come to know that we have this kind of non-linear relationship. So is it always suggestible to draw pair plot for each?
100%. If you ask me, I'll always say pair plot is the most important tool you have in your toolbox, which you should use to understand your data.
And suppose we got some pair plots, so we should not try those attributes at all for the model.
Try a different model, maybe a non-linear model. Okay. So now that brings me to a question: what is linear and what is non-linear? Okay. Now look at this. This is slightly funny and at the same time something which is actually serious. This y and x, okay. Mathematicians will say, if suppose this is x, this is y, and the expression is y is equal to x square. Mathematicians will say this is a non-linear function. Data scientists call this linear function. Okay. What we can replace this with some value k, so y is equal to k. So I can convert this into a linear and then build linear models on this. So when you build linear models, y equal to mx plus c, the reason why they're called linear models is these coefficients, they are not raised to the power. They're raised to the power 1. That's why they're called linear. They're linear in terms of coefficients. If I have a model like this, y equal to mx square plus c, for us, it's a linear model. Okay, so don't get confused with this. A lot of mathematicians will say this is not linear, but for us in data science, scikit-learn or R, this is a linear model. It'll show us a trend. you'll see that if you do an auto MPG case, in auto MPG case, MPG is the target, and your X is a weight of the car. You'll see that the data points are scattered like this.
You can still use linear model on this. You can still use a linear model on this.
So if R is close to 0 and if my scatter plot showing quite dispersion, so in that case I can say it's a real one. So I can remove it.
Yes.
But if R close to 0 and if there is some parabola kind of thing, in that case.
Non-linear models you might have to go to. Non-linear models are models where these coefficients themselves are complex coefficients. They are not simple coefficients. They are not simple ratios. They are something like e raised to power I theta and all those kind of things will come over here.
If we have in multi-independent variable case, if one is showing linear relationship, other is in that case.
So you'll have to try both, build a linear and non-linear, see which generalizes. Finally, what is the objective? Objective is it should have minimal bias variance errors. Which one gives you that minimal bias variance error? Put that in the picture. Combo is what we call ensemble techniques. In production, we never put one single model into play. We always put a multiple models grouped together in a play. We always install multiple models put together. Varun, good morning. No problem, sir. That's okay. Camera is facing me, not you. It's okay. All right? Okay. But don't knock the camera off here. He is also sleeping. Right? So what we do is, have you seen this Kaun Banega Karodpati? Have you noticed that the audience never go wrong? Though the audience individually may not have very high IQ, but put together they rarely go wrong. This concept is called wisdom of the crowd. The same concept is used in data science also. When we productionize our models, we don't put one single model into play. We always put a collection of models into play. That is called ensemble. The algorithm assumes that there is a linear relationship between independent variables and the target variable. It also assumes that there is no relationship between the independent variables. That all algorithms do. There's nothing particular about this algorithm. Assumption of normality of error distribution. This algorithm assumes that the model that you build, the best fit line would be such that the variance around the best fit line will have normal distribution. What do you mean by this? If this is my best fit line and the data points are scattered around this, and when you look at it from this angle, it will have a normal distribution. This is not guaranteed. Sometimes you end up with the best fit line, and the best fit line you might see a distribution like this, more errors on the positive than on the negative. This happens when you have outliers in your data sets. This algorithm, all algorithms will go down on their knees when it comes to outliers, but this particular algorithm is prone to outliers. If you have an outlier somewhere in your data set, the best fit line will get pulled towards that. It'll get pulled towards, it'll gravitate towards the outliers. Okay? So when that happens, the best fit line that you get, the MNC that you get, that MNC may not be the right M and C for reproduction. So model may perform poorly there. Okay? So when you build up models, linear models, any model, the first thing we have to do is handle the outliers first. Okay? There are various ways of testing this out, whether this is happening or not. One of the ways of testing this is you do a scatter plot between the actual values of y and predicted values of y. Okay? Between actual values of y and predicted values of y, since the data is spread around the best fit line, there should be no correlation. The distribution to be scattered like this. Predicted value of y, actual value of y, there should be no correlation between them. When there is no correlation between actual and predicted, that means your data is evenly distributed across this best fit line. Sometimes you might notice there is a trend in these errors there is a trend, some kind of a trend. In the difference between actuals and predicted, there are trends, which means there is a trend in the residuals. As the value of x increases, the residuals increase in magnitude. When you see such trends in the residuals, that means there's something not correct with your data sets. Maybe you're having outliers, maybe you're building models on non-linear data sets. Those are kind of things which will come out. I don't know whether you heard this word, homoscedasticity of errors. Homoscedasticity, heteroscedasticity, there are two things that will come across in statistics. What it means is, as you build a model, the errors should not spread out like a cone. The spread of errors across this model, for all the range that you have, the spread should be more or less uniform. Sometimes you will see that as the value of x increases for the best fit line, the magnitude of the error increases. The spread is still normal, but the magnitude of errors, residuals, for higher value of x is different from the magnitude of errors for lower value of x, the independent variables x. Such things indicate heteroscedasticity, homoscedasticity. The expectation is it will be homoscedastic. Homo means homogeneous. Okay, so the residuals, irrespective of what the range of x is, will be similar across all the range. Assumption of independence of errors. I mean, error done in one record is no way influenced by the error done in another record. Error done on one dimension is no way influenced by the error done on other dimension. The dimensions are independent of each other. That assumption is what is usually violated. But still, we go ahead and build our models. I found a very good site which discusses these errors. I've given you the URL here. By any chance you've done this Darwin-Watson test, statistics? You've done statistics, right? The inferential and descriptive statistics. Inferential statistics, you would have done z-score, z-test. You've done all the t-tests and all these things you've done, right? Okay. If you've done those things and if you remember those things, maybe you would like to visit this site. A lot of information. Please expand your horizons. Go beyond what we teach you in the class. It's just not possible to teach everything in the class for the time limit. So go beyond whatever we teach, expand your horizons. Yeah, that is what will give you a very firm, sound footing into data science, and you'll be able to face situations confidently. So wherever I come across any URLs, any articles, I'll share those things with you on the slide. Advantages, we are still not out of the woods. There's still much more to come. We're not yet learned the full stuff, but we'll do a hands-on and then we'll see the other stuff. Advantages is very simple to implement, and it's easier to interpret, provided the number of dimensions is less. So when I have equation like y equal to m1 x1 plus m2 x2 plus c, I can give a physical meaning to this. I can say for every 1 unit increase in x1, how much y changes, that is given by m1. So I can physically interpret this. I can give physical meaning to this equation. You can't do this in all the cases. You may not be able to do this. Suppose you are using neural networks. You can't interpret those models. You don't know what they are. They're all black box.
Sir, what do we mean by physical definition?
I can convert this, whatever this formula is telling me, I can map it to English, right? I can tell you in day-to-day language what it is telling you. I won't be able to do that if I use, say, random forest. You're going to do ensemble where you'll do random forest. Random forest is a black box model. We don't know what it's actually doing inside. Support vector machine is a black forest. We don't know what black forest. Black forest is a pastry. Black box. We don't know what it's doing inside, right? This model is a white box. Outliers can bring it onto its knees. This particular model is prone to outliers. All linear models are prone to outliers. Decision tree is not prone to outliers. And this is a very important point. Since the linear model goes through the point where x bar and y bar meet, the best fit lines, the lines evaluated for you go through where the x bar and y bar meet. If your x bar and y bar are not reliable, then your model itself will not be reliable. So if I built a model on a dimension y and x, where this is a very large spread, the x bar is not reliable. When x bar is not reliable, how will the model which is going through the x bar, making use of this x bar, how will the model be reliable? Right? So the more time you spend in selecting your attributes to build the models, the higher the quality of the attributes that you use to build the models, the better your models will be. And the last, boundaries are linear. This is a problem not in regression, this is a problem in classification. Okay, so if we can use linear model for classification also. So if you're having a distribution of classes like this, okay, and then this, and you're trying to build linear classifiers, you'll get probably a line like this as a best fit line. So above is this triangle, below this is circles, and one triangle is. Whereas on the other hand, if you have made use of non-linear stuff, non-linear models, then probably you would have got a better result. Maybe you would have gotten something like this. Okay, so if you use non-linear models, it might do a better classification than linear models. So this limitation is not in regression, it is in classification. Let's do one hands-on. Okay, the hands-on is not AutoMPG dataset as it is given here, it's the other one, which is simplistic. So we'll start with simpler ones. The other one which I've given to you is CAR. Okay, CARPA is linear regression. I've taken the dataset directly from the UCI site. It's called imports_imports-85.data. This is the name of the data file. Okay, so instead of downloading it, I'm directly reading from there. So let me begin. Matplotlib is an instruction to the Jupyter notebook to make all the plots in the notebook itself, sorry, Jupyter server. I'm importing Pandas, NumPy. And from scikit-learn linear model libraries, I'm importing the linear regression. You can have linear classifiers also. Then I'm reading the CSV file which is available in this URL. It's a comma separated file, and I've taken all these column names from the UCI dataset. So that gives me the data frame which I call car_df. This is my data frame. All of you okay? So this is like loading a data into a table. So let's look at two records. Transpose is not a must, but since the number of columns is huge, I put a transpose. I'm seeing first two records, record 0 and record 1. There is obviously missing data in some of the columns. And there is string data types in other columns. Fuel type, gas, it's a string data type. Number of doors, 2, it's a string data type. All right, no problem, go down. Our objective is to predict the last column. Given all these independent variables, can we predict the price of the car? Is there a relationship between price and all these variables? That is what we want to find out. What is that relationship? But before we do that, look at the data types. Many of the data types are object. Object means string. Machine learning algorithms cannot handle string data types. They have to be converted into numbers. So what I'm doing here is, I'm going to convert into numbers. But before I convert numbers, I'm dropping some of these columns. The reason I'm dropping these columns is, if you go and take a frequency count on these columns, fuel type, for example, or engine location, for example, most of the records have only one value for this. This is called low variance filter. Look at all the data provided to you. In the data you have columns, where in the columns there is not variance at all. There is a gender column. Gender column, all the data is about males. then that column is useless. It's not going to give you any information. Such columns are called low variance columns. Though they are supposed to have multiple values, they have only single values, a few values. We remove them from the analysis. So when I did this,
so you would usually do this check and get to this conclusion?
Yes. You do frequency count, then you come to conclusion.
What I did is I've manually browsed the data file. This is an Excel sheet, CSV file. You can actually see, let's do it now, why are we talking? Let's do this. What you do is, go to this site and let's download this data set. Control C, okay. Now, HTTPS, double quotes. Thank you. Now we'll save this down. We'll save it as. Let's save it as text document, and then we'll load it up. I'll just call it. Okay, where am I saving it? I'll save it on desktop. Okay. Done. Let's open it. Okay. Let's start Excel. Excel is running into problems with C. Oh God. Oh, okay. Okay. It's going to clash with their recorder. So I'm not going to open this. Let's get on to this code, but do this analysis. You'll find that these columns are having low variance filters. They're fit to be kicked out. Right? So then what I do is I saw the car data types, the column data types. Most of the data types are object string types. I dropped my useless columns. Number of doors, most of them have 4 doors. Then fuel type, most of them are giving the fuel type as gas. Engine location, most of them is front, 1 or 2 is in the rear, so on and so forth. So once I dropped them, I'm still left with some object data type. Number of cylinders is object. And any other object data type? No, only that is object data types. Single value there, we're dropping it. Okay. Which means the current price of the car is not a function of that, it's a function of other variables. Okay, look at this. Hey guys, do you understand why we drop low variance filter? The reason why we drop low variance filter is the price is not influenced by this particular column which is low variance. If the price was impacted by this column which is low variance, then all the prices should be fixed. Right? Which means the variance in the prices is because of the other columns, not this column. So that's why we drop it. Now the number of cylinders, what I'm doing here is I'm converting all this into numbers. So wherever I come across a string called 1, I replace it with numerical 1, 2, I replace it 2, and so on and so forth. You should do this with care. Okay. You should do this with care. Suppose you had a column called gender and the gender was male and female. Then I cannot do this blindly like this. Because if I replace a gender, say a male with 0 and a female with 1, then I'm introducing an order in that column. That's called ordinal columns. 0 is less than 1. But there's no such relationship in the real world. So if you have a gender column, then I will use a technique called one-hot coding. One-hot encoding. I will use that technique to replace my strings into numbers. That example I have given you in AutoMPG dataset. Okay, you look at that later. Okay. On the other hand, if I have a column called income group, where they have income groups like low, middle, high. Now there I can go and replace low income group with 0, medium income 1, high income group 2. Because the same order which exists between 0, 1, 2 exists in that column also. Okay. So if your column is an ordinal data type, you can go and introduce order in your numerical values. If the column is not ordinal, gender column, then you cannot blindly convert them into 1 and 2. You have to resort to one-hot coding. In scikit-learn, there is a facility function called label encoder. Label encoder introduces order in your data. So be careful when you're using that. Instead of using label encoder, use one-hot coders.
All right. Everything has a but. Yeah.
Before dropping this variable, we have to convert it to level encoder or one-hot encoder.
Which variable?
We dropped all of the variables.
Not necessarily. Since we're going to drop, why do you need to convert?
Then how will we check the variance of this?
I manually check. Frequency problem.
I just did like car underscore def not really so it showed some of the values which have the integers, which are only integer or float.
Yeah.
I didn't check the character. That we have to convert to
that. If you want to do it here, then we'll have to convert.
Yeah. So basically you did the background job and then fine.
Shall we move on? Okay.
So be careful when you're converting your object data type into numbers. Don't end up introducing any order which doesn't exist. So when you use one-hot coding, have you all seen one-hot coding anytime? You're not seen one-hot coding? Okay, I'll tell you what one-hot coding is, then we'll move on. Sorry, you have a column gender, and the gender column has male and female, okay? This I cannot use as it is in my modeling. So what I do is I convert this into numerical data types. All data types should be numerical. So when I convert into numerical, I use one-hot coding. What will happen is, it'll replace this gender column with two columns, gender underscore M, gender underscore F. Okay. Wherever the record is M, you will have 1 here, 0 here. Wherever the record is female, you will have 1 here, 0 here. So this column will be dropped. In your data set, you will be left with this column. 1 and 0 will be stored on the hard disk or in wherever you're storing it as numbers.
Numerical values.
Okay. In last class we had used this category.
Can you just name this?
Yeah.
We used what?
Category or something.
Label encoder we used. We just manually converted. We didn't use that scale. Category. Last time we just converted to category and then we changed it to 0 and 1. But we didn't use level encoder and 1 or encoder.
Be careful when you're doing this.
The same column.
You see, level encoder is something like it will do a sequencing 1, 2, 3, 4, 1, 2, 3 as per the number. But what happens if you see like cities, let's say we count 2, 3 cities, it doesn't have 1, 2, 3. If you have like themselves.
Bore and stroke is right now object. So I'm dropping these data types. Okay. And here car data types, let's say again. Bore and stroke is still object data types. Okay. Here I'm converting my cylinders into numerical data types. And here I'm converting my data types into this thing, float. Okay. Guys, all of you with me on the cylinders? Till cylinder point? Okay. After cylinder point, what I've done here is based on the experience I had in the other data set, where there were missing values. In AutoMPG dataset, you'll see missing values. Okay, so what we do is, if we come across any missing values, replace it with nan. Nan means not a number, null values. Okay, so what I'm doing here is car underscore df dot replace wherever we come across with some question mark, replace with nan. But I didn't find any question marks in this dataset. The question marks were there in AutoMPG dataset. Okay, so we can actually delete this line. We don't need it. Then at this point, what I'm doing is, there are question marks there. Oh yeah, sorry, there are question marks there. Correct. We saw it here, right? We saw it here. Question marks here. Sorry, mistake. There are question marks here. These question marks now would be replaced with not a number, null values. Okay. When you replace question marks with null values, you can do numerical Python operations on it and convert into appropriate values. Okay, that's why we did this. Move on. My data types right now are, after changing the data types here, after dropping the columns here, some of the data types are still object. Object means string data types. So what I do here is I first convert my cylinder into numericals. Then I change my data types here. Look at this. Car underscore df bore, I replace that with as type float. I replace stroke column as type float. So I'm changing all the data types to float. Because many of these columns, let's say which column had that question mark, normalized losses. Normalized losses. It's already a numerical column, I think. Yes, it is already a numerical column. So I don't need to change it. There you go. It's already a numerical column, so I don't need to change it. Rest of the columns which are object data types, I'm changing into float types. Till this point, is it okay? Once I've changed the data types to numbers, numerical, I know there are many missing values. So the strategy I'm using here for missing values is replace the missing values of price column with the median of the price column. I want to explain this step to you. So I have a data frame, and in this data frame I have one column. This column is called price. In this column there are many NAs. NA. Wherever there are question marks, we replaced all of them with NAs. The question mark has been left behind by the data entry operator because when he was entering the data, he did not have values for those columns, those records. Okay. So we replaced question marks with NAs, all this became NA. Because now these have become NA, I can use the function fill NA. What this function does is, if you see that syntax, what I've done is find out the median of this column. Whatever values are available, using those values, find out the median. Replace the NAs with the median of this column. It is always safer to replace missing values with missing values with median, because means they are easily impacted by outliers. Mode is used in categorical variables. We are running with float variables. So we always replace mean or median, but we are not yet checked the outliers. All columns will have outliers. Mean get easily impacted by outliers. So if you replace these values with mean and go and remove the outliers, then these values will be completely incorrect. So replace with median. Median is not impacted by outliers, right? And the beauty of this is, in scikit-learn, I can find median of even an object column. The column is supposed to be numeric, but because it has question marks, the data frame is converted into an object data type. But you can still go ahead and find the median of that column. Why? Because median is physical central value. Mean is mathematical average. It's a calculated central value. You cannot find mean of an object data type. You can find median of an object data type. Right? All of you getting the difference? That is where the difference between Python and R comes. In R, I will have to first convert into numerical value even to find median.
So as a thumb rule, can we say that always it is median?
No. Now, how do you address missing values? Okay, how do you address missing values depends on your analysis of the data and why the values are missing. The values can be missing because of some random reasons. We call it randomly missing values. Values which are randomly, you don't see any patterns in them. They're missing values in all records in all columns, randomly distributed. Then we say that data is missing at random. There's no particular reason for it. Okay. Whereas there can be situations where the values are missing because of some reason. They're not because of randomness. For example, if you take income, usually you'll find nobody wants to disclose their income. So you'll find missing values in that income column, many of them. So depending on what is the reason for that missingness, you will apply different strategies. If it is income column where the values are missing because of the nature of the column, then I might have to build a sub-model, a model inside a model, where I predict the values of the income based on the other attributes available. So my domain knowledge will come into play, which will help me understand what are the other attributes that this income column is going to rely on, depend on. How can I guess it? So whenever I create such imputed values, as we call them, I'll create a new column, income imputed. So I will not touch the original column. I'll create a new column called income imputed, where all the data available is copied as it is, including the missing values, and the missing values are imputed from the other columns. That is one strategy. If your data is missing at random, then replacing the column with a median is the default strategy we use. Look at the spread of the data on that column. If you see long, thin tails, mean is not reliable. So we replace with median. Right? There is a package available called mice. It's available both in R and Python. In Python, it is available in another package called stats model. Stats model. Mice stands for multiple imputations through chained equations. Multiple imputations through chained equations. Yes. When you run this package on your data set, it will automatically try to replace the missing values in all the columns with predicted values where predictions will be based on the other columns. It will establish the relationship, it will see which one is strong relationship, it will go and impute. So one column's missing value might be imputed multiple times from multiple columns. Please go and read about this. It's a very powerful package. When something comes with power, you have to be very careful in using it. So read about this mice. I'm not going to cover it here, but it's a very beautiful package. You should read about this. And just to add to the confusion, apparently the mice implementation in Python is slightly different from mice implementation in R. Now they both call it mice.
Suggest a lot of things also. Low variance in automatic drop. Nice.
So these are the tools that you should be aware of, you should have in your portfolio when you start doing data science projects. All right, all of you on this? Shall we move on? Once I've done this, then I go and do my basic statistics, diff, describe. Describe is descriptive statistics, and you know how to interpret this? All of you are aware of this? Take any column, say height of the car. First thing you should look at is difference between mean and median. The mean is 53.72, median is 54, not a very big difference. 53.72 and 54.10, not a very huge difference to worry about. Look at the distance between the length of the left-hand tail and the right-hand tail. Left-hand tail is minimum minus first quartile. 47.8, let's take it as 48, 48 and 52, that's around 4 units. 4 units. Difference between this and this is again 4 units. So it's going to be a very symmetrical bell curve. The distribution is likely to be a symmetric bell curve for height. All right, I don't see any skew to worry about. Look at the car weight. Same story repeats here. 2555, 2014. If there is any column where the mean and median are very different, then you might be having a skewed data set. Look at this one, price. Now price is the target, forget the price. Let's see if our analysis stands. Let's see whether it stands. Okay. So this is numerical way, statistical way of analyzing your data, but instead you can do a pair plot. In pair plot, I always prefer to have the diagonals in form of density graphs. How do you get that? When you call the pair panel, you give diagonal kind is KDE, kernel density estimates. When you do this, you get the plot like this. Now let us spend some time on this. Always keep in mind, the output of the pair plot is a square matrix. It has as many rows, as many columns it has, okay? So this is rows versus rows comparison. So we have normalized losses, then we have wheelbase, we have length, so on and so forth. What I've done is from car df, I have taken using index locator all rows column 1 to 16. Yeah, column 0 is my column 1 to 16. How many are there here? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have not taken the price column here. So what we do here is, instead of doing this, you do this. You do this. Just comment this out. Okay. SNS.pairplot car underscore df KDE. You do this. We'll do this pair plot. Now we run this. So let's let it plot. Fortunately, it's coming out fast. Yes, sir. Got it. Now I want to make sure my price column is reflected here. We're going to predict the price, right? So price column is, I think, second last or something. Cylinder MPG. It's last but one. Why is it not showing to me? I'm not getting it. One second. I probably didn't. Car underscore df diagonal. Are you able to get the price column? No, it's there in the data set. It's there in this price. There you go. Car underscore df describe, it's there in this data set. But you guys are getting it? All right, okay. Let's look at that, okay? The first thing that you need to do is, when you do pair plot is, first thing that you need to understand is, first row and first column is same, second row and second column is same, third row and third column is same, so on and so forth, okay? And when I do a comparison of a column with itself, if I do a comparison of, say, MPG versus MPG, what kind of a plot will I get? Scatter plot? It will be a straight line. There will be no information here. There's no spread, nothing. So trying to do a scatter plot for a column with itself is useless. It's not going to give you any information. So whenever it comes to that point where you are going to look at a column versus itself, what they have done is, instead of giving you a scatter plot, they have given you a density curve. By default, they give you histograms. We have changed it to density curve. The advantage of doing that is, in R, if you do this pair plot, it will leave out the diagonals as blank. It will leave out the diagonals as blank. It will not show you anything there. Whereas what happens in scikit-learn is, they give you a distribution. Why leave it blank? Use it to show the distribution on that particular column. Okay. So that is why diagonals, you will see the distributions, how data is distributed on that particular column. Okay. So let's look at the diagonals. In the diagonals, in my case, first column is symboling. Honestly, I don't know what symboling is. Maybe I should have done that homework. Next column is wheelbase. Wheelbase is basically how spread the front wheel and the back wheel, the distance between them. Okay, we see a normal distribution except for higher values. Higher values, there seems to be some kind of a tail, doesn't look worrisome. Look at the length of the car, again almost a normal distribution. But we see some kind of overlap here between the, you see multiple Gaussians here, one behind the other. May not be of a concern right now because they're all kind of overlapping. Remember which was the column where we saw a perfect match? The central values, what is the column? Bore. Height. Height was the column. This is the distribution of height. So in distribution of height, now look at this, the distance between mean and median was almost very nil. And the tails were also equally spread. We were expecting a normal distribution, but unfortunately it's not normal. What it is showing here is two Gaussians, two normal curves are overlapping each other. Okay? This is what we call the mix of Gaussians. Go to the other columns, look at this one. This one has a long tail on the right side, a long tail. It also seems to have, but these Gaussians are ignorable, they're very small compared to the other one. Okay, so look at the distributions, and on the distribution part, on each one of the columns, some concern but not too much to worry about. You should never expect a theoretical symmetrical normal curve in the distributions. All algorithms assume that the data on the independent dimensions are distributed normally. Okay, that's all they assume. Apparently not so, but still it's close to normal, so I'm happy with it.
Can you explain the compression ratio, that one?
This one?
No,
this one? Okay.
Compression ratio you see here, this is compression ratio. And compression ratio, what I'm seeing here is, there are two different clusters in it. Two buckets in the data on that particular dimension. Okay. This is a clear indication of mix-up of Gaussians. When you build models, especially linear models, you should not mix Gaussians. Every Gaussian has a particular characteristic. What do you mean by Gaussians? Gaussians means distributions. Okay. So if on a particular dimension, you have two different distributions, you are talking about two different processes which have generated this data. Remember, in statistics, you would have done a t-test or a z-normal test. When do we say the two data sets belong to the same process? When they're significantly overlapping each other, the central values are not very far away from each other. If the central values are very far away from each other, likely that the two data sets have not come from the same source. If the two data sets have not come from the same source, how can we include them in one single model? What is a model? Model is predicting the behavior of the source, the process which generated the data. Right? What happens when you use mix-up of Gaussians like this is, you're going to find x bar. X bar is going to lie somewhere in between these two, which neither represents this nor represents this. But your linear model is going to go through the s bar, x bar. So your linear model will neither be good for this prediction nor will be good for this prediction. He has done some typo. Hence, a lot of typos sitting on the extreme end. This happens when you measure these terms in some fractions and he's either added one extra zero or something of that sort he's done, because of which you're seeing outliers cluttered together in one group. So I have to go and find out what are these records which is causing this long tail in this cluster. My hunch and experience tells me this is most likely a typo rather than data coming from two different sources.
Once the graph will be good.
Yeah, yes. This will be significantly good.
How will you identify proportion?
Go and put 1.96 standard deviation limit. Yeah, this is outliers. Outliers. So I can detect anything which is lying beyond 1.96 standard deviation on this dimension.
So I can identify this too.
But standard deviation will be given for the complete observation, right? But that includes data of the this
Doesn't matter. As long as they're beyond 1.96, they're suspect.
So when you replace those outliers with values, proper values, then your standard deviation will collapse.
I think cylinder is the best example for what you are explaining.
I'll look at this. Guys, since this point has come up, I'll discuss this. In your original raw data set, suppose it's distributed beautifully, you have outliers here. You do something about the outliers. You identify the records and replace all these values with the median. Suppose you do that. Okay. When you do that, you remove the outliers, replace all the values with median. Your curve will become sharper. When the curve becomes sharper, standard deviation decreases. When standard deviation decreases, the data points which are earlier not outliers, now they become outliers because your standard deviation is decreased. So 1.96 standard deviation for both sides has decreased. So new data points will come out as outliers which earlier were not identified as outliers. And this will continue to go on infinitely. So just handle the first level of outliers. Forget the second level of outliers. They're not really outliers.
Alright? Yes.
Generally, at -2 standard deviation plus 2, right? You mentioned 1.9.
1.96 because 1.96 covers 95% of the confidence level. Some people use 2 standard deviation. Some people even use 3 standard deviation. That depends on your, where it's a matter of life and death, and I want my model to be perfect as close as possible. That means I want my deviations to be very tight. Where I can tolerate some errors, my deviations can be low. Right? So it depends on your requirement.
Yeah, correct.
Because I'm 2 different clusters which I'm seeing here. But since the size is very small, my hunch is it's the outliers. And the outliers have been introduced through some manual problems.
Alright.
So in this case, it is good to treat the outlier, or we can just remove the error. We can remove the record. That's also one strategy.
Removing record is always the last option because you're going to lose so many other column informations when you remove those records. Row only, he's talking row. He's dropping the rows. So if you start dropping the rows for all columns where you have outliers, your data set might shrink.
Exactly. We have one in the last exercise. So what happened here, they were having a 30 attributes, breast cancer ones, right? So now every column except one, every column has an outlier. So when we are removing the outlier for every column, 569 records coming down to 237.
So that's not good.
That's not good.
So dropping records is always the last option when you have plenty of data. When data size itself is restricted, dropping records is not a good option. Shall we move on? All of you? Okay, let's move. So now, always start by analyzing the diagonals first, how the data is distributed on each column. This is my univariate analysis. This is what the output of DF describe is. How your data is distributed on that particular column. It's a basic statistic, it's a descriptive statistics. Next we do is bivariate analysis. In bivariate analysis, how these columns interact with each other. For example, if you look at this one, this is telling you interaction between the symboling and this one, wheelbase. By the way, in this square matrix, above the diagonal and below the diagonal, it's mirror image. Either you focus below the diagonal or above the diagonal. Okay, so let's take below the diagonal. So I know this first column is symboling versus wheelbase. What it means is, as the value for symboling increases, you see that the wheelbase trend is going down. Wheelbase is shrinking as symboling increases. Okay, but I'm also seeing a lot of noise. For a given value of symboling, there are multiple values of wheelbase. So between symbolic and wheelbase, there is a negative relationship. There is a negative relationship. Okay. Look at this. This is between symbolic and length of the car. Since length of the car and wheelbase are almost kind of related, you'll see a negative relationship here also, but not as well as in this case. Look at the relationship between symbolic and width is almost circular distribution. No significant correlation between the two. Right? We can continue to do this analysis. Let me just look at this one. This is compression ratio, yeah, and symbolic. For increasing value of symbolic, compression ratio that you find is, in this range for one group of cars, whereas for other group of cars, the symbolic range of symbolic is very small. For this cluster, if the cluster is a real cluster, the range of possible symbolic values is much less than this cluster. That's what is coming out of this analysis. Okay. Now let us look at the other columns. Let's look at this one. Look at this. This is the relationship between wheelbase and length. Obviously, as your wheelbase, this is wheelbase, as the wheelbase increases, the length of the car increases. And you're seeing a positive relationship here. The R value will be very close to 7 or 8. So this is the case where you have two dimensions and both the dimensions are interacting with each other. They are not linearly independent. But the algorithm assumes that all dimensions are linearly independent of one another. Okay. So we have ways of handling this. One way of handling this is find out using your domain expertise whether calculating the length of the car is more prone to errors or whether calculating the wheelbase is more prone to errors, measurement errors. If calculating the length of the car is more prone to measurement errors, drop the length of the car. Keep the other one. However, if you're not able to take that call, you might want to run a principal component analysis, a mathematical technique, or singular value decomposition, another technique. Okay, using those techniques, we can create synthetic dimension out of this. That synthetic dimension will be a composite of these two, so I'll drop both of them and keep the synthetic dimension. I'll talk about this when we come to PCA, principal component. Right now, I'll ignore this. Okay. So in the data set, what I'm saying is there are distributions amongst columns which have linear relationship. There are distributions amongst columns which are indicating no relationship. This one, these are all no relationship. But this is negative relationship, so on and so forth. It's a mix. Some columns are related, some columns are not related.
Can you just tell the cylinder one?
Cylinder one? Where is cylinder?
Last.
Oh, sorry. Where is the last? Yes. Which one do you want in cylinder?
Just
cylinder versus cylinder. Cylinder versus cylinder?
Yeah.
Right. This one?
Yeah.
Okay. What is the problem here?
If you look at the cars with number of cylinders, okay, in your data set, most of the cars have 4 cylinders, 5 cylinders, 6 cylinder, and 8 cylinder. Okay, most of the cars, look at this, have 4 cylinders. By the way, these data points might be sitting on top of one another. So that doesn't mean your data set has only 1, 2, 3, 4, 5, 6 records for 4 cylinders. Don't do that mistake. Your data set might have hundreds of records for 4 cylinders, but they're all sitting on top of each other. So that's why you're seeing only 6 dots. Most of the data have 4 cylinders. Some of them have 5 cylinders, some of them are 6, some of them have 8. Only few records have 12 cylinders. Very few records have 2 cylinders. Now when you go to the extreme end, where cylinder versus cylinder, that's why you see a peak in 4, some peak in 5. then you'll 6 and the small peak here. None of the other have any peaks. Now cylinder is a numerical column, integer column. You can have 1 cylinder, 2 cylinder. Then what do you mean by the spread? What is a spread? How can you have a spread on integer columns? This diagram which I plotted here is called KDE, kernel density estimates. So there are 3 words in this. First word is it's an estimate. It's an estimation of the possible distribution, density distribution, density estimate in the population. In the population, how the cars are distributed around this value in cylinder. It is a density estimate based on a mathematical function. That mathematical function is called kernel. So using a mathematical function on the available data, I'm estimating how the density distribution of this column is likely to be in population. That is why you're getting the spread. The spread is not in your data. The spread is the estimate of the distribution density in the population based on the observations in your data set. So for integral columns also you can have spread like this, because what the kernel is telling you is in the population it's likely to be like this.
If you're building the model on this data set, it's like involving is something that as to not understood what does it mean.
I actually went and studied what symboling is, but unfortunately I forgot. I should have known.
I mean, if I come to know that this is not of a very significant use, shall I not drop this?
You can drop it. Data. See, you can't do model building without domain knowledge. You have to have domain knowledge. We have to go and find out what the symboling stands for.
But in your drop statement, like we are not dropping symboling, so we should, I think.
Why do you think we should?
Because, I mean, it's also categorical value.
So what? Doesn't matter.
If a car coming from Japan versus car coming from US, the miles per gallon is going to be different. So it's a categorical variable. Origin of the car is categorical variable. It has an impact on mileage.
If you see the domain kind of
so symbolism drop the uniform growth variance with the what you take as a limit for that. There are columns with values. So there are columns which have a couple of values and there are some with 3 values, and you decide to drop all of those. So how do you determine which one is picking?
Look at the ratio of the distribution. In a column, there are 8 values, but majority of the records is with value 1, very few percentage of value 2, then that becomes a low variance filter. That's a candidate for low variance filter. But the skewness in the distribution, suppose I have gender column, male, female. 95% or 90% of the data is males, 5% is females. So I might take a call that this column is going to be useless for my analysis and drop it. So it's a call that you have to take. It may not be 100-0, it might be some distribution, but is that distribution good enough for you to use it? You have to take a call. And that call you will be able to take both based on domain knowledge. If I know the drivers in the people who use the car is 50-50 amongst these gender in the market, I know that. But for some reason the data which I have does not reflect that.
So I might drop the call.
Should we be doing this scatter plot matrix analysis before we drop that? Wouldn't it help that way then? Do that first and then.
This analysis is done on the original data set. It's not on the dropped data set. You should always, this analysis on car DF, you should always do this pair plot analysis on the original data set, always. Okay? Once, because this analysis is what is going to tell you which dimensions are likely to be important, which are not likely to be important. You should always do this on the original data set. Hey, you got your coffee?
Yes, that's right.
But I think here we've already dropped it and we're doing this analysis. This is not on the original.
Hey, no. I changed it here, no? I changed it here. I asked you to.
We've removed fuel type engine indication, all of that we've already removed and then we're doing this analysis.
No, I commented out this line. I just now did that.
But you've already dropped the columns, that's my point. You drop first and then you're doing this analysis.
Car underscore DF?
Yeah.
Oh, you're talking about this one?
No, about this. You go further up, yeah. So
you're talking about these, yeah. Okay. Yeah. You should be doing this before you do this. Before you do this. Always do your analysis on the raw data set. Okay. Alright, shall we move on?
Just one question.
Yes, please.
We did analysis on compression ratio and the second one is cylinder.
Yeah.
What we found is compression ratio have two Gaussians, so we need to treat the outliers and
Yes.
what are the things.
Yes.
But in this case, we know as per the domain knowledge, we cannot treat the cylinder thing. Right?
Yeah.
Like we cannot change the cylinder 12 to cylinder 4 just because it's kind of an outlier or something like that.
No. What you can do is go back to your data, find out what is a car model, go and refer to the manufacturing, because you have all this information, whether this car model can have 12 cylinders. That analysis will do. That is what you have to do. See, missing value replacement, outlier replacement, all these things you cannot do without your any domain knowledge. You have to have domain knowledge. When I went and studied this data set, I found out that for a given car, say Toyota, some particular, within Toyota, one particular subvariant, the data given for mileage was unreliable because the factory manufacturing label itself says the miles per gallon is going to be in this range, whereas this guy is claiming to be so high. So the data itself became a question mark. So you have to do that analysis. Okay. So when you do a real life project, when you get into capstone project, you have to reflect all these things. How did you analyze your columns? How did you handle your outliers? How did you handle your missing values? And you have to justify your strategy, why you did that. You can't blindly replace something with a median. That may not be the optimal strategy.
Right? Shall we move on? Okay.
For symbolic, symbolic means cars are initially assigned a risk factor symbol.
Risk, yeah, correct. They are assigned a risk factor. Yeah, that risk factor is what they connect with symbolic. Can you just read out more louder?
The cars are initially assigned a risk factor symbol associated with this price. Then if it is more risky, the symbol is adjusted by moving it up the scale.
Okay, all right. So this is a risk factor associated with the car. And again, this reminds me, the risk factor associated with the car depends on the color of the car. I don't think we have color here. It depends on how the car has been driven, how the car is driven. These days, a lot of people, they take pride in telling that my car has so many chips. If you buy these high-end foreign brands, they all come with embedded chips. Those embedded chips, in real time, they capture the data about your driving style and pass it on to a central server, where they sit down and analyze. And the risk factor is adjusted, recalculated, recalibrated, based on how the car is being driven. The symboling reflects that. Right? Okay, let's move. Now, are you able to understand how to interpret this pair plot? It'll come through experience, but this is where you have to do it. Okay? Move on. So what I'm doing here is, from the car_df, I am dropping the price because that's my target. And whatever columns I am left with, I'm capturing that into X. So I'm creating a new data frame called X, which will now have only those columns which are independent variables. The target column price will not be part of X. Then once again, I'm dropping number of cylinders here because this is the same problem. It's a low variance filter again. But if you wish, you can keep it. Then what I'm doing here is, from car_df, I'm dropping the price. And sorry, I'm not dropping the price. I'm selecting the price column and storing it in Y variable. So X variable is all columns except price. Y variable is only the price column. So if you have 1000 record 10 columns, this will become 1000 record 9 columns. This will become 1000 records 1 column. Are you all okay with this? So I have segregated the independent and the dependent variable. If this was R, I don't need to do this because R takes in as input only one single data frame, and along with that a formula. Whereas in scikit-learn, I have to separate this data into independent and dependent variables. Then I'm making use of the random function which generates the training set and test set. We call it train test split. When I make use of this train test split on X and Y, I'm asking it to split the data in a ratio of 75-25, 25 for test, 75 for training. the output of this will be four data sets. So let me explain this to you, because some people get confused here. So if this was my data frame df, this was my target variable iv, independent variables, target. First thing which I did is I captured the independent variables and stored them in x. I took the target variable and stored it in y. Then on this x and y, I did a train test split. When I do this, what happens is it breaks this x and y both into x underscore train, x underscore test, y underscore train, y underscore test. This training label y underscore train is for this x underscore train. This is my test data, x underscore test corresponding y underscore test. Now when I build the model, what I will do is I'll call the fit function, fit, and with the fit function I'll supply these two. This one, x underscore train, and y underscore train. I'll supply these two. This is at this point, the gradient descent will come into play. It'll identify for you the best fit model. The best fit model will reflect the relationship between y, this one, and x. This x comes from this training set. So it will be of the form y is equal to m1 x1 plus m2 x2, so on and so forth. How many columns are there? 16. So m16 x16 plus c. This will be the model. Once the model is built, we want to evaluate it. We want to see how it performs. To this model, I'll supply the x underscore test values, which means these values. And it will give me the predicted values, y pred. Are you getting it? So I supply the test data, the x underscore test, only the test data to this model. The respective columns get multiplied by their coefficients for every record. For every record, I get y underscore pred. What is the predicted price for this car? In the data set, I know my actual y underscore test is this. Predicted y is this. What is the difference between these two? That will be my accuracy. Accuracy will be the difference between the y underscore test, which is actual test labels, versus y underscore pred, which is your predicted test labels. Right? So let's see this, but before we go there, yeah, I think we can do it comfortably. So let's look at this. Train test split. I'm calling the linear regression here. This is where I'm instantiating the linear regression model. This is where this class becomes an object. And in that object, there is a function called fit. I'm calling that fit function and supplying the training set. When you run this, this is the point where the best fit line using gradient descent is found for you. Now look at this, I'm printing out the coefficients of all those, the best fit line, the best fit plane, hyperplane rather. So when I print the coefficients, these are the coefficients. Now we need to understand what this is. You said there are 16 columns. So the 16 columns have 16 different coefficients, m1, m2, m16. This is that M1, M2, M16. M1 is 88.57, M2 is 71.82, M3 is minus 93.38. All these are those M1s. So let's understand what it means. What it means is, for every one increase in symboling, 1 unit increase in symboling, the price of the car goes up by 88.57 units. dy by dx. For every 1 unit increase in the wheelbase, the price of the car goes up by 71.82 units. Whatever the units may be, dollars, yen, rupees, whatever it might be. For every 1 unit increase in the length of the car, the price drops by minus 93.3 units. Now look at this. This is where you need to be careful. We know that wheelbase and length are positively related. We saw that. Then how come one has a positive relation, other has a negative relation? But both of them should be positive, no? Wheelbase and length are positively related. But one of them is having a positive impact on the target, the other one is having a negative impact on the target. How can that be? Such things indicate to you something is not right in your data set. And one thing which is not right in your data set here, we all know that, is multicollinearity. Engine size, when engine size increases by 1 unit, the miles per gallon, price goes up by 251.74 units. Okay, that is the way you have to interpret this. But what is happening is, some of these ratios are kind of not gelling in, they're not fitting in properly. For example, we already found the length and the wheelbase, they're going in opposite directions. Okay, that is one problem. Then we have horsepower. When horsepower increases by 1 unit, your car price goes down, whereas actually when horsepower increases by units, car price should go up. Horsepower increase means large cars. Large cars, you pay more price. Bit more considered, but this is not only negligible, it's also the wrong direction. Right? Good point. Right? So there are problems in these coefficients which are not falling in line with our domain knowledge.
So this coefficient is what we are talking about, right? So is it saying about the weightage kind of thing? The one thing I'm not able to understand is when it say 88, okay, it increased by 88 when unit change, keeping other constant. But some values is talking about 6,000 line, 6,000 scale, one is talking about 88. If we compare among each other, it's a huge difference. So how we are going to interpret this in after?
The reason why the 6,000 is happening is probably you have an outlier on that dimension which is pulling it, right? So we have not addressed the outliers here. One reason could be that. The other reason is if you're not able to, I mean, if these numbers are not falling in place, then we can convert them into z-scores. The entire data set can be converted into z-scores, and then we can look at this. But the magnitude of the difference, you will still see that the magnitude is still there. Okay, the difference is still huge. And the root cause of this problem that we are seeing, the root cause for this is, 1, we have not handled the outliers. 2, we have some kind of a, correlation between the independent variables, which you noticed. We have not done anything about that. Multicollinearity. Right? So those are the core reasons which you will come across in all data set, which lead to overall model level problems. Okay? Now I'm going to take you through further down into slightly more deeper stuff. Let me see if I can cover it today. If not, we'll start with fresh minds tomorrow, because I need, that particular thing needs a lot of brain energy.
Brain power.
So right now, all columns has specific units. They are not normalized. So this coefficient is on the not normalized data.
Correct.
So it's always better to have to normalize the things and then calculate the coefficient. Is it like that? Because otherwise you are not able to relate the coefficient.
The coefficients will not change when you normalize. It doesn't matter. By normalizing, you're just centering the data to 0. The relationship between y and x will remain same, whether it's a normalized data or a non-normalized data. Coefficients will not change. Linear regressions are not impacted by normalizations. The accuracy score, the coefficient, everything remains same. Okay, shall we move on?
Yes.
So linear regression only gives the coefficient, but not the power of that x square. Those things we cannot.
No, this is simple linear model. If you build quadratic model, then it will. Right. So let's move on and let's see the intercept. This is the intercept. I'm printing the intercept. What you need to do is model.intercept. This is the model name. Model name.intercept. This function will give you the intercept. Whereas if you want the coefficients, you have to use model.coefficients. Look at this. For coefficients, it is model.coef underscore. Coef underscore will print the coefficients. Model.intercept will print the intercept. Now the intercept that we are getting is minus 1, 2, 3, 2, 3. There's an array. In that array, we are passing the index. So the first one is intercept. In the other array, we have the
coefficients.
I just tried
for coefficient also we are passing 0. Yeah, that is a different array. So I'm saying starting from 0 and all the coefficients.
Yeah, in my code I just tried regression model not coefficient. So just that much. Yeah. Regression, I mean the dataset dot coefficient.
Dataset.
This regression. I just typed that code. It was showing some other results. It's not showing the whole set.
No, are you sure you're getting 0 in IDX? No, you have to do this. See, this is a different array. In that array, I'm accessing all the elements of the array using this, which is why it's printing out all these things. You have already done that. After fitting it, the output of this is best fit line. The best fit line has coefficients. All the coefficients are internally stored in an array which is accessible through this function. This function is accessing that array and printing out the results. Similarly, there's another array for your intercept. It's accessing that array using intercept. We don't know what that name of the array is. We can only access that array through this function. This point in the graph, all these coefficients in the graph are the lowest point in your error. This is error. There are multiple 16 dimensions over here. This is the lowest point. This combination of coefficients gives the lowest point in the error graph, the best fit. Right? So let us look at the performance of the model on test data. And as you can see, performance on the model on test data is 83.6%. Not bad, not good either.
So what does it mean to 83.68?
The comparison between this and this. Okay, so the 83.6%, what do you think it is? No. This is your coefficient of determination. 83.6% of the total variance in your data, test data, has been captured by your model. R square. This is not adjusted R square, this is R square.
That means 70% we still don't know why.
Yes. Sum of square errors.
X minus mean.
Xi minus x bar is for 2 by n. That residual error is 17%. 17% of the variance in your test data has not been explained. Alright?
So where does the intercept lie on that graph?
Intercept is one of these dimensions. Error is a function of slopes and c. Error is a function of m and c, right? So c is one of the dimensions. What I showed you earlier was only one m and c. Here you have 16 m's and 1 c. We can't visualize it, so I'm not able to show it.
That's the problem.
This 83.6% prediction is accurate.
It's the coefficient of determinant. How much of the variance in test data has been captured by your model, explained by your model. Shall we move on? Okay. Now we need to improve the performance of the model. Your first cut model will never give you the results that you're expecting, very rare. So you'll always end up in another cycle where your objective will be how do you improve the performance of this model? How do you notch it up? So there are various things you can do, but before you do that, I would like to introduce you to a library called stats model. Stats model, the formula API, SMF, stats model functions. Okay. What happens is, when you build these linear models in R gives you a lot of statistical information about your attributes and your models. Scikit-learn linear regression does not give you those information. But there was a lot of demand for that kind of R kind of analysis in Python. So those people who support Python, scikit-learn, they came out with this library called stats model. Stats model tries to replicate the behavior of R, okay, and gives you similar kind of statistical analysis as you would have received or obtained in R. So let's see what it does and why is it required. So I'm importing statsmodel.formula.api. I'm importing something called SMF. SMF is a bunch of statistical model functions. And this, I'm going to build a linear model using this. But before I build a linear model using this, I have to combine my X train, Y trains into one data frame, because R takes as input one single data frame. It does not take independent variables, dependent variables separately. So I'm recombining the two into one using concat function. I'm creating a new data frame called cars, which now has both the Y and the independent variables put together for training. Okay. Now look at this. When you do cars head, you get the price column on the first column, and the rest of the columns. Now I make use of the smf.ols. OLS stands for ordinary least squares. Linear regression, ordinary least square. And as input to this function, I give price a formula where I say price is a function of the various columns. The plus which you see here, this plus is a field separator. It's not a mathematical plus. And at the end of it, you will see the data file name. Sorry, the data file name is cars. There you go, data is cars. So the output of this is once again the same model. But this model has been built in R, R-based, similar to R libraries. So the model is price is equal to, I'll take the intercept later, symboling is 88.57. 88.57 symboling plus 71.82 wheelbase minus, I'll just take one more, 93.38 car length CL, and so on and so forth. The last thing being minus 123.06 or something intercept. This is your model. This is the representation of your best fit line. Now you can write a code in Java where you have a function where function takes as input 16 variables, multiply those variables with the respective coefficients, subtract this intercept from that, and give the output as your predicted price. Convert that Java code into a runnable jar file, productionize it, your model is in production. All right. So that is the model. Same model we got in scikit-learn, same model we're getting here, but here we're getting some extra results. which we did not get in scikit-learn. Do some of these things look familiar to you? R square, adjusted R square. Look at the difference between R square and adjusted R square. Adjusted R square will always go down when you add useless columns. R square will always go up. So adjusted R square will usually be less than R square. F statistics, analysis of variance. Remember these words, Fisher statistics, analysis of variance. Then you'll also have AIC, BIC. What is AIC? Hey Guru, we would have covered in stats. AIC is Akai information content, BIC is Bayesian information content. Alright, forget it, no problem. Not required. Let's go straight down. Most important of these is your adjusted R square. Adjusted R square is lower than R square. 80%, is it okay with you? You have to decide. But before I go there, I'll come down to this. Okay, I'm going to stop at this point. What is this table telling you? I'll just take one example and you have to use that example on others. Okay. Then I'll tell you why this is not there in Python. Now you take any one of these dimensions, say length. The coefficient for length is minus 93.3. We already seen that. And then it gives you standard error, t values, probability of t values. Remember your hypothesis testing? When do you reject null hypothesis? When do you accept null hypothesis? You remember those concepts? Remember we use a p-value there? Right? P-values, that is what is this. Okay. Now the thing is, let's take one of these example, length. I told you to find the best fit line, the algorithm will try out various lines. Okay, and it will find out the errors for each line for you using gradient descent. And I also told you that the best fit line that it finds out will always go through the x bar, y bar. Agree? So it would have tried out various lines for you before finding the best fit line. For each line on this particular dimension length, you can take any dimension. For each line on this particular dimension called length, you would have had different slopes. Each line would have had a different slope, different coefficient. So those coefficients would have a distribution of their own. Those different coefficients which it tried out on the length dimension before it found the best fit line, those coefficients would have had different distributions. Of that distribution, the one given to you for best fit line, minus 93.38, maybe this one, minus 93.38, how far away it is from the central value is given by your t-score. This is minus 1.2, whatever it is, t-scores. What is t-score? T-score is a z-score. All of you remember z-scores? Xi minus x bar by standard deviation. How many standard deviations away a data point is from the central value? We use z-score for that. When you use student's t distribution, we call it t-scores. Formula is same. Remember student's t distribution? Okay, the formula is same. So the selected value for coefficient for length, how many standard deviations away it is from the central value for the distribution of coefficients on length, that is given by this. The standard deviation of this distribution, the standard deviation of this, which we call standard error in t distribution, that is given by this. This is the standard deviation. This is how many z-scores away it is, your selected value is from the central value is this. You multiply these two. Multiply these two, please. Multiply these two. And tell me what is the value you get? Into minus 1.24. 73. You will get back the same value. You will get back this value. Okay? Look at this. if I'm doing z-score, okay, z-score centralizes your data, converts the x bar and y bar into zeros. I take any value xi minus x bar by standard deviation is my z-score. Agreed? X bar is 0 because it centers the data. So that means z-score is nothing but xi by standard deviation. So xi is nothing but z-score into standard deviation. Here we call it t, and we call this standard error. So when I multiply t with standard error, it gives me back the value that you had over here, xi. It gives me back the xi, okay? So that is the way to interpret this. Of all the various coefficients tried out on this length dimension, just select you this one, how far away it is from the central value. If it is too far, maybe it's not reliable. I'll do that analysis using this. The most important analysis which I want to take you to is the p-value. What does this p-value tell you? What the p-value is telling you is, I'm going to talk only for length, but the same thing applies for all. What this p-value is telling you is, probability is 0.2. What is the cutoff probability for your confidence level? 95%? 0.05, 5%. 0.2 is much higher than 0.05. What this is telling you is, even if in the population there is no relationship between the length and the price of the car, no relationship between length and price of the car, null hypothesis, and you're taking data from that population, you're likely to find this kind of a relationship between length and price in your data, which means this is a fluke relation. I repeat, what this p-value is telling me is, probability of finding this kind of a relationship between length and price in your data, even if there is no relationship in the population. In population, the slope is 0 between these two. And from there, you're taken a sample, random sample. The probability of finding this kind of relationship is very high, which means this relationship is fluke. It's a statistical fluke. It's not reliable. Look at this one, p-value. Look at this one, stroke. P-value is almost 0. What it means is, if in the real world, there is no relationship in bore and the price, and then from that population you have taken this sample, finding this kind of a relationship between bore and price, the probability is very low. Probability is very low. I'm talking stroke, sorry. Probability is very low, which means this relationship is not fluke. It is likely to be there in the real world. Okay, so let me put this pictorially and explain this to you. Then we'll wind up. Let's take one of these columns, stroke and price. Same thing applies to all. If suppose between stroke and price, if suppose there is no relationship between these two, then how will the scatter of the data points look? Agreed? All of you? R value will be very close to 0. The scatter of the data points will be circular. Okay? Now, what you will observe is, most of the data points are near x bar, y bar. As you move away, the density falls. That is why you get a plot like this on this and a plot like this on this. Are you all okay? When I convert this into 3 dimension, where in the 3rd dimension, this is my x bar, y bar. If I plot the density on the y-axis, question to you is, how will the distribution look? Parabola? Cylinder? Keep in mind, very close, it's very high. As you move away, the density falls. So this will be your normal curve, a 3-dimensional normal curve. A 3-dimensional normal curve is the shape of the density of distribution between 2 dimensions which don't correlate. This is the shape of null hypothesis. Null hypothesis says, in your universe, the data is distributed like this. Agreed? We don't know what the universe looks like, but null hypothesis says it looks like this. If so, and from there I have taken a sample, and in the sample I am finding the distribution between this core, whatever it is, say core, and price, I am finding the distribution like this, where this is X bar, Y bar. I am finding a squashed bell curve. I am not finding a symmetric bell curve, I am finding a squashed bell curve. This relationship is what is expressed as this coefficient. Now the question is, what is the probability of finding this kind of a distribution in your data if the real data is like this? That probability is expressed as p-value. If the p-value is very low, less than 0.05, that means your universe is not like this. We reject the null hypothesis. Whereas if p-value is greater than 0.5, we say that there is not sufficient evidence to reject the null hypothesis. So I'm unable to reject the null hypothesis. May not be, I don't know, but I don't have sufficient evidence to claim that there is a correlation.
Shouldn't the null hypothesis be, I mean, by default, we are trying to prove the other way, right? So
no, we are trying to establish whether null hypothesis is likely to be true or not. We can't do the other way. We can't prove alternate hypothesis is true or not. We can't do that.
So shouldn't the null hypothesis be, is a relationship already and...
No, null hypothesis is no relationship. They are independent. It always negates your alternate. Alternate says there is a relationship. Null hypothesis is nothing doing. There's no relationship. No relationship means this is the way. Now the question is, from this you're drawn the sample. In the sample you're saying this. What is the probability of seeing this kind of a distribution if it's coming from this? If the p-value is less than 0.05, we reject the null hypothesis. If p-value is 0.05 or greater than or equal to, we say we don't have sufficient evidence to reject the null hypothesis. So we accept the null hypothesis likely to be true, we reject this. This analysis R provides, Python doesn't. And if you look at this, this is the p-values. So this tells you the importance of the attributes. Those attributes whose p-values is greater than 0.05, useless. Statistical fluke. Those attributes where p-values is less than 0.05, good attributes. Let me be a killjoy, okay? In the statistics community in the real world, there is a vertical split between the statisticians. One school of thought says p-values is not reliable. The other school of thought, which comes from the conventional statistics point of view, they say p-value is reliable. The reason why they say p-value is not reliable is, you can go and check it yourselves. Suppose I drop one of these dimensions with high p-value, symboling, and redo this analysis. All the other p-values will change. Now the question is, between your price and your length, if there is a relationship given by the coefficient, why should that coefficient change when I include another dimension, width? Why should it change? It should not change, right? The relationship should remain relationship. Why should the intensity of the relationship change when I add another dimension to it? But when you actually go and analyze this, drop the dimensions, you see that all coefficients change. Correspondingly, all the p-values will also change. The reason why they change is collinearity. They are not truly independent. Since there is collinearity and they impact each other, the coefficients are not reliable, hence the p-values are not reliable. It is because of this reason, this split between the statistics community on whether they should rely on this or not, scikit-learn guys said, forget it, we don't need this. We have other ways of establishing the reliability of the dimensions and the models. Let's use that. That is why scikit-learn does not give you this facility. But then subsequently under pressure, they came out with stats model libraries, which gives you this. Okay. Now, just to end up the show, what is telling you is p-value, and what it is telling you the 95% confidence within which these values lie. Okay. So if you guys remember 95% confidence level, area of rejection, area of, you'll see all, you'll be able to connect to those using this. I'm going to jump this, I'm going to move forward. Last one. overall probability value of the model itself. Can such a relationship between the price and the other good attributes, does such a relationship exist? P-value is very low, which means null hypothesis overall is rejected. Model level p-value is very low. So after removing all the unwanted dimensions, hopefully you will have a reliable model.
All right.
So do we need to reject or not based on p-value?
The p-value is very less here. So we should
lot of columns.
If you're working for people who believe in statistics and all, I mean, not that I don't believe in statistics, those people expect p-values from you, then you have to use stats model. If they don't care about p-values, don't come here. There are other ways of deciding whether a dimension is reliable or not. Ensemble techniques and all these techniques are available with us. So we use that technique.
Most influencing factor for the price. Then
Use decision tree regressor.
That will list out for you the dimension, as you will see now after lunch. It will list out for you dimensions in terms of importance. Which dimensions are more important?
But don't they again use the p-values?
They use Bayesian statistics. They don't use p-values. You remember naive, you won't have done naive. You remember Bayesian distributions? They use that for this. Some statisticians say that Bayesian distributions are more reliable than this. All right, sir. I'm going to call it an end of the day for today. For me, for you guys, it's going to continue. We'll meet tomorrow at 9 o'clock again. Yeah. So let's see what this logistic is. The name logistic regression is slightly a misnomer. It is used for classification. It cannot be used for regression, okay? Though the name says regression. But there's a reason why it's called regression, not logistic classifier. The reason is, under the hood, logistic regression uses linear models, linear regression. That's the reason. It's a classification method based on a linear regression. The response variable, that is the target variable, can be binary class, defaulter, non-defaulter, diabetic, non-diabetic, or it can be multi-class classification also. I can use logistic regression for optical character recognition. I can do that. And in my personal experience, I have seen and I have also read some papers about it. When you compare models, often logistic regression comes out on the top. If not exactly on the top, at least top few, top 2 or 3, okay, for classifications. So I'm going to start by showing you binary classification, but this can be used for multi-class classification also. Given your independent variables, what is the class likely to be? That is the objective of this model. I can also use a function available in scikit-learn where instead of defining which class an observation belongs to, a test record belongs to, I can print out what is the probability that this record belongs to this class versus this class. I can even print probabilities. Okay. This particular function is nothing unique to this. It's available in all probability-based models. Predict. You remember we use predict? We just add underscore proba. This function will print out probability values. If you go for just predict, this will print out the classes. Decision tree also has this, naive Bayes algorithm also has this, logistic also has this. Predict underscore proba. Let's take a hypothetical situation. Don't worry about the PPT. Let's take a situation and discuss this concept. And for that, we are going to use 3 colors. You are a data scientist, you're working in a bank, and you have been tasked with, you have been given a responsibility to build a model where the model will take certain inputs and the output of the model will be, is this person likely to default? If I give him loan, is this person likely to be a defaulter or a non-defaulter? You have to build that model. Okay. So what kind of data will you need to build such models?
He's salary income, he's student or his profession.
So past history in terms of
Civil score.
Civil score. Okay, civil score is an output of a model actually. So let's keep civil score aside. You'll need his age, gender, income, any past loans he has taken, any property he has, so on and so forth. So many things. Now let's assume that one of the things given to you is his income. Forget it. This is a touchy subject, so let's call it age. Okay. One of the inputs given to you is the age of the people. So you have the past data with you. The bank has given you a past data set. In the data set, you have both defaulters, non-defaulters, and one of the columns in the data set is age. You notice a pattern here. The pattern is most of the defaulters, okay, most, not all, most of the defaulters are in the lower age bracket, okay, and you also notice most of the non-defaulters are concentrated in higher age bracket. But that doesn't mean there are no non-defaulters in low age. Okay, you observe this pattern. Now, since there are two classes here, what we're going to do is we are going to say green class, we're going to assign a numerical value 1, red class numerical value 0. Remember, we can't work on string data types. So the target columns will be assigned numerical types. Okay. Why 1 to this, why 0 to that? No reason. You can flip it also if you wish. But we assign a value 0 and 1. We don't assign any other value, we assign only 0 and 1. There is a reason for that. Okay. Now, your object, yeah. Now you find that the pattern over here, as income increases, you find more greens. As income decreases, you find more reds. You have done a linear model already. So what you do is, you try to build a linear model here. So you say, let the y-axis be probability of belonging to any one of the classes, let's call it 1. The y-axis is probability of belonging to class 1. You can actually take it as probability of belonging to class 0 also if you like. The two probabilities will be inverse of each other. So you can take any one you like. Alright? So when you build a linear model, the linear model, anybody has a black pen here? Black? No, this pen. Oh, okay. Now you'll notice that as the age increases, if this is a probability, the probability of somebody being belonging to green, the probability increases linearly. Probability increases. I can represent it with linear models. If I had taken this as 0, if this was 0, then this line, how would it look? It will be reverse. That's the difference. So you can use any line. Okay. So I'm taking this as 1 for ease of explanation because you will be able to connect to what we did yesterday. So the line will look something like this. So this line, y equal to y is probability of belonging to blue class is related to mx, x is this variable, plus c, c is the intercept over here. C may be 0, c may be negative. But the problem with the linear model is, linear models go to infinity, minus, plus. Probabilities have to be within 0 and 1. They can't be below 0 or above 1. So, we can't use a linear model. We use another technique where we transform this line into an S-curve. This S-curve is called a sigmoid. And it is very easy to achieve this. The sigmoid is nothing but 1 by 1 plus E. E is an Euler constant we use in mathematics, minus mx plus c. So this best fit line, the best fit line which is found for you, this best fit line is fed into this transformation, this mathematical formula. The result of this transformation is this curve. Yeah, sigmoid curve, the property is it will reach 0 at infinity, it will reach 1 at infinity. That's exactly the property of a probability distribution. Now let us interpret what this formula is saying. Keep in mind we're building the model, so which means we're in training set. So in training set we already know the labels of every record, right? The algorithm gets both the input variables and the output variable, x and y. So all the labels are already known. And the labels are shown in the color over here. Are you all okay? Shall we proceed? Now, what the models, now that I got sigmoid, I'll remove this line. I'll remove this line. Okay, this is going to infinity. We don't even need this. We don't even need this. Now, what this model is telling you, let's look at that. If you take this red point, look at this. If you take this red point, what the model is saying is the probability of belonging to blue class. What is the probability of this guy? Suppose we don't know the color. What is the probability of this point belonging to blue class? It's very low, which means it belongs to the red class. So the model prediction and actuals are matching here. The model prediction and the actual label, both of them are matching. Take this green one. What the model is saying is, what is the probability that this green point belongs to blue class? This is probability of blue class, right? The probability is very high. And he is actually green. So both prediction and actuals match. Right? Hey, lady, are you with me? Sure, 100%. Okay, don't get left behind. Your expressions tell me a lot of stories. I have conducted I lost count, more than 250 sessions now in data science. So I built a model. You know what's coming, right? So looking at the place, the position people occupy in the class, I can guess a lot of things about the person. Believe me, we all follow patterns, and you'll be surprised. I've noticed this pattern without fail. Based on the position people occupy in the class, okay, of course, latecomers, they don't have a choice, but people who come early, okay, based on the positions they occupy, I can draw a lot of conclusions from there, inferences from there, right? So people who are feeling doubtful but are able to ask, they're not asking, I know I can identify such people. Okay. So feel free to ask, okay? All of you, please feel free to ask. Don't get left behind. I was always a backbencher. I was always a member of the backbench society. I'm not saying anything to you. Don't look at me. If you sit in all places means? I was always a backbencher, so I know more over the backbench than the front bench. But other patterns which I observed was during the sessions, right? So a deviation from our main topic of discussion, bottom line is don't hesitate to ask. Okay, feel free to ask, don't restrict. Coming back to this, are you all with me on these two discussions? Okay, now look at this point. You see a red point here, this one. What the model is saying is, as per his income, he belongs to, probability of he belonging to blue class is very high. So the model will pass him as blue. Sorry, in this case green. Green, in this case green. So what the model surface is telling is predicting the probability of belonging to the green class. It's very high. So the model will classify him as green, but he is actually red. So model has done an error over here. Mistake. Similarly, if you look at this one, this side, the green point here, can you tell me what the model is telling you? The model is telling you the probability of him belonging to green class is very low, so he's likely to be red. But actually he's green. So the model has done an error here, a mistake. Okay? So whenever you have overlapping data sets, as in this case, in spite of the best fit line, the classification, you will find some errors. There will always be errors. These errors are called training errors. Errors in the training data. Okay? All right, no problem. Which one is -1? This is 0, this is 0, this is 1. And this axis in this particular picture, this axis is probability of belong to class 1. Okay, that's why your S curve is coming like this. This S curve has been built out of a linear model. If you had taken this, as probability of belonging to class 0, then it would be reverse S curve. Because your curve would be like this, the line would be like that. Oh yeah, all models have problem with outliers.
So can you explain what is the reason you have taken S curve rather than the linear line?
Can somebody answer that question? Why S curve?
Because the linear was going it will go to plus infinity to minus.
Hey, linear will be overfit. Who said that? What did it? In linear models, we don't have any boundary. They go to plus infinity, minus infinity. We don't want that. Probabilities have to be between 0 and 1. That's why they will convert into sigmoid. Sigmoid curve has that property that will always remain between 0 and 1. So we are able to map the numerical values to probability function.
So coming back to the same question, now you explained the binary thing. So same thing is applicable for the multi-class.
Yes, in multi-class classification, it will be 1 versus rest. Suppose I used this logistic regression for OCR, optical character recognition. So you'll have one S curve for A versus others, one S curve for B versus others, so on and so forth. So in your mathematical space, you'll have multiple S curves cutting each other. One is for A versus others, the other one is B versus others, C versus others, so on and so forth. All these algorithms, decision tree, naive Bayes, support vector machines, neural networks, logistic, they all break your mathematical space into compartments. They break them into compartments, pockets, where one pocket belongs to this object, the other pocket belongs to that object. All of them do that. You done decision tree yesterday? Yes. Which data set did you use? Diabetes data, PMA diabetes data set, okay? That is a binary classification actually. And so when you make decision trees, okay, this is the structure you have of decision trees. What you're doing here is, this entire mathematical space is your root node. The entire data set, all data points put together is your root node. Then you find out one particular column on which you break the data into two. That is like putting a vertical boundary here. So these two now are these child nodes. But you have not achieved your what you call homogeneity. Your Gini index is still very high, or entropy is very high. It's still not pure leaf. So what you do is you again find a column here in this data set and break this into two. That means you're drawing a vertical boundary. So this and this is the child node here and here. So decision tree also breaks your mathematical space into pockets such that each pocket becomes homogeneous at leaf level. So right now I've reached the leaf level. Hopefully at leaf level, each pocket is become homogeneous. Now I know what are the conditions under which somebody belongs to this pocket. That is called the rules of the decision tree. All algorithms break your mathematical space into pockets, including logistic regression.
For this,
you treat A as class 1.
For this family, the default is
this is binary class classification. If you are in multi-class classification, optical character recognition, then you treat at one point in time all data belonging to class A, alphabet A as 1, and rest of them are zeros. See what is the boundary. Then treat all the records belonging to class B as 1 and rest of them zeros. Then redraw the boundary. So you'll have multiple boundaries cutting each other.
This is like multiple variables affecting a particular attribute that we're trying to tell. For example, if a customer is fraud or not, if I'm considering age as a factor, I'm also considering gender as a factor. I'm also considering
that will be hypersurface. Hypersurface. But multiple hypersurfaces for A, for B, for C. You'll have them, right?
So will that be a consolidated single mathematical space?
Yes, 100%. Yes. The whole model will be a composite of all these surfaces. Okay. Let's move on.
So multi-class is always 1 versus a rest.
Multi-class classification, most of the algorithms give you OVR. OVR means 1 versus rest. Some algorithms give you a facility of replacing the OVR with Bayesian probabilities. Okay, you can actually go and modify that in your hyperparameters. But most of the algorithm by default will give you OVR. Right? Some algorithms like support vector machines, OVR is not very efficient, so they give you another technique called Bayesian probability based. Shall we move on? Okay. It has a gradient descent algorithm working under the hood to find you the best fit line. Right? The linear model uses gradient descent algorithm. Do you remember gradient descent discussion we had yesterday? See, the gradient descent is to find best fit line. I'll quickly summarize this. I know it was too much in one day to cover. Your error function will always have this form, not very difficult, guys. If I give you equation y equal to x square, for any value of x, y will always be positive. It's a squared term. If x is -1, -1 into -1 becomes +1. This is called a convex function. So whenever you have any function raised to power 2, it will always be convex. Right now this is single dimension. This x can be multiple dimensions. So if I take 2 dimensions m and c and plot the error, this will be a bowl shape. Right? Now in this ball shape, we have to reach the global minima. It's guaranteed you will have only one global minima. You won't have any other. For quadratic error expressions, you will always have one global minima guaranteed. Okay. So we start with some random MNC. That random MNC gives us some error. The same concept applies in logistic because logistic is also a linear model. Right? From that MNC, it will come down to this using your partial derivatives. Concept, okay? There's a lot to discuss in this. I'm not going to discuss all those things at this point, but you will need this if you're going to do deep learning, neural networks and all those things. Right? At that time, we'll take it up in detail. Same concept will apply today in logistic because logistic uses linear model under the hood. So it finds for you the best fit line given the spread of the data points in mathematical space or best fit plane or a hyperplane. Once that plane is found, that plane is sent through the sigmoid transformation and it's converted to S curve. Right? Now the driving force behind this, here in this case it was quadratic. In this case, the S curve which is formed, the S curve can be shifted forward, backward, upward, downwards. Let me see if I can show this to you, okay? What happens is, insert, if I take this S curve, I hope it works. Yeah, it works, okay? Now this S curve, you can move it up by changing the C in y equal to mx plus c, or you can move it down. You can flatten it. To flatten it, what do you think we'll use? The slope, m of the line. By changing the slope, I can make it vertical or flatten or move it up and down using c. So by using these two parameters m and c, I will find out which sigmoid surface I get is the best surface. And to find out which is the best sigmoid surface of all the infinite possibilities, it uses a function. That function is called log loss. This is just like your gradient descent. Okay? Don't worry about this function. It's actually very easy. Looks dangerous, but actually it's very easy. Now let us look at the log loss function. Looks very dangerous, but it's actually simple, very simple. Okay? So forget the sigma and all these things. Just take the expression yi into log of pi, okay, plus then 1 minus yi into log of 1 minus yi into log of 1 minus pi. Correct? Just look at this expression. What is this y? Y is the target variable. Target variable. We know the target variable ranges from 0 and 1 only. 1 is for green and 0 is for red. So this yi can take a value of 0 or 1. Okay? Now let us look at 4 situations. I'm going to show you 4 cases, and the 4 cases we're going to discuss here. Where is the 4 cases? These are the 4 cases. Look at the first case. In your data, the first test case, these are 4 test records. Okay, the first test record has this income. The model is saying the probability belongs to blue class is very high, and is actually blue class. No error, 0 error, right? 0 error. Come to this. What is the y value for blue class? 1 into what is the probability? Very high, almost close to 1. Log of a very high number, when log comes close to 1, this is 0. Log of a very high number is 0, close to 0. 2 raised to power 0 is 1. So this is log to the base 2. Okay? So log to the base 2 of a very high number means close to 1, will always be 0. Come to this term. This becomes 1 minus 1. We don't even need to evaluate because this is 0. So when you do correct classification for the blue points, your error is 0. Let's take the next case. The next case is this red point. Let's take this red point. Let's take the case number 3. Or let's take case number 2, the second case. Okay? As per the model, given his income, the probability of him belonging to blue class is very low. Which means the model is predicting that he belongs to the red class. As per the income group of this person, the model is a blue line. It's saying probability of him belonging to blue class is very low. Anything below 0.5 is very low. So the model is predicting that this guy is going to be red, but actually he is blue. So let's see what the equation says. He is blue, value is 1. Probability is very low that he belongs to blue class. The model is saying probability is very low. Log of a very small number is a very large number. So this is into a large number. Okay? Since he is a blue class, this expression we don't even need to evaluate. It will be 0. So whenever you do misclassification of the blue, you get a very large error. All right? So the more the blue class is on this side, larger the error will become. So in technical parlance, what we say is, more confident this algorithm is about a particular classification, which we know is wrong, more the error it does. Right?
So if the probability is less, because in this PI will be, if it goes lesser, then the large number becomes more large.
Yeah, correct.
The error will go more. If you go down, it will still further.
So for this blue point, where the probability of him belonging to blue class is almost 0, this error will be very high.
So what we are saying is more error we do on this side.
For blue class.
For blue class, then loss is more.
Yeah, exactly.
And upper side, even the error is there, but loss is less.
We'll come to that. We'll first discuss only the blue class. The more blue points are on this side, in this case, the more the errors will come out. Larger the error will be. Okay? Now look at this, the red one, the fourth one. Or let's take the third one, third one. We know that this guy is a defaulter. The class is red. The model is given the income, the model is predicting he's going to be defaulter. Come to this equation. What is the label value for this guy? Class red, 0. So this expression becomes 0. We don't even need to evaluate. Come to this guy. 1 minus 0 is 1 into log of a very small number. Number minus 1 becomes almost 1. So this expression turns out to be 0. Log of a very large number, okay, is 0. So this expression comes too close to 0. For red classification, we use this part of the equation. For blue classification, we use this part of the equation. Take the last case where the red class is misclassified. The model is saying he belongs to blue class.
So one question. So Ci is the probability, right?
Of belonging to blue class.
Belonging to blue class. That's why it is 0.
Yeah. See, the model, the surface is probability of belonging to blue class.
Okay. That's why it is 0.
Yeah, exactly.
For the right.
Exactly. Look at the last case. Last case is the fourth case, where the fourth case is misclassification of red. So when you do misclassification of red, this expression is not for red, so forget it. Come to this. This is 1 minus 0 into log to the base 2. This is a very high probability which your model is predicting. So this becomes a very small number. Log of a small number is a very large number. So error is very large. That's all this equation is. So you sum up the errors done across all the data points, those which are correctly classified, those which are not correctly classified, sum it up, you will get the total error across the entire model. Sum of squared errors, same way this. So the objective is to minimize the sum of squared errors by finding the right logistic surface given the classes.
And so the gradient distribution will be the same. Right? So suppose it's a high loss, and it will go in a direction where it want to reduce that loss.
Reduce the total loss. Correct. Yesterday, the sum of squared errors was driving the gradient descent. Here, this will drive the gradient descent.
So it does gradient descent first to get the linear equation, and then does the second to get the high sigma.
Right sigmoid curve. Both happen together actually, both happen together. It's not one after the other, both happen together simultaneously.
What is the range from this block? Specific to the data?
0 and 1. All 100% is your complete loss. Which will happen when you have all the red 7 classified as blue and all the blue 7 classified as red.
Logic sheet always plays with 0.
Yeah, for classification, always 0. All right, shall we move on? Extension of linear model that we saw yesterday. The beauty of logistic regression is it makes no assumption about the distribution of classes in the feature space. Many of these algorithms, linear model especially, if you're building linear classifiers or linear regression, they expect Gaussian distributions. You understand the term Gaussian distribution, all of you? No? Okay. When you build any model, expectation is if you take this attribute, the data will be spread around the central value of this attribute with some standard deviations. Same way, this attribute will have a distribution with standard deviations. When you plot this together in the mathematical space, they will look like, if they are independent of each other, they will look like this. We already discussed this. This kind of a distribution is called Gaussian. So in 3D, it looks like a bell curve. All right. This algorithm does not make any such assumptions, but keep in mind, if you have outliers in your data set, even this algorithm will fall on its face because it is based on linear model. So those outliers have to be addressed. What will happen if you have outliers? If you have outliers, you're likely to have outliers for, say, for example, what do you call them? The class 1. If you have an extreme outlier here, then you're in trouble. If you have outlier on this side, no problem. If you have outlier on this side, you have a problem. So more extreme it is, more severe the outliers is, more the errors will be. Right? Okay. You can do multi-class classification using either binomial distribution in this case or multinomial distribution also is possible. You can also print out the probability values if you're not interested in the class, but I want the probability values. What is the probability belongs to this class or that class? Quick to learn because it's based on linear model, and you have gradient descent to help us out to find the best fit line quickly. Fast in your test data also. In test data also it's very fast. And as I said, many times I have personally seen logistic regression stands out among the top few in many of the situations. Resistant to overfitting, because as a simple linear model, linear models cannot be very complex shapes. It is resistant to overfitting. Okay. Resistant to overfitting does not mean resistant to bias errors. It means resistant to variance errors, right? But we have another one to deal with. And you can print out the coefficients, the probability values, and interpret the probability values. So the model is not a black box, right? Disadvantage in classifications is it uses linear boundaries. What it means is, if the distribution of the classes is something like this, then the model will suffer. Right now we took a linearly separable this thing, but what if the distribution is not linearly separable? Then logistic regression will suffer. If the distribution was like this with overlap, but it was like this, then it will do well. But if the distribution like this on the attribute you have decided, you see the difference? The difference is, if I plot the density graph, okay, in this case, the two density curves are overlapping. Your t-test, analysis of variance, and all these things will tell you that this record belongs to this class, that class, 50-50. It will not be able to classify. On the other hand, if I look at this situation, your overlap is there, but the central values are shifted apart. So when we have distributions which are linearly separable, may not be 100%, then logistic will do well. But you have distributions like this. I don't know whether you noticed, PIMA dataset is like this. That is why in PIMA dataset, you will not be able to get accuracy beyond 70%, 76%. Do whatever you can, right? So, it will not give you beyond 75. When the data distribution is like this, none of the algorithms will be able to help you out.
When we start building this model, we need to check what our data distribution is like.
100% you have to know your data before you start building the models. You have to know your data, which means you have to know every attribute, how the data is distributed if you're in classification, how the classes are distributed, which dimensions or which attributes are able to linearly separate the two classes. Use only those for your classification models. You have some attribute where both the classes are significantly overlapping, including the central values. Using such attributes for building model is useless, and PIMA Indians, you will see all the dimensions are like that.
So this is what we can do actually. We can't do anything. No other algorithm.
No algorithm. Okay. What human brain cannot do, an algorithm cannot do. So you have to have at least one attribute, as you will notice in another data set that is called bank.csv. There also the data overlaps on all the dimensions between the two classes. But there are few dimensions, 2 or 3, where the data central values are separated apart. Based on this 3, it gives you 96% accuracy.
So for our model, we should consider only those.
Only those, yeah, correct. You don't need to include all of them.
What is the name of that bank.csv, that two attributes?
Some attributes, I'm just randomly taking.
What is that gross error?
This is scatter plot. This is scatter plot. Now you find out how the density of the plot changes when you move from this direction to this direction. You will see that the density is very low, very low, very low, increases very high, highest, then it starts falling. So when you convert this into 3D, it becomes a normal distribution. In 3D, this becomes a normal. That is called density function. 3D.
So can't we switch the axis for analysis in this case?
Can we?
Can't we switch the axis for analysis?
Switch means?
Say y-axis becomes x-axis so that you are distributing.
What you're basically saying is, no, I'm comparing these two with this over here. This axis is not there. I'm just saying, if you have a distribution like this, your logistic will do well. If you have a distribution like this, your logistic will suffer. Any algorithm will suffer. Okay? But what you're saying is, can't we switch to this axis where the two classes are separated out? That's what you should be doing. So if you have two axes, two attributes, on one attribute they are not linearly separable at all, but on the other attribute they are linearly separable, use the other one. That's what I'm saying. Yeah, all right.
In 2 dimensions, you can see like this. You can change to 3 dimensions. You can see some of the data are up.
So use that dimension, which is helping you to separate out the two. Don't use this dimension.
Can we apply one model on one attribute and another attribute?
That is what random forest does. Random forest, every node of the forest is constructed using randomly selected features from the data set. Yeah, it internally does that. But random forest is the only one which comes close to what you're asking. No, it doesn't do that. It randomly picks up. It doesn't see whether these are the best attributes. All right. Okay, let's move. Let's do a hands-on. This is the same data set. P-Mandian's diabetes data set. Same data set. Shall we do a hands-on on this? Okay. All right, guys, are you all ready? Okay. So if you have access to the code, the first line is Matplotlib. We already know what it means. I'm importing from scikit-learn linear model logistic regression. Yesterday we had imported linear regression. Okay. Then I'm importing matplot, SPLT, Seaborn. I use Seaborn libraries for my plots. Especially pair plot comes out very well in this. So I'm going to use this. Train test plot, you already know what it is. Numerical Python. And to measure the accuracy of the model, I'm going to use metrics. So whenever you're doing classification, one of the most important tools for evaluating a model is your confusion matrix. Okay. So that comes through this metrics library. We'll see all those things down the line. Earlier, this PIMA diabetes used to be available in UCI dataset, but now I think it has been removed or archived. So it's not available, but I downloaded it from kaggle.com, another site. I'm loading the dataset over here. It's a data file, it's a text file. While loading the data file, I'm feeding the column names here, which I got from the original source, the column names. So the column names are, the first column name is pregnancy, how many times, by the way, this particular test was done amongst Pima tribes, a tribe in South America, where apparently the ladies are prone to type 2 diabetes very early in age. So this research was done by this university, where the objective was, can we build a model and predict who is going to have type 2 diabetes by the teenage? Okay, for that they did research on that community. Some of them were diabetic, some of them were not diabetic, and the characteristics that were captured are these. The first one is number of times pregnancy reported by the subject. The next one is plasma level in your body. Plasma is a component of the blood. Then we have blood pressure. This is systolic, diastolic blood pressure. This one is diastolic blood pressure. Then we have skin, where apparently people suffering from type 2 diabetes in that tribe, they have some kind of skin folds. This is measurement of that. Then they do some testing. This is called fasting sugar test or something. That is this test. Body mass index. PEDI is another test. Some pedigree test they do, I think. It's another test related to blood sugar. Age. And the last one is your target column, whether this person was diabetic or non-diabetic. Diabetic means 1, non-diabetic is 0. Now the whole thing, that the objective is, we are trying to find out, is there a relationship between the independent variables and the target variable? What is that relationship we are trying to find out? That relationship we assume exists in the universe, in the real world. We are trying to find out whether we can discover that relationship. So for that, we are building this model. And I always do this based on the experience on car MPG dataset. When you look for this head, okay, when you look for some sample records, you see all numerical values. But what is a guarantee that there is no record further down which has some non-numerical values sitting in the numerical columns? What is the guarantee? How do you identify that? To identify that, we can use this method. What I'm doing is, I'm using a numerical Python function isReal. This function is a binary function. It's a Boolean function. It will give true or false. This function, I'm applying it onto, look at this apply. I'm applying it onto all the rows, all the columns of this. This is the beauty of Python, where you have to do minimal coding. If you had to do this in Java, you'll probably write a for next within a for next over here. So all that thing is taken care of. So what's happening is, I'm going to apply this function isReal on all the rows, all the columns of PMADF. Okay, and you see this tilde over here. This is a NOT operation. I want only those records where it returns a false. Okay, fortunately there are no records where it returns a false, which means all records, all columns are numericals. What is the other way of finding out whether any such non-numerical characters have come into the data?
Data types.
Df types, that's it. Df types, when you do, it will return the data types of all the columns. If there is any non-numerical value in any of these columns, it will return it as object. That is easier than this, Df types.
What we do if there is a non-numerical?
What we do if there is a? We have to go and identify the record, convert that into NA, NaN, numerical. Then you can replace with median, mean, whatever replacement strategy. We don't have any such case right now, okay? But we have nothing to be happy about because we're seeing a lot of zeros. And zeros in blood pressure is surprising. It can't be, not possible. 0 in plasma is not possible. But you have 0 values in blood pressure, you have 0 values in plasma. So missing values are there. The missing values will cause problems. We need to address the missing values. Okay, let's move on. Do a describe how the data is distributed on the various dimensions. Univariate analysis. If you don't like this, don't do it. Do the pair plot. Pair plot also gives you visually the same univariate analysis. Okay. So I'll quickly tell you one. Look at the difference between, for the test data, the test attribute, look at the difference between the mean, 80, almost 80, and the median, 30. The mean is drastically shifted away from the median on the higher side, which means there is going to be some long tails on the right side, on the higher side. Mean gets easily impacted by outliers. So some outlier is pulling mean towards the right side. How do you confirm that? Look at the distance between the third quartile and this. Look at this. Correct. Look at, you're like me, you don't want to calculate? Can you tell me how long is long? The right side tail, look at the length and compare that to the left side tail. Left side there is no tail. 719 units. So is this possible or is this a typo? We need to go and check. Maybe this is a typo. We don't know. Okay? Right, I'm going to move on. The next thing that you have to do is first understand how the data is distributed on your various dimensions. If you think there are outliers, we need to address outliers. We already know we have missing values, we need to address missing values. The next thing you need to do is, since you're in classification, how many records are available for each class in the data set? Look at that. The number of cases for non-diabetic, 0, is 500, whereas the number of cases for diabetic is half of that, almost half. You are preparing for your board exams, and most of the questions that you solve, practice on, is calculus. A small part you do it on trigonometry. Obviously, you're going to flunk in trigonometry, right? Why? Because the pattern of questions that come to you in the exams in trigonometry may not have been reflected by the patterns that you have used. Which means you have not gone through all the possible patterns in the trigonometry questions. Same thing will happen here. To the model, I have given only 268 of the diabetic cases. Maybe this 268 does not reflect all possible permutations that lead to diabetes. So the model will perform poorly in predicting the diabetic cases. It will perform relatively well in predicting the non-diabetic cases, but I want the reverse. The objective is the reverse. Okay? And keep in mind, whenever you're in classification and the classes are skewed like this, all algorithms are biased towards the higher represented class. All models, the objective is to minimize the overall misclassification. So their focus will be on the higher class. So this is another source of bias which comes into the model where the algorithms themselves are biased. So how do you handle this? Make find it too? Yeah. We call this strategy upsampling, downsampling. Okay, there is a strategy called upsampling, downsampling, which I'll refer to, which I'll take you through when we do FMT, model tuning, but right now we're not going to do that. There is a package available, it's called imlearn, but right now we're going to live with this. There's another way of improving the the classification, performing better in the underrepresented class, that is called modifying thresholds. Thresholds. In logistic regression, naive-Bayes, any other probability-based model, the cutoff is 50%. If the probability of belonging to blue class is 51%, the data point will be classified as blue. If the probability of belonging to the blue class is 49%, the data point will be classified as red. So the boundary is at 50%. Okay, I can modify the boundary. Though none of the algorithms allow me to modify the boundary directly, I can build wrapper class around the algorithms. I build the model. Around the model, I write my own class where I modify the threshold. Okay. Once again, I'll cover this in FMT, not now. It'll be too much. So we can play around with the threshold, modify the thresholds to improve the accuracy of the underrepresented class. We can do that. Okay. How do we do that? We'll take it later. But whenever you see in classification skewed distributions like this, be ready. There's no way you can achieve a very high accuracy for the underrepresented class unless you play around with these two techniques. Let's move on. So this is my pair plot. Okay, I don't like this. So let me quickly redo this. all right, I'm going to come into, I'm not going to do all this, I'm going to come straight to this, where I'm going to say SNS pair plot, comma, dag underscore kind is equal to KDE, kernel density estimate. Since these are numerical values, it makes sense to have this. And hue means color, is equal to the last one, what we call it, target class. So hue is equal to class.
You haven't treated outliers
Not
or
yet.
the zero values. So you just
Yeah, on the raw data. It'll take some time. It's fast actually. Yeah, there you go. Now let us understand this pair plot. All of you have it? Let's look at the very first dimension. The first dimension here is pregnancy reported. Okay. The blue is non-diabetic class, and the red one is the diabetic class. The orange is the diabetic class. Okay. If you look at it, the two distributions are overlapping with the central values. They're overlapping. Very small separation over here. Come to the next dimension. The next dimension is your plasma. Plasma, you see long tails on the left side with a small bump. This is their outliers, the zero values. But otherwise, both the classes, the blue classes perfectly looks like almost like your normal curve. And the central values are overlapping. The central values are eclipsed. So once again, not a very good attribute, but at least we have some differentiator here. Look at this one. Even the outliers are overlapping. This is your blood pressure. These are the zero blood pressure cases. They are also overlapping. Yeah. So there is no way your blood pressure will be able to separate out. Based on blood pressure, you cannot distinguish diabetic versus non-diabetic. There's no way you can.
but if you correct those zero values,
Still, whatever technique you apply will be same technique. So both of them will shift together, right? So we have a problem there. Look at the next one. This is even more surprising. Almost gone. Skin color, not skin color. This is skin fold. Yeah, you see the same problem here also. Every dimension you look at it, every dimension has this problem. On none of the dimensions, except for a few dimensions where you see small difference in the two classes, none of the dimensions are separating the two classes out. So even if you put all these dimensions together and build a model, we are not going to have anything. Yeah, it's overlap, almost this case, the previous case, this one. And that's what we are seeing here. The two classes are overlapping on every day. They are not shifted like this. Let's go ahead and build a model. Let's not be very hopeful about this. Any model will give a problem here. So what I'm doing here is, this is not required. It's not required to be done. All algorithms can take as input the data frame itself. But earlier I used to do this as a practice, where I'm converting the data frame into an array. So data frame minus the column headers is called an array. Okay. And that array, I'm taking the independent attributes into X and dependent attribute in Y. And then I'm splitting this X and Y into train set, test set. Is this part okay with you people? All of you with me on this? All of you, Sairam? You're also on this? Great. Now look at this. I'm instantiating the logistic regression model. You can call it anything you like. I'm calling it model. I'm doing the fit. This is where the best fit line is found and convert into your sigmoid curve. The fit. Once the model has been found, Then I make use of the predict function of that object on test. So these are my predicted labels, diabetic, non-diabetic. The actual labels are Y test. Okay. Some people get confused here, so I'm going to stop it. Don't look beyond this. Just stop here. I'm asking you to just look at this part. Till this point, everything is fine? Okay. Now what I can do down is, I can, for the time being, I'll remove this, okay? I'll put a, yeah. For the time being, just ignore this. Control X. We'll put it over here. Insert cell below, and we'll put it here. All right. I'll uncommit it later. I'll do that. Okay. Now look at this. Have you seen confusion matrix before? Yeah. All of you agree it's exactly what it's called? It confuses people a lot, right? Confusion matrix. So what I do is, as a practice, when I make my confusion matrix, I always keep the actuals on this side. Actual diabetic, non-diabetic. And the predicted, the output of the model on this side. Diabetic, non-diabetic. This is my practice. You can follow the other way, but whichever way you follow only one. How do you control this? Since again Y test first, this is actual, it goes to the rows. Y predict next, this is your predicted values, goes into the columns. If you flip this, you'll flip that. Now what it's saying is, of the 147 diabetic cases in your, sorry, this is non-diabetic, not diabetic, this is ND, non-diabetic, this is diabetic, ND, D. Awfully sorry. If you go and read the source of the data, they are very clearly told 0 is non-diabetic, 1 is diabetic. Of the 147 non-diabetic in your test data, 132 have been classified as non-diabetic. No mistakes. For this class, true positives. Of the 147, 15 have been identified as diabetic. Incorrect classification. These are those values of red lying on the extreme end, values of blue lying on the extreme end. Look at the diabetic class. 84. There are 84 diabetic cases in your test data. Of this 84, 46 have been correctly classified as diabetic. 84 minus 46 is 38. 38 have been misclassified. Okay? Now look at this. Now look at this. What is the overall accuracy? 77%. Looks decent. But let's look at accuracy in diabetic class. Okay? We call it recall. Recall is, the formula for recall is true positives by true positives plus false negatives. Looks very hi-fi, but what it means is true positives divided by row total. So the recall is 46 divided by true positives plus false negatives. This is false negatives. For this class, this is false negative, right? So yeah, so it is 46 plus 38 back to 84. That comes to around 55%. Hey. It's coming like 55, 54%, right? That is like tossing a coin, heads or tails. You don't need a model for this. Right? So to get this kind of accuracy, you don't need a model. You can just toss a coin and say diabetic, non-diabetic. That is what this is. So overall looks great, but don't get fooled by this. What is important is this, but this is what we expected because this is represented very poorly, the diabetic class. This is important for us. Look at the recall for the non-diabetic class. Non-diabetic class, the recall is 132 by 147. This will come very high, 90%, 80%, 90% roughly round. So the recall for the non-diabetic class is very high. Recall for the diabetic class is extremely poor. But that's what you should expect. We wanted the reverse. So that's what will happen when you have situations like this. Okay? There is no way you can get a very good model when the individual attributes are poor attributes and the classes are underrepresented. You can't do it. So the magic happens in the data. How do you prepare your data for analytics? That is where the magic is. It is not in the algorithms. Okay? It depends on data preparation. 80% of our project estimated effort in data science goes into preparing the data. Running the algorithm is matter. Then rest around 15 to 20% goes into fine-tuning your model. It goes into that. All right, let's do, there is a function called score. Instead of doing this, I can directly call score, but don't rely on this when you're doing classification. What this function does is, it regenerates the model and then tests it on this test data. It regenerates the model, then compares the test data and this automatically and gives it the score. Okay, so this has nothing to do with confusion matrix. You can actually run this and say remove the hash, run it. It should give you the score. Model is not defined. Why? What spelling mistake? Oh, I have not executed. I'm just showing you this. Okay. I have not executed these lines. So it gives you overall score, but overall score is not reliable, so don't depend on this. Shall we move on? You need to learn the tricks of identifying good attributes. Feature engineering, feature selection, and that is where the core lies. 100%. Domain. If I want to predict the time taken to travel from A to B, then I should have the domain experience of what are the factors that can impact the time. That's what the attributes they collected are useless attributes. It's not good attribute. I don't know, but the fact is it's not good data set for classification.
Here we see the diabetic class of all your models were biased towards
non-diabetic.
So we cannot be data.
That is what this imlearn does. Upsampling, when you create upsamples, it actually creates synthetic data out of the underrepresented class.
Is it acceptable practice to do that? Or
you have only one choice. Either accept it or stay with this. No, I'll tell you. On a serious note, it is an acceptable practice. It is an acceptable. Finally, what is important to me is the model should generalize in production. That is important to me. So when we release models into production, the models are not immediately used in production. They are put into alpha test, beta test. If after jacking up the data, if the model is performing poorly in the alpha and beta, I will not release it.
It's like pre-prod.
Yeah, it is.
Just because you don't have enough data
it's allowed. Synthetic. See, I'll tell you quickly what happens in upsampling. Okay, upsampling uses k nearest neighbors. So what upsampling does is, if you have two classes, this is underrepresented class, so diabetic class, triangles, and non-diabetic, most of them will be non-diabetic, okay, and there is some overlap here, okay, most of them are non-diabetic class. What this upsampling using imlearn does is, it tries to generate synthetic data out of this. Just one thing, let me finish this. The synthetic data generated is such that it does not disturb this overlap region. It creates synthetic data in these regions. Yes?
But while doing the upsampling, are we not introducing the bias error?
100%, guaranteed.
Yeah.
So we are, by introducing the bias error, we are taking away the bias in the algorithm, which is towards the higher class. We are trying to cancel that bias error by upsampling.
So actually upsampling and downsampling is adjusting the bias.
Correct.
We are actually trading the bias.
We are trading off the bias which exists naturally in the algorithm towards higher class.
Are they exact duplicates or?
No, they are not duplicate. They are synthetic data generated using k nearest neighbors. So I take a random point here, then k nearest neighbors. If you use k nearest regressor, for example, you'll sum up these three and give you the average.
In this case, if you use k-nearest, all our stars will not circles.
No, all are stars, but what it'll do is, it's k nearest regressor. So it's going to take the blood pressure of all three, find out the average, give the average to this new point.
So that can be circular.
That can be?
That can, so there are two classes, star and circle. So if you don't,
it works only on the underrepresented class. It generates synthetic data only for the lower class. So in this case, it will generate synthetic data only for the diabetic class.
Okay, so in this case, like if you take this sample and if you decided to upsample our data, at what point we should stop? Like these many samples would be enough. We should not go further beyond.
It will bring both the samples to 100 same level.
So 50-50 you mean to say?
50-50. It will bring you to 50-50.
can you give us some pointers?
Imlearn. Go and search for Imlearn on Google. You'll find that package Imlearn. You'll see a lot of reading materials there. But we will cover in detail in FMT.
Okay. So when you do downsampling, it will reduce the records of
non-diabetic. It'll really go.
So either we can go with that approach or
don't do your manual approach of deleting the data. Don't do that. That will be the worst thing to do. Anyway, coming back to this. So what the next thing which you're going to try is, since all data is numeric, let's convert all this data into what is called standard scale, xi minus x bar by standard deviation, right? And that's what I'm doing here. From pre-processing library, I'm calling the scalar function. So it converts every record, every column of this data frame into scaled data. Same with test record is also convert into scaled. On that, I rebuild my model and relook at my scores. As I said, sometimes we expect miracles to happen, it never happens.
Which type of scaling does it use? Which type of scaling does it use?
This is z-scores, central values. Yesterday I told you, scaling does not impact linear models. So you won't see any impact. There's nothing else we can do. It converts in z-scores, xi minus x bar by standard deviation for every column. Centralize the data to 0.
So we have a few ways. One is either we do upsampling or downsampling. But right now we don't know which is okay. So we need to try with both and see.
Exactly.
But will that really affect if we do an upsampling?
100%. It will affect the accuracy of the recall for the diabetic class. 100%.
No, I mean doing an upsampling or downsampling. I think we can go for either choice. Or compulsorily we have to go for both the choice and then.
That depends on how your data is distributed. It depends on that.
like both and see whichever will be more accurate.
It depends on that. Okay, it's a very subtle relationship with the data distributions in the various dimensions.
So the only solution is
and the threshold management, changing the thresholds. 50% is the threshold, no? So I can say whenever probability is less than 30%, it belongs to red class. Above 30%, it belongs to blue class. I can change the threshold. Right now, by default, it's 50%. If probability of belonging to red class is less than 50%, that means he belongs to blue class. Right now, it's that. So that 50% can be changed to 30% by building wrappers around this model. The number of records is what you have in your data. Threshold is in your sigmoid curves, okay, sigmoid or any probability-based algorithm, this is my probability dimension, 0 to 1, 0.5. Whenever a function, this sigmoid function says the probability is greater than 0.5, 0.55, 0.56, then it will automatically say that this record belongs to the blue. If it is below 0.5, it will say it belongs to the red. So I can bring down this threshold and I can put it over here, 0.3. Anything over 0.3 belongs to blue, anything below 0.3 belongs to red. So by changing the threshold, I can control the misclassification of the diabetic cases. No, it's not a parameter. You have to build a wrapper around your model. There's no automatic way of doing this. So I'll use a function in scikit-learn. It's called binarize. In case you're very impatient and you want to know what it is, please go and explore this function binarize, B-I-N-A-R-I-Z-E. How using binarize we can control the threshold, explore that. If you're not able to find, I'll tell you how to do that in FMT.
We hope you liked this complete tutorial on data science. Great Learning offers high quality, impactful and industry relevant programs to working professionals like you. Our faculty pool comprises of leading teachers and industry practitioners in the field of data analytics. For more information, check the links in the description down below. Don't forget to like, share, and subscribe. Remember, the only learning that matters is great learning. See you in our next video.